Hello, 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 hello. Check one, two, three. Hello, mic test one, two, three.
Very good morning. Respected Chairman ISRO, Secretary DOS, Shri Kiran Kumar Sir, Chair Apex Science Board ISRO, senior members from academia and institutes, researchers, Director RRI, Koteshwar Rao Sir, Alex Sir, and all the dignitaries who have joined offline and online to ISRO platforms. Good morning to one and all. I take this opportunity to welcome all of you on behalf of ISRO. And today we have gathered to be ready for the scientific usage of the data from the XPOSAT mission. As you are aware, the mission carries two instruments. The primary instrument is POLIX, which would study the polarization from the X-ray photons coming from celestial objects, and an instrument called XPECT. So during the courses of deliberations, we will come to know the different aspects of both the instruments. They're covering different energy ranges. And let me tell you, on this auspicious occasion, we are very happy to have received you to discuss about the utilization of data of this important mission. And on one hand, when the preparedness is going on to scientific data. So both are happening together. So this gives immense happiness to all of us. So in this happy occasion, I now request respected Sri Somanath Sir, Chairman ISRO Secretary DOS, and Shri Kiran Kumar Sir, Chair Apex Science Board, to kindly grace the dais. Sir. So I take this opportunity once again to welcome all of you formally. And I now request Shri Kiran Kumar Sir, Chair Apex Science Board, to address the scientific context of this mission. Sir, over to you.
Good morning to all of you. Somnath, Chairman, Secretary, Department of Space, and all of you who have gathered here today for this program. And as already pointed out, the importance of X-ray polarization studies is an endeavor where you are trying to bring in new parameters available to you for observation and make use of that for improving our understanding of how things are happening in astronomical area. And today's meeting is primarily to not only enable, but also appreciate how prepared we are for dealing with this data and what kind of interactions are needed, and learn from our previous missions inadequacies, if any, in dealing with the information transfer and also the use of this information. So in that context, today, all of us have gathered here where we will also be told about the status of the mission, where the instruments, how they perform, and more than that, we are going to look at what we can do with the data when it becomes available and how we can move ahead. Because today, as the country is changing the way it is looking at the space activities, importance of space science being actually part of a larger community where the community is really active and pushing things is important. And it's in this context today's meeting needs to be looked at. And I wish today's deliberation a great success in both enabling us to conceive of systems for future and make effective use of what we are going to get from this mission. Thank you.
Thank you very much, sir, for telling about the scientific context and the importance of this mission. And at this juncture, I would request Chairman ISRO, sir, to kindly deliver the inaugural address. Over to you, sir.
Morning, all of you. Kiran Kumar, sir, Dr. Alex, Koteshwar Rao, sir, Director of Phenomenal Research Institute, and all other dignitaries, the mission team of XPOSAT. My greetings to you all on this occasion of the user meet, which we consider as one of the very important element of the preparedness towards any mission. Like we build the satellite, we have to also build the community. Otherwise, a science mission will naturally become the utility of only one person or one idea, etc. So that is another issue that we are seeing. From conceptualization, realization, go through a huge amount of review, understanding, bringing more people into the domain to make use of the data, etc. So this has been the culture that we have been building in the science mission. I think all of you are aware of those heritages that has been built in the past. When we started building even the very first scientific missions in the early 80s or so. And this community is not only in ISRO, it's also beyond ISRO, other scientific institutions, academic institutions. And we also bring in a lot of young people to look at this data and bring value to it by working on it, researching on it over a period of time. Some of the earlier missions are very great testimony to this, including the Chandrayaan mission, the Astrosat missions, and of course Mars Orbiter mission as well. Because I'm not mentioning about the previous scientific missions of ISRO. So building the community has generally been done through this process of interaction, especially the users meet, and also taking projects under this data utilization programs, which is run by the Science Program Office, which is supported by sometimes with the Respond program or some other routes. So this actually produces some good scientific outcome and result, justify the investment that we made for building the satellites and launching it. First of all, we have to understand that it is not a low-cost process. Building a science payload, putting it on a satellite, launching it involves thousands of people's work and a huge amount of money to make the scientific mission happen. That implies that the utilization of this data and results should produce a corresponding result. Though I can't say in terms of the money, in terms of the value for the effort, but it has to justify for itself. Otherwise, it doesn't mean taking up such missions. Just not for that it adds some extra value to what has already the knowledge has been created in this domain. This has been a point of contention, has a point of discussion in most of the debates that happens in the science mission domain. And this is also one of the important bottleneck that we face in proposing new science missions as well. How good the data is utilized, how much value it creates in the community of scientific community, and how it progresses the nation as far as scientific capability building in this domain are concerned. These questions are very pertinent questions. So it's very important that we address them, not simply say that it is a great value. It doesn't mean a value unless you are creating the type of pool of scientific community and talent that will sustain this activity for a longer period, not for just that publication, which may be of high value. So it is very important to create the family or the pool of talent in the country, in the domain, which is very, very important. So talking about it now, we have come to the point that we are trying to bring in people. I think this bringing in people is also a difficult task. Somebody builds an instrument, which is again normally the idea or the push of one or two people, not all those people. This generally happens. Even in this case also, you'll understand the very important payloads are built not by the entire science community, but it is also built by some people who have the engineering talent to convert the scientific goals into an engineering product that can be hosted on satellite. It's also equally important. How to convert the need of the measurement into an instrument and make a very reliable, good instrument is also a challenging activity in this country. And I'm very happy that this has been reasonably well addressed in many institutions with the support of ISRO and other labs. We have been able to build very satisfactory detectors, measurement systems, data collection methods, data dissemination methods, of course, so which ultimately leads to the scientific finding. I think this skill also has to be enhanced. But of course, even now it is a very strong skill that is available in the system. The recent examples are the launches of the Chandrayaan-1 Mars Orbiter mission, which produced excellent results. Even those instruments that we are going to fly in Chandrayaan-3, Astrosat, very unique observational platform, which produced a multispectral observation of the universe. Even today, these instruments that we are hosting here are also very unique, built by the skills of our own people. But this, of course, requires further enhancement and work, in addition to the scientific outcome that will come out of the data. And we need to support that community which works on the engineering side of it. Of course, the unsung heroes are the people who will build the satellite finally, look at all the missions and put it there and operate it, and even the launch vehicle people who are forgotten just after the launch. So should thank all of them for their wonderful work they are likely to do in the future, for much before the data is available. So we should also congratulate them, thank them for their effort at this moment. Without that, this mission is not possible. Now, coming back to today's discussion, I think we will be hearing quite a bit about the mission XPOSat itself on the satellite, the payloads, the polarimetry, why we are putting it, and what are the observations possible with it. There is a science possible. I think my suggestion is that you have to really not look within what currently that are available. It has to be expanded. I understand the XPOSat user community is actually very small compared to many other user communities that we have created for other science missions, which is a point of concern at this moment. So we need to expand it. We need to also to create maybe little more talents in the institutions and organizations to look at it, even if some people stop and go further somewhere away. I think the continuity of observation, utilization observation becomes important, and making science out of them is very important. Let us catch some younger people in institutions and mentor them to do this work for the future. It's the only suggestion I have at this moment. I also want to say great work done by rest of the people in terms of the data, the utilization, the data chain. All of them have been addressed and well created. If you find any gaps there, it need to be addressed, because it's very important before the mission is taken up. All those chains are prepared and well in advance. They are ready with it. Also specifically thank the payloads builders. It's very, very interesting payloads. And the engineering of it's also very unique. And I'm very happy that it is going through very well today. So thanks to all of them for making such interesting science mission possible. This year is going to have a lot of science missions. All of you know that we are going to have the Chandrayaan-3 launch, the Aditya L1 launch. Both are very interesting science missions. And added to that XPOSat as well. So it's add a lot of them to our kitty for the community to be really excited. And many other discussions are going on for such similar missions, but not reaching to the final definition, primarily on account of such issues which I mentioned earlier. Hope the country will feel much more confident about us, our ability to do such missions and produce good result ultimately. Thank you so much, and all the best for the today's discussions and the conclusions that are yet to reach. Thank you.
Thank you very much, sir, for your address, and especially bringing out the role of the academicians and scientists to spread and catch the early career researchers young, and to expand the scope of the domain of X-ray polarimetry in the country. And at this juncture, ladies and gentlemen, let's today's meet. I will speak a bit about the today's meet. It is divided into 4 sessions. In the first session, it is dedicated to the mission, details of the mission and the instruments and the payload proposal processing system. While the next subsequent 2 sessions, 2 and 3, they are going to deliberate on the significance of, how to utilize the scope of utilization of the XPOSat data. That will be covered in session 2 and 3. And finally, the 4th session will be dedicated to a discussion, open discussion, on how to expand it further to rope in more people, young people in this field. So this concludes the introductory session. And before we start the scientific sessions, we will take a short break for group photography, which is going to happen outside and which will be followed by high tea. And high tea is arranged downstairs in the food court. And after that is over, the sessions will resume at 11 o'clock. Thank you very much. Good morning and welcome back to the scientific sessions of the ExpoSat User Meet. And in this session, we have 8 deliberations, mostly on the mission and scientific instrument. So this session will be chaired by Director of Raman Research Institute, Dr. Tarun Saradif. So I welcome you, sir, to chair this session. And before you chair the session, I would request you for a few words from you, sir. Over to you.
Good morning. It's particularly a great pleasure to be here at this, ExpoSat users meet, and also to chair this session. Partly because when I came into the institute already, I saw a very dedicated team, putting in a heroic effort to put together one of the payloads, and it shows you what it's needed, what Chairman ISRO told us about the effort that goes into building such a mission. And so I hope that, during the day we would, come up with plans for how best we can grow a community around it that can do the mission very successfully. And, Raman Research Institute, as I often say, we are committed to be a academic partner to efforts in space because of the number of programs that we have, including some radio-based and about the quantum secure communication, where we are trying to put in what we have as scientific expertise at the disposal of the space program of India. So we have a very interesting session describing the Polsat, ExpoSat, and then describing the mission as well as how the data would be processed. I also understand it's a long day, so I would request all my colleagues speaking here to try and stick to the time. So if you have a 15-minute slot, please, I'll give you a bell at 10 so that you can finish by 12 with some time for questions. With this, let me invite Sri Murugan, who is the project director of ExpoSat, to tell us about the X-ray polarimeter satellite mission.
Respected Chairman ISRO and Chairman of the session, and our beloved Karan Kumar sir, Alex sir, Kodishwar sir, and all other my seniors who guided us in ISRO and in ExpoSat fabrication, ExpoSat mission also, and my colleagues and all users. I welcome you to this session and good morning to all. With this small introduction, with the permission of Chairman's session Chairman's permission, I will start the presentation. Right.
morning, all of you. So I'll be presenting the constraints which are considered. Yeah, thank you. So during the payload operation in XPOSAT, some of the constraints have been considered before actually planned for the payload observation. So I'll be going through those constraints in this presentation. This is a list of the constraints which we are considered. The first one is the source to sun angle. Basically, if any source out of 54 sources which are given by our payload team, on a given day, only few sources will be visible. So how do we decide out of 54 sources which source has to be seen in a given day? That is decided by going through these constraints. First one is the source to sun angle constraint. Basically, we have a one expo viewer module which is provided by our FDG team, Flight Dynamics group team, which estimates what is the whether this source, particular source, is visible or not on a given day, and also it considers the source should be operated or the observation should be done during the eclipse time when XPOSAT is actually in eclipse, and also it should be done. It should also ensure that it is not going through the SAA times. So whenever the satellite is going through the SAA, South Atlantic Anomaly Zone, then the payload should be switched off. Expect will be switched off, and the POLIX payload will be switched to low voltage mode. And also, out of the two star sensors which are mounted in XPOSAT, at least one star sensor should be away from the Earth and seeing the deep sky. That constraint also should be considered. Yeah, this is one. Actually, we are seeing this circle is the equatorial plane. We are seeing from the North Pole. So, in Earth-centered inertial frame, this center of the circle is the Earth center. So, from the Earth center to any X-ray source will be inertially held. This is our reference actually to measure the angle. So, we all know that in the Earth-centered inertial frame, Sun will be actually revolving around the Earth. Actually, it's a relative motion. So, we know that Sun moves 1 degree per day, and whenever in 1 year it completes one rotation, whenever it comes to this position where it actually makes 100 degree from the source. So this is the zone. Actually, for Sun position from here to here is the duration where that particular source is assumed to be visible. In fact, you can see here that the number of days for a given source is not constant. So different sources will have different days of visibility. This is because not all the sources are close to the equator. Some sources are actually elevated. Their declination is as high as 60 degree. So because of that, whichever source is having more declination, they are visible for more duration, like 113 days. And whichever source is very close to the equator, they are less visible, like 66 days. So accordingly, we have to plan all the observations. This is how the eclipse duration vary in this 650 kilometer, 6 degree inclined orbit. So it varies nearly from 33.5 minutes to 35.5 minutes per orbit. This entire graph is actually taken over 1 year, that is nearly 5,400 orbits. So this pattern is going to repeat every year. Yeah, this is the SAA duration, South Atlantic Anomaly. Actually, this is the zone where the charged particles from the solar wind are actually drifted towards this zone due to the gradient in the Earth's magnetic field, and they are actually confined to the South American region. So we have to ensure that the payload is not operated in high voltage mode during this zone. Whenever XPOSAT is passing through this zone, we have to ensure that it is switched off or switch it to low voltage mode. So for that, what we are doing is in the ground, we are computing the times when XPOSAT is actually going through this zone, and we are trying to avoid that zone by the ground planning. So, this is how the SAA duration per orbit varies for the 6 degree inclined orbit, and this also has taken actually for 1 year, that is 5,400 orbits. And we can see that here actually there are some cycles which are a 45-day cycle. So for 6 degree inclined orbit, the orbit regression cycle is 45 days. That means the paths are actually I'll just go back to the previous slide. When a 6 degree orbit is run over 1 year here, so in 45 days, whatever the ground pattern goes through this zone will keep repeating every 45 day cycle. So that's why the peaks are coming every 45 days here. So out of 5,400 orbits in a year, 2,800 orbits will have a SAA zone, SAA occultation. Sir, actually, yeah, actually 4 degree is better in terms of SAA, but the problem with 4 degree is Bangalore is not visible. So that's why there is a trade-off actually whether Bangalore also should be visible and SAA also should be able to manageable. That way, in fact, AstroSat orbit is actually considered for this purpose. So the study wise, we have taken both considerations. So one is yes. Even 5.5 is also manageable, sir. In fact,
Not manageable. What is the optimum from these considerations? See, suppose lower than 6 degrees, there is an improvement.
okay.
Every,
Definitely, sir. That's what. Actually, if you keep SAA as a factor while deciding the orbit, then definitely 5.5 degree is better orbit than 6 degree in terms of SAA. But if you go to more and more close towards the equatorial plane, the visibility, number of visible passes over the Bangalore will come down.
yeah. They are saying this.
Okay, sir. Anyway, I'll repeat the study, but the study has
No,
been
you
done,
can
sir.
repeat.
Yes,
We
sir.
have done this for AstroSat also.
Yes, sir.
The lower inclination, you don't have visibility problem. Higher inclination, when it goes to south only, you have the problem. Okay? Lower inclination, this problem should not be there. If PSLV can give a lesser inclination, as the chairman also was asking that question, I think that should be considered because it solves your nearer to zero actually is preferable. And you can make a study, it will not affect your visibility 6 to 0 also.
Sure, sir. Definitely, I'll repeat the study.
And,
Just
and sincerely, you explore the possibility of PSLV giving a lesser inclination. Because from the mission point of view, 6 to 0, it doesn't matter for observation. But for South Atlantic anomaly point of view, nearer to 0 is better. And this constant almost will be removed if you are near 0.
yes, sir.
And you can have a study. My feeling is ground visibility will not get affected.
Sure, sir. Definitely, I'll take that action to revise the study. So this is the plot where all the 54 sources are actually plotted along the x-axis here. So every source, how many number of days are visible in a year? That's what is actually shown in this pink curve here. So we can see that there are some sources which are having a better visibility, more than say 90 days in a year. These are all high declination sources. So and the sources which are close to the equator, as I mentioned earlier, they are having relatively lesser visibility duration. Yeah, this slide actually already Murugan sir has completed. So this I'm going to skip here. Anyway, in fact, this slide actually compares 6 degree and 30 degree. Initially, there was an action for mission that to study the impact of change in the orbit from 6 degree inclination to 30 degree inclination. So how it is going to affect, whether the payload observation duration is going to affect. We have made a study here. So what happens here is from 60 to 30 degree, 6 degree, we have a average eclipse per day as around 500 minutes here, which is going to reduce a relatively smaller margin, that is 495. But SAA duration wise, as Koteshwara sir was already mentioning, the SAA, what happens is SAA duration is more for 6 degree, but for 30 degree, what happens is because the number of passes going through the SAA zone has reduced, so the duration also reduces. But relatively, if you observe, SAA-free eclipse duration is what very important for XPOSat for operating the payload. So that remains more or less a constant for both 6 and 30 degree. So that way, from 6 to 30 degree, both orbits are in between any inclination is also cleared by our payload team also, and we have studied all these orbits in between 6 and 30. Yeah, this is on typical mission profile, where as Murugan sir already pointed out, during the sunlit zone, XPOSat will be sun pointing. where the negative pitch axis, which is our solar panel normal, will be pointed towards the sun. And our reference for switching from sun pointing to star pointing is the source viewed start time. So it can be many times actually source view start time is also eclipse entry. For many sources it happens. So whenever source is visible before eclipse entry, then we consider eclipse entry as our reference point. So from that 10 minutes before itself, forward maneuver from sun to star pointing will start. And 7 minutes this maneuver will continue. And we'll wait for at T1 minus 3 minutes for inertially. Basically, we go to inertial star pointing here and wait this 3 minutes we'll wait just to get the star sensor updates. So any error in the during the rotation, any scale factor error or misalignment error will be corrected here with the star update, and then spin will be started. This point onwards, at T1 onwards, a spin of 1.2 degree per second will be imparted on the pitch axis of the body, and it will be continued throughout the eclipse zone. And at the eclipse exit, this source view end time is also eclipse end in many cases. So that will be taken as a reference, and 5 minutes before that, the reverse maneuvering will be started from star pointing to sun pointing. The entire scenario, the mission profile is actually
during that period, observation is not valid. That 5 minutes.
Exactly, sir. You are right.
No, why do you need to do that?
But we have to come back to.
No, you can come back a few minutes later also. Is it so critical that right at the start you should be sun pointing? See, you should maximize the capability for observation.
In fact,
why are you wasting 5 minutes?
Definitely, sir. In fact, that was the plan initially. So both the forward maneuver and reverse maneuver were done in sunlight. So because of our thermal design analysis, they said at least one maneuver should be in eclipse. So that way, actually forward maneuver was done in sunlight, and the reverse maneuver were actually shifted, preponed to eclipse zone.
I think
it is because of the thermal design.
No,
anyway, we'll again go
you
through.
should look at it very carefully.
Yes, sir.
See, I don't think we should waste the opportunity. As it is only within eclipse you are able to make. Okay. Even if you say 1 minute, it's important.
Sure, sir, definitely.
I don't say that all 5 minutes you take out, but at least do critically to smaller resolution elements, and then conclude that beyond this I cannot do. Okay. See, right now you have taken 5 minutes there and 3 minutes here as a liberal margin, I would say. You do it to a finer tolerance. Definitely. And then conclude. At the end, if it comes out even 20 seconds, 30 seconds, it's okay. Don't compromise on either thermal or this, but don't give extra margin.
Yeah, definitely. Because entire thing is a ground planning. So anytime we can actually refine the study and revise it.
Okay.
So definitely we will take that. Yes, sir. Definitely. The entire scenario is actually made a video. In fact, we can see here the pink axis are actually the Yarrow pitch axis of the XPOSAT. The cones here, what we see are the star sensor FOVs, and the yellow vector here is the sun vector. So right now we are actually in the sun pointing inertial, where the negative pitch axis is aligned towards, this is pitch axis of the satellite, and the negative pitch is aligned towards sun. This is a sun pointing. Right now we are in sun pointing. And we can see that at least even in sun pointing time also, at least one star sensor will be away from the earth. Actually this zone is the earth. We can take that this bottom of the screen is the earth. And we can see that forward maneuver from sun to star has already started. So now the pitch axis is actually going and aligning with this green vector. That is the star pointing. That is the star vector. Till star is actually seeing towards the earth only during the maneuvering. So whenever we actually aligned with this body pitch axis aligned with the star vector, we can see that it is actually coming out of the earth. It is just come out of the earth. I'm not able to show you the earth here. Actually, there is one small curve here which shows the earth edge here. So the spinning started here. Now 1.2 degree per second rate is imported on the body, and we can see that one star sensor will be occulted by the earth and one will be seeing the sky. That way, at least one star sensor during the observation will be clear from the earth for getting updates. Actually, this rate has not increased. I just forwarded to finish that 30 minutes quickly. Otherwise, a rate of the body is 1.2 degree per second only. At the end, we are spinning down from 1.2 to inertial, and then reverse maneuver for star to sun started. At the end, we are coming back to sun pointing. where the negative pitch axis will get aligned towards sun. Yeah, now we are in sun pointing inertial. So this is also matches with the eclipse exit. Completes my presentation. Five, sir. Actually, one rotation, 0.2 RPM. So 5 minutes is required for one rotation. So 30 minutes, if I observe, nearly 6 rotations will be. 5 to 6 will be there, yes.
They have to do the integration.
Yes, sir. Actually, same source will be viewed again and again, every orbit for nearly 1 week. As Murugan sir was pointing out, some sources, transient sources will be seen for longer time and some sources will be seen for lesser duration. So, same source will be viewed all orbits, every eclipse for almost 1 week. So, that way they will integrate all the observations time.
Takes to integrate. They have given any time or anything?
So as of now, 1 week to 2 weeks is what we have understood. So maybe if some sources require more duration also, maybe Dr. Paul can confirm whether.
And what is the field of view? You talk. Okay. So every orbit to next orbit, after all the maneuver, you have to come to same point within 0.1 degree, right?
Yes, sir. Yes.
Madhu, your forward maneuver, what is the angular rate? At what rate you are moving?
Actually, we are going with acquisition maneuver. So maximum 1 degree per second.
Now, why I am asking is,
Yes, sir.
the star sensor
Yes,
may be still tracking. So that 3 minutes, whatever you have allocated
Yes, sir.
for updates,
Yes, sir.
that may not be required. This is in view of what Kiran Kumar sir is telling, that you have to optimize the maximum time for observation.
Sure, sir.
You carefully look at that. If it is in still the track, you don't need to wait for 3 minutes.
Sure,
That is one.
Maybe
The
after-
second part, the thermal part, you go to the package qualification or acceptance, what levels it is tested.
Yes.
Based on that, you take a decision of that reverse maneuver also. I think there is a possibility to increase the observation time.
Sure, sir.
Thank you. So we have had quite a few questions. So last question from there.
Yeah. One last question is basically, sir, as already triggered, you were telling thermal
Hold the mic
constraint.
closer.
So actually peak load on the satellite is when we are doing maneuver. That's what in the initial slides PD had mentioned 600 watt. So if only conserve that energy and use it for that thermal control, if it is really thermal issue, you can definitely extend the usability of full
Observation time.
eclipse
Yes.
duration for
Yeah.
observation.
Sure, sir. That action is already taken. We'll analyze, revise the thermal analysis again.
Thank you. Thank you, Shri Madhu. So we will move on to the part where we are discussing the payloads. The payload POLIX would be covered by 2 talks. I'd request the questions are held till the end of the 2 presentations, then can be taken together. So first, I invite Professor Vishwajit Paul to tell us about the instrument capability and major science goals of POLIX.
A very big moment for POLIX and Exposat to have so many interested people present here to, who are looking forward to do science with POLIX. Before going into details in my talk, I would like to say that right now there is not enough time to thank everybody who have contributed to POLIX directly, indirectly, in various ways, guiding us through very difficult times. And it's indeed, we are here today because of contributions from not only the team of people who work directly on it, a whole lot of people at various ISRO centers outside ISRO, who have helped and guided us. So I express my gratitude to all of them. It's because of all of your support that we are here today. So XPOSAT satellite, POLIX is the central instrument, and this is the main detector part. And here are the electronics modules on both sides. POLIX works on a principle that is known to us for more than 100 years, Thomson scattering. X-rays which come from celestial sources are to be scattered from a low atomic mass material so that you can minimize absorption of the photons in the scatterer itself. So it requires low atomic mass material with low impurity. If some fraction of the incident photons are polarized, they would tend to go in a direction where the electric field vector doesn't have to change. So they would tend to go in the, as shown in this diagram. If the electric field vector is this way, they would tend to go here or there. So polarization has an intrinsic ambiguity of 180 degree. The energy band that we have chosen, initially our goal was to work in 5 to 30 kV band, but because of the scatterer that we had to settle for, it's actually 8 to 30 and with some capacity to go beyond 30 kV as well. This is the range where Thomson scattering is the only way of doing X-ray polarimetry. At lower energy band, one can do with photoelectron tracking, with which the NASA mission IXP works, that's in lower energy band, or Bragg reflection. And at higher energy, one has to necessarily go for Compton scattering, and there are discussions going on for future Compton scattering polarimeters as well. This is the intermediate band where Thomson scattering is the only way for measuring polarization. And that's what has been used on POLIX. The whole instrument consists of a collimator. Right under that, there is a disc, which is the scatterer. The photons, after going through the collimator, after getting scattered from the disc, go into the 4 detectors. Okay, the detectors are operated using drive electronics, where the high voltage is generated and controlled. Each one has its independent drive electronics, and then there is signal processing electronics and also power electronics and telecom and telemetry interface, data interface, etc. on these 4 electronic boxes. An instrument of this kind, Thomson X-ray polarimeter, has low scattering efficiency, no matter what scatterer is used. A lot of photons get forward scattered, get double scattered, and so on. There is a lot of loss of photons in the scatterer and in whole scattering business. Plus, since the scattered detectors have to be scattered photons have to be detected with detectors surrounding it, the detector effective area is rather large. So these instruments naturally have large internal background. That decides the sensitivity for such instruments. And this is also one of the reasons where, in X-ray astronomy, X-ray imaging, X-ray timing, and so on, X-ray spectroscopy have been explored to great detail, but polarimetry has been sort of left behind because polarization is rather difficult to measure. A closer view of the instrument, if you remove one of the detectors, what you see is inside of the detectors, there is a wireframe. And in this wireframe, we have vertically running anode wires onto which the high voltage is applied. There are 12 of these anode wires and a very large number of cathode wires, then anti-coincidence cell also surrounding it to reduce the charge particle induced background. So what we tend to do is, or want to do is, the scattered photons will get absorbed in gas cells defined by these anode wires. We need to identify which anode wire this has been absorbed, and that's what helps us to measure polarization. And that is done by a method called charge division. So there are total 12 anodes. 6 of these are interconnected. They are resistive anode wires. And if an event happens near one end, that end will get a larger fraction of the charge, and the other end will get a smaller fraction. But just taking ratio of these two, we get the position. That's how it works. And then this whole instrument is to be rotated around the viewing axis. So effectively, each one of these wires is a detector. And each one of these wire, therefore, is also a polarimeter. As it rotates, it has ability to measure polarization. The data from all of these are then to be shifted and added to get the combined response from the instrument. Inside of the detectors, if we see, this is the detector housing in which this is an exploded view. The wireframe sits on, it's covered by a mylar window, which restricts the gas to within the detector volume, supported by a top plate on top, and this is one area The detector wireframe, we had a lot of problem, which in fact took almost 2 years to resolve, and that led to a delay in the mission. But finally, all of that has been overcome. The collimator, which restricts the field of view, is also unique in a way that the holes in these collimators, which are hexagonal in shape, this is just to ensure that we don't, minimize the effective area loss. These hexagonal holes are actually slightly tapered, giving us a flat top response. If we have a parallel anode cells, then that would have a triangular response, and very near the peak, we would be insensitive to polarization, because even small jitter on the pointing of the satellite would lead to variation in count rate, and variation in count rate is what we are looking for. We are out to measure that. So the top of this collimator, this response has been flattened by making the collimator hole slightly tapered. There is a little compromise in effective area of about 10% because of that, but this helps us mitigate any pointing offset within that range, plus minus 2 degrees, and we therefore require the satellite to be pointing with an absolute accuracy of plus minus 0.1 degree. These are details of the instrument. Total photon collection area 640 square centimeter, Erangi range 8 to 30 keV. Actually, for bright sources, very bright sources and hard X-ray sources, sensitivity can go up to 50 keV as well. The scatterometer is beryllium. The whole instrument weighs about 130 kg, and you have already seen the dimension. It peak power is about 68 watt. Polix payload is meant to be on at all times. Only during the passage of the satellite through the South Atlantic anomaly region, the high voltage will be lowered instead of switching it off. So Polix will be generating data therefore round the clock. During low voltage mode, there won't be any X-ray event, but it will still continue the data stream. These are details of how the electronics is designed. There is a detector. Each detector is operated by a front-end electronics. Data from this is processed by a processing electronics, and each one has a housekeeping electronics as well. So all of that makes one chain, and it's power electronics. All of that makes one chain. However, there are some common units like the central data processing unit, which collects data from all of them, and the telecom and telemetry unit, which interfaces with the satellite and interfaces with the payload also. So therefore, the common electronics and telemetry telecommand unit, we have redundancy. Rest of it is a single chain. This is 4 such chains. So there is a lot of redundancy in Polix. So now coming to what kind of data Polix produces. Once you have an X-ray event detected, its time is recorded, which detector, which channel, and within that channel, the pulse amplitude at 2 end is recorded. So from the pulse amplitude, if we make a histogram of the charge ratio at the 2 ends, that is ratio at 1 end divided by total charge, the photons get distributed in this kind of pillars. Each one of these pillars represents one of those anode wires. So we need to identify these pillars basically. And the gap in between is basically the gap at the edge of the detector. So Polix in some sense is a self-calibrating instrument. Therefore, as you have this data, you can clearly identify which anode each event has come from, and that's all the identification we need. Plus the time needs to be recorded. And at that instant, what is the orientation of the satellite, that needs to be known, and a total pulse amplitude needs to be known. So these are the information that is needed to take the next step of measuring polarization with Polix. These are the energy response of the instrument when you shine it with monoenergetic resources. In one of the detectors, some anodes have a different charge gain, which is known and calibrated. So this will be corrected data. And when you shine it with X-ray sources, by shining X-ray sources at the central region, this is some data acquired during thermovac, which shows the expected performance of the instrument. Photons getting detected in all 6 anodes. So what is needed from the satellite with this instrument to do polarization measurement is that it needs an absolute pointing accuracy of better than 0.1 degree. The satellite has to be spinning around the viewing axis, and about 0.2 RPM is what has been decided, and that is fine. And observation durations will be long, from running from 1 to 4 weeks on a single source. That depends on the source intensity, not so much about whether the source is persistent or transient. It's the total intensity of a source that decides how long the observation has to be to achieve a certain polarization level. So each of these anode wires, as the instrument rotates, would give us a modulation curve. Now, one anode may not have enough sensitivity to derive the modulation curve. From ground simulation, we know what is the phase offset between each one of them. So we need to correct it for its phase and then add, and that for a given source observation would give us something like this modulation curve, and the amplitude of this modulation is the degree of polarization in the source. The phase of this modulation is the orientation of the polarization vector in the sky, on the sky. So these are some photographs of POLIX. This is total integrated system, and this is with only 2 detectors. You can see the scatterer. This is POLIX just before going to thermovac, before the MLI was put. This thermovac tests are performed in the month of March this year successfully. So POLIX gives an effective area, even though the instrument is very big because of its inherent nature of Thomson scattering and subsequent reabsorption and loss of photon, about few square centimeter up to 30 kV band. And at higher energy, even though the instrument, these instruments will have higher background at higher energy, but good thing is that in xenon gas, just after 34 keV, the effective area is much larger. Xenon K is K shell electrons energy is about 34 keV. So just above 34 keV, xenon has larger cross section. So therefore, the effective area actually increases at higher energy, giving us some sensitivity at higher energy as well, even though POLIX was designed between 8 to 30 keV. The sensitivity is shown here for 100 to 1 crab intensity of sources for different durations of 250 kilosecond, 500 kilosecond, and 1 megasecond, which would require weeks to several weeks of integration to achieve. And so the sources that we would be looking for and the kind of science that POLIX will enable us to do, it includes several types of sources, mostly accretion powered compact stars. So if you look at the brightest of this class of sources, I will show you some of the sources and some details about them. If we look at least in the early days of XPOSAT, we would target sources which are in this band, about 400 millicrab to above 1 crab. And we have very interesting science to do with these sources. The expected degree of polarization in these sources is in the range of about less than 10% to about 20% or so. In fact, data obtained with the NASA satellite does show that many black hole sources, this trend is seen that the actual degree of polarization in these sources increases with energy. That puts POLIX in a very favorable situation to do this science. So what kind of science shall we do, or this enables? Of course, we are looking forward to learn more about it from people present here. One is neutron star, accreting neutron star. You have material falling onto the polar region from where radiation comes out. The soft X-rays get Compton, inverse Compton, suffers inverse Compton scattering. They get Compton upscattered, and hard X-ray photons come out. Some of those photons, while coming through the magnetic field line, produces signature of cyclotron absorption in the spectrum and so on. But this radiation, when it comes out through the magnetic field, should be polarized, because radiation passing through magnetic field has different cross section in the medium. So we expect to measure polarization in accretion powered pulsars, and they are predominantly in the hard X-ray band. These are hard X-ray sources. So if a source is emitting primarily towards the polar region, or if it is emitting towards the equatorial region, the polarization signature should be different. These are the things that we would like to probe on accretion powered pulsars. And of course, the accretion column structure itself changes significantly with the amount of mass accretion. So if we make the polarization measurement at different intensity states of these sources, that would give us clue towards accretion column structure and its changes with mass accretion rate in this kind of sources. What is expected from these sources were initially estimated a long time ago, and there are efforts going on to update this knowledge. Then there are black hole sources. Black hole sources, or even low magnetic field neutron star sources, when they accrete material from the companion, they go through different spectral or intensity states. Sometimes the intensity is very high, but the spectrum is soft. Sometimes the intensity is low, but flux is low, but the spectrum is very hard. And in different intensity states, these sources are expected to give different polarization signature. Plus, even in the hard state, for example, different models give predict different polarization signature. So energy dependent extrapolation measurement of these sources in their different intensity states would give us clues towards the structure of, for example, the accretion disk, which produces the thermal emission, versus the corona, which surrounds the accretion disk, which produces the hard X emission. The shape and size of the corona is debatable, and polarization should give us clues towards that. In fact, polarization not only in hard X-ray band, that combined with the low energy band would be very, very crucial. It so happens that most of these sources, the polarization degree is expected to be very low, around 2 keV, okay, where the IXP emission works, and in most of these sources, it's expected that at higher energy, the degree of polarization will go up. And its sensitivity is not as high as the NASA mission. It would still give us good opportunity to investigate quite a few sources. Not moving. Tarun, I have some more time.
Then
Sure.
we can have.
Let's yeah. So sources that you would like to investigate, let's basically measure the polarization in this energy band. Prime source for every astronomer every ex-astronomer is CRAB. The CRAB nebula, which is a synchrotron nebula, powered by a neutron star at the very core. And you would hear more about these sources later today. So the neutron star, which is a pulsar, itself would have polarization. Its polarization would vary as a function of the pulse phase that is to be measured. And in the off-pulse region also, we expect polarization to be measured, which would represent the polarization of the synchrotron nebula. Okay, that this whole thing is powered by a tiny neutron star at the center, which is throwing out charged particles, and those charged particles are going through a magnetic field producing synchrotron emission. So there is both pulsed and non-pulsed emission. Measurement of polarization and measurement of polarization is a function of phase and function of energy would be our target. And CRAB, of course, being very bright, is the prime target. There are many other accretion powered sources. Some of them are extremely bright in this energy band and often exceeding CRAB. So the subsequent plots where I show this blue curve here represents the CRAB intensity. Okay, so source like Cygnus X1, it quite often even exceeds CRAB. And otherwise also in hard state, it is quite close to CRAB in its luminosity. So in a few days observation, you would get a polarization signature from CRAB. Cygnus X1 is a black hole, which is accreting material from a massive star in a binary system with about 6 days orbital period. Cygnus X1 occasionally also produces jets. So here we do expect strong polarization, and POLIX is an instrument which is very suited for measuring polarization from Cygnus X1. In fact, with AstroSat CZTI, I understand there are measurements of polarization from Cygnus X1, which is yet to be reported. But that's a much higher energy. So IXPE, POLIX, and in future harder X-ray measurements would give us an overall view of energy dependence of polarization in this source. Next. GX301-2 is another very, very bright X-ray pulsar. Here you have a neutron star going around a massive star in an elliptical orbit. The inclination of this orbit and the angle at which we are viewing it, etc., all are very well known. Okay. The companion star has outflowing wind from it, and sometimes through the dense heat, when this neutron star goes through, it produces extremely luminous. The neutron star becomes extremely luminous. In hard X-ray band, the luminosity often exceeding 1 CRAB. Okay, this source has a periodicity of about 40 days. We need to observe it primarily, during its peak, which lasts for several days. So we will have to revisit this source many times during its peak. And this is a very, very promising source for measuring X-ray polarization in the hard X-ray band in an accretion powered pulsar. Neutron star in a low mass X-ray binary, prime target would be SCO X1, which is again the brightest X-ray source, persistent X-ray source. Even though it's primarily a soft X-ray source, even in hard X-rays, its intensity often goes way beyond CRAB, and therefore SCO X1 is a good target for us in the coming days. The polarization issues around low mass X-ray binaries and around black holes in the neutron stars in low mass X-ray binaries and black hole in the X-ray binaries are somewhat identical, somewhat similar. Whereas polarization signature that one expects from accretion powered pulsars is different because here you have a very strong magnetic field involved. There are several other transients in the sky like Vela X1, Hercules X1, Cygnus X3. These are persistent sources. And there are some sources like EXO 2030 plus 375, which are persistent, but they have very strong orbital phase dependence. So once every orbit of about 40 days, for about a week or so, these sources are extremely bright. So Polix in the early days, we would like to target these bright sources in their highest intensity state to measure polarization. Then we come to this class of transient sources. Here, we don't know which source we can target. It depends on when a transient source becomes bright. Okay, persistent sources, we can plan our observation very well in advance. Transient sources, we'll have to just wait and monitor all the all-sky monitors available, like Sweep BAT, the BAT instrument on board Sweep, the MAXI instrument on board, which is Japanese instrument on board International Space Station, the Fermi Gamma Ray Burst Monitor, which also detects pulsar. So there are several all-sky instruments in the sky which tell us the X-ray intensity of these sources all the time. We need to keep an eye on these sources, and whenever any of these sources go bright in a suitable zone for Polix, we'll have to investigate whether this source is suitable for observation at that instant, terminate the ongoing observation, and look towards the transient source for as long as possible, maybe a week to several weeks. So Polix does have a very good set of sources in hand with very interesting science prospect, and the instrument has been integrated with the satellite and tested, and in a few weeks time we are hoping that the satellite will be ready for to be shipped for launch. Thank you for your attention.
Thank you, Bishwajit. So, if there are some immediate questions, okay, you can take the questions underneath, and then a question. Yeah, please. You want to ask a question?
So, a question from a non-instrumentation person. So, how do you ensure that the polarized light that is coming, and when you are some interaction is sort of separating out in two directions, either of the directions, how you are ensuring that it does not induce its own polarization, or if there is a polarization, you are destroying it by a degree?
Scattered photon is always polarized, but with the detector, you are not measuring polarization of the scattered photon. You are measuring polarization of the incident photon by scattering. So the scattered photon is of course polarized because Thomson scattering induces polarization. But in the detector, you are not measuring, in a given detector, you are not measuring the polarization property of that particular photon. That comes from just the anisotropy of the scattering, anisotropy of the intensity of the scattered photon. So instrument induces polarization, but that is not what is being measured. What is being measured is polarization of the incident rays.
You were mentioning you're also keeping the system on all the time, except for the anomaly, South Atlantic anomaly. During that period, can we make anything out of the data?
No, South Atlantic anomaly, it will just,
not South Atlantic, rest of the period.
For rest of the period, yes, that is very useful actually. During sun pointing mode also, it will be looking at like the anti-sun direction.
No, I understand.
So that is useful for knowing the background characteristic of the instrument.
No. Have we made a plan to make systematic observation or systematic sense out of the observation? Have we made any plan?
One thing is that, okay, so when it is looking at, when it is in sun pointing mode, power generation, and so the satellite is ideally looking, the instrument is ideally looking at anti-sun direction. With any other instrument, some science would have been possible, but because Polix, the scattering efficiency is so low, even if you look at another bright source, it may not be.
I appreciate all that. My question is simple. You are keeping the system on except for South Atlantic anomaly. Yes. That's a significant portion of observation time. What can we make out of those observations?
That will help us know and model the background. Because this kind of instruments are subtracting the background.
I think you're not getting my point. My question is, have you made an attempt to really analyze what can be done? Or you're making a general statement? That's all my point.
It's more of a general statement that, given the scattering efficiency, I do not anticipate this data being used.
Is it worth looking at? Is it not worth looking at?
We looked at, not for this instrument, but for expect instrument. Expect when it is looking at anti-sun direction, let us, we can probably go slightly off anti-sun 1 degree, 2 degrees or 5 degrees. So thereby, in a year, we can actually sample the ecliptic plane, which has very strong implication for some charge exchange reactions.
Anyway, my suggestion is some effort should be made to look at what can be made out of this. It may turn out to be nothing, but at least our effort should be to do that.
For expect, we have clear prediction that there is things to learn if we can keep this.
AP, just before your question, there's one question pending from.
Question, you have total 50 stars. So you have
Can
1 to 4 week observation
close?
time. So total all stars will be observed within.
Could you hold the mic to your
No, there is a 50 stars and each star observation time is 1 to 4 weeks. So all observation may be completed probably in 2 to 3 years.
No. In this kind of observatory, you wouldn't go like that, that there are 50 stars, let's go and look at all of them. First year, we have this, let us say, about 1 dozen to 18 sources. We look at them, understand their properties, and from there, from the remaining sources, either we revisit some of these sources for something more interesting, or then from the next layer of sources, we select some more. Plus some more transient sources will come up, and if they fall in the interesting category, like even accretion powered pulsar or a black hole with jet. So it's not that all 52 sources have to be given equal importance.
No,
So what we learn in the first 1 year, we would teach ourselves like how to optimize the next level.
Probably all observation will be completed within a period of 3 years.
No, the observatory runs for 5 years, so we can go on and on. There is no consumable on the in the instrument, so ideally the instruments can the detectors can run for a very long time. It's not necessary that we have to finish within 3 years or 5 years, but ideal mode for such an instrument will be we start with the brightest sources and most interesting sources, see what we learn from them, then from the next set of bright sources we optimize, and that is where larger user base with their ideas would give good feedback.
So can we move to the question from KP Singh?
I have one question.
Have you made an estimate of the likely leak rate and life depending on what is the thickness of the mylar?
That is difficult. What we do is that leak we measure, okay, to the level possible in lab, and then the leak rate itself, what you can measure with the leak detector, that itself doesn't tell you the stability of the instrument. So we put the instrument in vacuum chamber and monitor different detectors for 4 weeks to up to 8 or 12 weeks also, and that shows that it is gain is stable enough, so that I do not see any leakage problem as of what has been seen. If we want to see beyond that, then you have to put the whole thing in a vacuum chamber.
So the estimate kind of limit on what is the maximum lifetime and so on.
So over a period of let us up to 12 weeks, we have kept some detector in vacuum. Okay, the gain has not exceeded what we initially had started with. So as of now, in the given data, there is no indication of leak.
One more question. You see the previous presenter showed that the average visibility around 70 days. So why you not observe one target?
No, that is, I think, that is a little conservative. That's probably a little
1 to 4 weeks.
That's little conservative estimate, probably. Yeah. So that is we are assuming like you can look at a source when its angle with respect to sun is 110 degrees is assumed. Probably that there is a little compromise there. You can probably observe sources which are above 90 degrees. So that duration, as the mission goes and we start operating, we might be able to expand it a little. So my rough estimate would be a source should be observable plus minus 90 degree from anti-sun direction, giving us good visibility. So it might extend up to about 100.5 a year. Initially, we are going with a conservative plan.
Dr. Koteshwar Rao, and another question there, and we'll cap it at that so that Sujay gets some time to.
Paul, when you select the source for observation, do you make sure there is no other potential source within that 3 by 3 degrees which can potentially cause a background increase in your instrument?
Yes, that is not a problem with these sources that I showed.
Sir,
that's one consideration.
What I'm asking, if it is so, the mission should consider it as a constraint because you are aware. But if a new proposal comes from somebody, they should be aware of the constraints of observation. So the mission should put, when he presented those constraints, this constraint I have not seen. So you should ensure that there is no other potential source within that 3 by 3 degrees of
two things. I mean, other than this also we are doing two. One is during the PV phase, we have plans for looking at trying to figure out if there is a source slightly away from the main source, what is its impact. So that we will do by looking at like Crab offset pointing. So we have clarity about what happens when there is another source in the field of view. Plus also make some observation there is actually a source within the
but what I'm telling, right now you put a constant of 3 by 3. If you can relax it at a later stage, that is a different issue. But that should go as a constant for the new proposals. Yeah. Don't assume only RRI is going to use the instrument. Okay. Yes. So the other proposals are also there. They should know what are all the constraints. That is one point. My second question is, when you want to observe a transient, okay, you mentioned that you are going to take from other astronomy satellites. Is there a plan of action which data from which satellite you have to take, and within what time the new proposal has to go to observe the transient at its initial stage.
No, this has not been worked out in detail with mission team. Typically, these transient sources last for several weeks.
Yeah, but what I'm telling,
2 to 6
you
weeks.
make a plan.
Sure.
That is.
Thank you so much. One last question.
I have one question. Can
Yeah.
You keep it brief, yeah.
What are the safe maximum operating temperatures, maximum as well as minimum operating temperatures for these Polix? Can you please specify?
Polix is 10 to 30 degrees is the acceptable temperature range over which Polix has been tested, and that entire range is fine. But I think thermal group is actually limiting the temperature to slightly finer range, 15 to 25.
Let's cap the questions now. Let's move to the next speaker.
No, you are answering to that question.
Oh, sorry, you are answering.
Yeah, we have acceptance limits 10 to 30, but we will ensure within 15 to 25. It is fine.
Within 15 to 25.
Thank you. Sorry. So, can we hold it till Sujay's presentation? Sujay, you have about 15 minutes to questions. So you can. Thank you. This is Dr. Sujay Mati from TIFR, Mumbai.
Morning, everyone. So I'll talk about some of the on the simulation sides of Polix, like what we have done to make response and background simulations of Polix. So just a quick background before I go into details for non-astronomy people, that like why we do need to carry out simulations. So typically, like X-ray interactions with matter happen with different types of physical processes, like photoelectric absorption, coherent or like Thomson or Compton scattering and pair production, and there is a secondary emission also from like when photons interact with the matter typically. And so these interactions are dependent on the energy of the photon and the material and which it will interact with, and these are all probabilistic interactions. So we need to do a forward modeling of the detector, which we are the X-ray detector which we are building to get the response and all. So that's why such kind of simulations are important, and the way to do is mostly using this toolkit called GEANT4, which is widely used in high energy community, especially from built by CERN to carry out their high energy physics simulations. But now it's also been used in space applications widely for most of the X-ray missions. So it's an open source Monte Carlo toolkit, and it can simulate interactions of X-ray particles and X-ray photons into material. So the advantage of this toolkit is that it's fully scalable. You can code it on your laptop and then also run it on high performing computing clusters when you want to do that. So with this, I have mostly worked on making the XPOSAT and Polix mass model, mainly for the Polix simulations. So here is the rendering of the model which has been from the GEANT4. So you can see the Polix payload here, and this is basically I have right now modeled the top deck of XPOSAT, and the satellite is assumed to be a bus right now with an aluminium. So you can see that the Polix is modeled with greater accuracy. We have a scatter inside. I have opened up this part of the detector just to show the components inside. It's the collimator, the back end, like the front end electronics on the back side of the detector also modeled, and the top deck I have modeled expect and the background and the processing electronics. So these are modeled with an average component but accurate dimensions. And these typically simulation of this from the simulation output which we get is basically the event ID, which is the interaction, like the photon which is incident onto the scatterer and to the detector. So then it has the detector ID, anode ID. You get the deposited energy in each anode, and also get the multiplicity if there are the multiple interactions within the anode cell and between the two anode cells rather, and also the vertical position which will be also detected in the real case. So this has been used to do two kinds of simulations, is one the efficiency and the response, and also the background simulation. So for the efficiency simulations, what is being done is that shine on axis photons. So it is one rendering with the photons shining on the collimator top, and then you can see some they get scattered and then get stopped in the detector volume. And so this is we tried for different types of like the different impurity in the scatterer. So the first to get the efficiency. So here is some of the results. So first we had tried with the beryllium, which gives you the maximum, the pure beryllium without any impurities. Then there was one scattering material which was available, which gave us a better result. But ultimately, the flight model scattering, which is the red this thing, this is the efficiency curve, which is also Biswajit also showed the effective area, which is basically multiplying this by the area of the scattering disk. And with this, so this is the FM scatterer with the impurities which we have been measured is this. So the red curve is the final sensitivity. And as Biswajit mentioned, that this increase around 35 kV is because of the xenon cage effect. The effective area of the xenon increases above that energy. So this is the typical cap spectra we get for the 8 to 30 kV range, and the count rate is about 3.26 counts per second in this energy range. Other than that, the same simulations were used to do, have been used to measure the polarizing response. So as Vishwajit mentioned, that each anode is going to be an independent polarimeter when the instrument rotates. So in the simulations, the thing has been reversed in a sense that you don't rotate the instrument, but you rotate the polarization vector to get the same effect. So you can measure the response of each anode by rotating the polarization vectors, like for two anodes I have shown here, and then you can co-add them to get a final profile when you can measure the modulation factor, which is the mu100, which you need, which is there for 100% polarized light, and based on that you can measure the you can find the observed modulation, and based on the mu100 you can measure what's the actual polarization of any source. So you get about the 0.4, the mu100 about the 0.4. So this is slightly older, the Materon scatterer efficiency, so the number will probably remain the same, but we don't expect this to change. The new simulation is yet to be done with the flight model scatterer. So then one other things which were done is the background and the shield efficiency, measure what is the typical background count rate. So first, like we have only tried with the cosmic X-ray background photon first. So with the isotropic flux, so that you stimulate that model inside a spherical geometry and you shine photons isotropically onto the entire model. So originally the design was to have a stainless steel and molybdenum shield on all sides of the detector and on the top of the collimator also. But that gave a significantly high background. So then we have added now the tantalum shield on the top, which has reduced the background quite drastically. I'll show the way. So the final configuration is now that there will be a layered shield on all sides, with the innermost will be the stainless steel, the molybdenum on the 0.2 mm, and on top and the final will be the tantalum shield, and this will go on the detector bag, the side, the top, on the top cover, and also on the collimator side on the top. So this is the simulation. This is the result. So this one is the count rate with the just SS and demo on the left is the spectra and the count rate. You can see the counts for about 72 counts per second in the 8 to 30 kV, which is quite a bit high. But after you add the tantalum, you see the count rate reduce about almost half the original value. And you do see some peaks here because of the tantalum fluorescence and then doing escape interactions in the xenon volume. But with the applying the resolution, it is getting like smearing out. So this will be the more or less final like counted, but we still need to add other background components. So that is basically the things which we need to do now with the final FM scatterer, or we need to make the spectroscopic and polarimetric response that we'll be working on. Then also now add all the other background components, like the CXP is already tested, but around with that we can have Earth albedo. Then there is a cosmic ray and maybe SA background effects, what have that also can be included. So one thing which we is that if we can if the satellite bus is made available, like the components is made available, that also can be included easily into the simulation, because that will improve the accuracy of the simulations, because the materials coming, the photons coming from below the polix, and will be able to then measure the scattering better and whatever the impact it has on the background counts. So then once we have a better estimate on including all these components, have a better estimate of the background, we can then determine the MDP for each source and what the exposure times which are needed. And then there's some possibility of maybe doing some Jarvis science. Varun has a talk on that. He will probably talk about that also. So that's it on my side. It's a aluminum bus. So background, yes. So background, you put the model inside, and there is a imaginary sphere, and then you shine photons from everywhere. Isotropic.
And what kind of materials are sensitive to what sensitivity is there? You said in the spacecraft cube, for example.
Yeah.
You are treating it as equivalent to some aluminum.
Yeah, right now it's just a aluminum, I mean just a bus which is aluminum dimensions like some payload mass equivalent, but there is no information available, so I've taken that right now. Yeah.
Can you speak up so that?
And into sensitivity of polarization, what can be detected, and what is the background which is going to limit the performance? What are our current numbers?
So the background is this. I mean, this is the background count rate. So
this is what you are getting.
Yeah.
I'm asking from observation point of view, what would we consider as the limit to that?
I mean, this is the. I think this is the observed background. I mean, we'll have, if you add more components, your count rate will go, and then that will determine your R background for the MDP.
Correct, I understand. Yeah. So based on that, what can we say is the limit of our observation for this system?
So the
both
MDP
in terms of polarization.
That comes from the minimum detectable polarization. So that I have not computed because we are waiting. Like I want to do the final full simulations. With that, we get the background count rate. We can then use the minimum detectable polarization, which will determine the sensitivity of any source.
If these are the numbers, what would it be?
If these are the numbers, so that I have not computed.
I had that in my presentation. Okay. So for a 200 milliclap source with 1 million second exposure, you get about 7 to 8%.
Okay.
The same number.
Okay, yeah, it's the same number. Okay.
Okay.
That mu100 that you mentioned, 0.4. So what is the energy dependence over this energy band?
So we had some computation. So this is for old scatterers. I'm not showing any plots because there were some there, but I don't want to, like with the new FM model, I'm going to compute this. So these are slightly old numbers with the different scatter, which had a different. That's why I'm not showing something right now.
The average over.
This is average. This is energy, 5 to 50 kV. So there will be there is a slight dependence, but I don't think it was too high. But again, since the impurity is now different for FM, this need to.
Dr. Rao?
You have introduced the 0.2 mm tantalum to reduce the background.
Yeah.
Will it have effect on the response?
Yes, so that's a slight response. I mean, the background, for example, you have a slight, you will detect these escapes in the background. Photons. I mean, the photons.
Why I'm asking is, if it reduces the response, finally your signal to background ratio will remain same, or it will improve?
The on-axis response.
So finally, that is what has to improve.
Yeah.
So have you made an assessment of how much response will be lesser and how much background will be lesser, and a ratio? What is the improvement?
Yeah, so that has not been done. So on-axis response won't be affected with the tantalum. So now
I think one exercise you can do, because finally that is what is important.
Yeah. So the shield and all was decided last 2 months only. So we need to carry out all the simulations, and so it will be done in 2 months.
What we find is there is a lot of redundancy because of the number of wires. 1 or 2 wires breaks, till the mission can continue. Similarly, out of the 4 segments, the whole one system is failed. Still, you can reproduce your polarization, or how bad it is. How many of them you can afford to fail?
Biswajit, because I think we can probably get the effect from the simulations. You can, if there's something fails, we can probably again discard the data in simulations and get the models.
Inside a detector, if the wire breaks, this is most likely that detector has to be discarded because there will be high voltage will short, it will be shorted to the ground. But then the remaining 3 detectors, it will be 3/4 of the current Polix, which will corresponding sensitivity change will be there, but it will still work as a Polix.
Yeah, that's what I want to know. What type of degradation in your phase measurements can happen?
And no, that is not compromised because measured by rotating every element.
Okay.
So
even if one wire goes, the other one will still produce.
The detector is fine. But if one wire breaks inside the detector, that whole detector is most likely to be high voltage will be shorted.
Thank you. One last question.
I have a question regarding orbit sensitivity that is in two parts. One is what is the currently one orbit is selected and it was told anything above 500 or 600 kilometers is good enough for observing all the 50 sources. But then to extend the question, what Kosheshwar Rao sir had asked some time back, why did you not consider observing these 50 sources from two different orbits in the same mission and then asking for satellite to have the capability to change to a different orbit, especially in terms of some of the sources which if you have to observe, maybe to avoid that background possible sources, if you need to study that particular source in a better manner compared to earlier whoever have studied from a particular height. Have you done any studies?
Change in the background with the orbit, you mean?
Yeah.
I didn't get the.
From 600 kilometer orbit, okay, all the 50 sources when you see, it has a fixed background sources if at all any is there for one of those sources. And then now if you change it to higher or slightly lower orbit, maybe you can avoid that background which will be affecting the proper polarimetry measurements. So that way, whether if given a chance that satellite can provide, could you consider having the satellite at two different orbits at least or more orbits?
Or background.
Studying the sources.
Observation duration of sources, can that be increased by changing the orbit of the satellite itself? The XPOSat, I don't think any orbit maneuver was considered. However, for this kind of satellite, going up, like 650 onwards, going up doesn't help because your magnetosphere shrinks there and your actual SA free region will be shorter. Going down helps. Instead of 650, if you go to 550 or 500, but you don't want to go to 2 down because that will probably compromise the lifetime of the satellite. So this 550 to 650 is optimal zone for this kind of instrument.
In the beginning, we have data and then we want to add value to it by studying the same sources in a better manner. Whether we could have considered
mission operation
or even choosing what our current orbit could be different from what orbit earlier observations were made for these sources over a period of time. What my question?
Can I have a last question from there?
Yeah, I have one quick question. You showed all the results. Do you also have a slide which talks about the input of your spectrum? Is it a combination of models which are available for charged particle and CXB?
Yeah, so
and
for
one last thing. Did you also consider the 2 pi or the 4 pi, the entire hemispherical or in a geometry of source?
Yeah, so I didn't go to too much detail. Just so like for this simulations, on-axis simulations, it is just monoenergetic simulations here to get that. The modulation, this was exact Crab power law, minus 2.1 with the normalized to the in this energy range. And then for background, it is the CXB spectrum from Moretti et al. And that's the standard one mostly used. And it's shine from 4 pi. You shine from entire here around your instrument, around your simulation, around your instrument. Then you normalize with respect to your, because you also restrict your emission angles and all. And one thing which is done is that effect of Earth is included. So you exclude the part. So assuming 600 kilometer orbit, you know how much part Earth will be blocking because you have isotropic flux, but there is a part behind the satellite that will be obstructed by Earth. So you don't expect 6B from there. So that is also excluded. And then the only photons coming from the sky gives you this shape. All this is included in that.
Okay, we can take any further discussions offline. So let me thank Sujay and Vishrit for covering the POLIX payload. Also, I've been noting the fact that there are a lot of very interesting comments and suggestions for further work. So I would request Vishrit to arrange a little meeting in RRI so that we can make sure whatever we learned during this session from the valuable comments that came in, we can make a plan for what should be done. Okay, thank you so much. We'll move on to the next payload, which is ESPECT, and There are 3 talks here, each of 15 minutes. So 12 plus 3. I request the speakers to stick to the time so that, we don't have further slippage to lunchtime. Thank you so much. So the first speaker is Vivek Kumar Agarwal. He's the science PI of Expect from Space Application Group, URSC.
I will speak about this major science goals of Expect and what is the capability to get those science goals. So this is the overview of my talk. I will give some introduction, the instrument specification and background, how we determine the background and scientific objective of the satellite. So X-ray this goal of this major capability of this instrument and this mission is to get the long-term observation of very selected few bright sources from weeks to months time scales. That is major capability of this missions. So we can study this long-term evolution of spectroscopy and timing and for many selected sources. Then this Expect can handle large count rate. Large count means we can observe even SCOEX one also. So no such like XMM, BEPOSEX and so many other mission which was basically spectroscopic cannot observe such a very bright sources due to pile up. And it has very fast timing capability, 1 millisecond, and good moderate a good spectroscopic resolution of that thing. And with also we have additional advantage of POLIX in the same platform. So we can study the same times, we can study the spectroscopy, long-term spectroscopy, and same time we can do the medium energy X-ray polarimeter. So we can from this we can study the emission mechanism, other things. From POLIX we can get polarization information of these sources. So what are the instrument specification of this? We will be using the SWAP chart device, which is very similar to Silicon CCDs, and it has a very fast timing capability with low pile up. And energy ranges of the instrument is 0.8 to 12 kV range, and effective area is greater than 30 centimeter square at 6 kV. Energy resolution is better than 200 EV at 6 kV, and time resolution is almost 1 millisecond. We have chosen 2 field of view of the detector, 2 degree by 2 degree collimator and 3 degree by 3 degree collimator. I will give the advantage of this. Why chosen 2 types of field of view? What is advantage of that? I will just discuss those things in the next minute. This is the effective area of the instruments, how it varies energies. For 3 degree combined effective area of 3 degree by 3 degree and 2 degree by 2 degree collimator. Geometric area of this instrument is 64 centimeters. So we have total 16 detectors. Each detector is 4 centimeters square. The total comprising the 64 centimeters square. So how we'll get the background? So from PV phase we will do some blank sky observations, and there are 15 detectors which will observe the source, blank sky, and 1 detector is blocked. So it will measure only galactic cosmic rays. Only cosmic rays will be measured. X-ray will be stopped by this detector. So what we'll do is we'll subtract this CXB GCR from this 1 block detector, and we can get measure of the cosmic X-ray background from this model. We can get it. Either we can do if you have no source confusion, if you have 2 degree by 2 degree field of view and 3 degree by 3 degree field of view. So from that, if there is no source confusion, this has only source plus 1 source plus background. This has 1 source plus background. If you subtract these 2, we'll get the background GCR plus GCR also will be subtracted because GCR will be very similar to for these 2 field of view, and there's only will get the CXB around the source. So we can get very close to the source. What is the cosmic X-ray background? We can compute. So these are the class of X-ray sources which will be observed. These are the first X-ray pulse, X-ray pulsars, black hole binaries, low magnetic field neutron star in low mass X-ray binaries, and active galactic nuclei and magnetars. So these are the list of the sources which you will observe in first years. It will cover HMSG pulsar, 6 HMSG pulsar will cover, 5 neutron low mass extrabands will cover. Then there is a low mass extraband pulsars are there, black hole binaries are there, AGNs are there, and supernova remnant also one is there. So what is the major science objective of this instrument? So the main objective is origin in, I have highlighted, I have done few points, the other points also there. Origin and variability of soft X in X-ray pulsars. So X-ray pulsars, so instead of continuum is also so soft X's in low energy band, and origin of the soft X's is very debated. So we can study this, why this soft X's is seen, and spin period evolution and accretion torque history in the X-ray pulsars. How this expert is going to observe for a few weeks same source, how spin period is evolved, how with accretion rate, how spin period changes, how pulse profile changes. Those study also we can do with the for the X-ray pulsars. And RNA profile modeling. The RNA profiles are skewed due to gravitational effect. So from that we can measure the spin and mass of the black hole. Then also we can study the spectral transition and relation studies in black hole neutron binaries at all sources. Black hole, these sources show spectral transition on time scale of, if you start bursting, it will evolve on one time scale, and in different times we can calculate the spectrum, and we can study how this spectrum, especially in soft band, how it evolves, that we can study. And X-ray spectral evolution is G sources along jet track. G sources are very bright low mass X-ray binaries, and these sources traces very specific diagram in color code diagram. How this spectrum evolves in jet track, how this jet track is produced, that is also one question. And we can also study the temporal variability in AGNs. So this is soft X's. This is soft X's seen in the Hercules X1. We have simulated it from the observation from SXP has observed the soft X's from the Hercules X1. Using that data is simulated and found the expect also is sensitive to the soft X's, and we can with this time we can compute. And then these are the sources which has been from which soft X has been seen, and we can, if we seen how it evolves and what are the models for that we can study. Then there is a spectral transition et al. Et al means there is a low mass X-ray binaries which traces particular diagram in the, this is called et al. This is a low mass. You can, then there is a called neutron. What is the right models, phase and models, phase, and then computerized, and there is disk from that black body emission is coming from the like sources mechanism with RNA profile is the 200 kilosecond simulation, very tiny this thing, and that model like there is other model mass of the spin of and we go quasi-periodic bright low mass X-ray band, especially in soft X-ray band. Till now, this is get a 3 to 4 kV, like with lax PC astrosat. Quasi-periodic oscillations in the soft. This is simulated. Oscillation has been in this source. This is called color diagram. The plotted is band, this is normal band, this is flaring band. static calculations. So till now, till 30 soft Excel related to Corona, that we soft Excel how about that. And also sources so type many version of type first Excel burst, and this burst can be characterized how this burst from accretion due to hydrogen fusion, helium fusion. This are triggered. That how the accretion is modified from satellite.
The importance of background is already known for this community, but let me set a tone for the rest of my talk and bring out the importance, especially from the perspective of an X-ray spectroscopy instrument like Expect. And next I would like to list all the sources of background that can play a role in the instrument, and then and find out the relevant sources, and then I'll come to the simulation aspects. So we'll be using discussing on how the simulation is done. It's very similar to what Sujay has done for Popolix payload based on GANT4 simulations. So I'll discuss how the simulations are done and also the results. And then once we have some results, we would how we have tried to validate them, what terms, because we don't have the onboard data yet. So it's a confidence gaining measure. As a confidence gaining measure, what do we do for validation and with future work? So yeah, I'll start with instrument design. Just when we think of instrument design, like for an X-ray spectrometer for astronomy, all these questions pop up. What are the integration times? It's quite natural that these questions pop up. Effective area, what is the preferred configuration, or what's the collimator should be, and what detectors should be used. Integration times needed to observe a source and all. So there are of course all coupled questions and related to the design, and there's one common denominator to all of these. It's the background. So background starts from, the consideration of it is very much essential from the to the entire life cycle of a payload realization and even to the end of it. Something like from cradle to grave. So background starts it to play its role from its design, and also eventually it ends up being a very crucial component for the science in the science data analysis for the eventual users. So that is the motivation for us to estimate the background for this payload and see what we can do, and what are the essentially it folds into sensitivity aspects and what's the eventual performance of the payload. Then we move to the sources of background that can be there in the orbit. It's almost an exhaustive list, but all of them are relevant or not. I'll just come to it. So on the left side, I've segregated them into in situ and remote sensing remote sources based on. So all the remote sources are the ones if a detector or experienced when as a spacecraft moves through them and we detect them in situ. Remote sources are the ones that are sourced from elsewhere. So what are and I've further subdivided them into two, dynamic and static. So we can't do much about the dynamic sources or rather sources of background here, because it's best to do is to avoid them. So we choose an orbit or the observation time such that they are avoided. So we are not into because they are dynamic in nature, the background is not so useful at that time. So we concentrate on the static aspects, and solar wind being at LEO, solar wind is not going to affect us. So the main components will be the galactic cosmic rays that are coming from all sides at the spacecraft, and then the cosmic diffuse X-ray background are the main features. Apart from that, there is Earth's albedo that's there, but that's again another feature that if you are looking at into the deep space away from the sun direction, away from the Earth direction, the effect of it is not going to be much. So the main components that are there and static are to be considered are GCRs and CXPs. And then with that, so what are the inputs onto the instrument? So this is a GCR input taken from Slava et al. It's a very famous galactic cosmic ray model that are the model is given by Badwar O'Neill, and they have been updated even as recently as 2020. So on the left side, it gives you the spectral distribution of the galactic cosmic ray protons. So this is what we use as spectral input, and also we know that galactic cosmic rays are correlated with solar activity. So we have to find out at what position or what time of what phase of the solar activity we are at, and then pick the integral flux of it from this plot. So it's based on both observations and simulation and the estimated model. That's the main input for the galactic cosmic rays. And for the cosmic X-rays, we use the standard observations from RXT and ASCA, which is a single power law model. Then the other input, which is very much pertinent, is the very much geometric design of the payload. Here I'm showing you the explored view of the expect detectors. And as mentioned by Vivek sir, one of the detectors out of the 16 is blocked by this a tantalum sheet to obtain the GCRs for galactic cosmic ray spectrum. And the rest of them actually have the very similar geometric distribution, with the collimators having 2x2, half of them having 2x2 cross section, and half of them having 3x3 cross section. So what we do essentially when we say we are simulating is to do the Monte Carlo simulations of these when we create a virtual model of the instrument, and then incident the inputs that we have just mentioned, and then see the response. For us, the instrument is a spectrometer, so we see the spectral response, not just the total count rate. So this slide essentially summarizes as to what we did in terms of methodology. So all the relevant inputs in terms of the spectra are taken. Basically, currently here we are using the GCRs and the CXB, and we try to construct with as much detail as possible the detectors and its near proximal elements. So that's why I've shown this. So this is the SCD, and then all the proximal elements are the light filters, light filter frames, and all the posts that are there. We have built virtually in that in GANT. And then we use a mass model for the peripherals, and also we have simulated for an approximate model of a spacecraft, and then give all of the inputs to generate the net response to do all of the summation of all these inputs independently, and then try to validate. How we are validating, we'll come to that, but the results of this would look like this, a GANT simulation. So on the left hand side is a manually not from an imported geometry site, so manually generated geometry of the expect one of the quads of the expect payload. And on the right side, you can see is there's a approximation of a spacecraft, and if you see from the previous pictures, you see that this is one side of the expect payload. Totally, this is imported geometry, and the influx is from GCR influx. And what are the results that we have? So on the left hand side, I'm showing you the output of GCRs, and there are two plots here, as in two curves here, one with tantalum and one without tantalum. So there's a change in the spectrum only at the points where the tantalum lines are shown. Otherwise, the continuum remains the same. So we can, in principle, use the block detector or the one SCD that Vivek sir already mentioned, that the GCR spectrum can be obtained directly from this. And on the right hand side is the cosmic X-ray background. So the left, the blue curve is the input that we have taken. It's a single power law. And on the right side is the observed flux that we can expect in the observed units. And once they are there, we see we fold in the entire spacecraft, the entire spacecraft level simulations, and include all the finer components like bolts, screw heads, everything. Then we see that instrument generated fluorescent signs also come up. So this is the GCR induced spectrum. So GCR induced background spectrum. So for us as a validation measure, there's another instrument called on the called HXMT. It's low energy telescope. So we use that observations of that as a blank sky observations of that instrument, which is shown here, brought down to the same units, and then we see that it's and we also have scaled our observations from similar units, and to find that spectral profile is a close match. But there is still a discrepancy here, which of course will be filled by the cosmic X-ray background. So when we feed in our second component of cosmic X-rays, we see that the net spectrum is shown as shown in the purple trace. That's the summation. So this sort of is the initial validation. Although there's slight residues here at this point, which I can attribute it to the response that we have used. So the absolute numbers that we have here are yeah, we're confident of them. That's what we can say. And of course, they will be validated with the onboard response, onboard observations during the PV phase. So what are the key takeaways? So we see that the two components to this vision, around 7 kV onwards, till the 7 kV, the cosmic X-rays are the dominant feature, and from then on, you'll see that it's the cosmic galactic cosmic rays that are dominating the background, and that's one of the observations. And we see that from HXMT observations also, while trying to scale them, we see that the spectral profile of GCRs is invariant in shape, so that it's not locational spacecraft dependent, but only it scales with the scaling factor. There is a scaling factor based on the cutoff rigidity or the positional spacecraft verities. So as the spacecraft goes from latitude to latitude, the extent to which the Earth's magnetosphere can shield the spacecraft from the cosmic rays will be different. But the essential response of the spectral response of these cosmic rays will be the same. That is what we are trying to say. And then the third important takeaway is that yes, putting a tantalum on one of the SCDs, we can directly obtain the GCR spectrum, and that is as shown in this plot. So in the future work, as you can see, that there's slight residue with the HXMT observations. So we want to use a fine-tuned spectral redistribution function that's catered, that's tuned for particles, charged particles, not just X-rays. Also, we will be using an updated single event response X-ray for X-rays in the background, because there will be fluorescent X-rays as I've shown in the background results, and then finally validate them with our onboard observations eventually when the spacecraft is up. That's all I have. Thank you.
Any questions? Yeah, KP.
To all these instrument teams, I mean, there's a plan to do a background observation, blank sky.
Yes.
That not seen.
Yes.
Okay. And for how long? Because that will set rest all the certain other questions about what is the contribution of the instrument itself to polarization, for example.
Just for 1 week.
1 week will be sufficient? No.
Okay, I don't see any other hand up, so shall we? Oh, okay, sorry.
Yeah. A quick question. The locally in
Carlo, so all the
no, I'm saying cosmic ray photon is hitting to the satellite mass,
correct,
and it may induce local.
Correct. All the secondary protons, secondary photons, all of them are generated, and they will automatically get it. It's a Monte Carlo simulation, so that's taken care. It's intrinsically taken.
Okay. Thank you. So let's thank the speaker, and the next speaker is Professor Ranjiv Mishra. He'll be telling us about a unique science with long duration aspect measurements, observations.
We're going to have a lot of talks in the afternoon about science with expect. So I'm going to limit it to some very generic comments out here to start off with. And I think there are two main advantages of expect, and we should emphasize on that. The first important one is that as POLIX is observing a source, we will be able to use expect to identify the temporal and spectral state of the source, and we expect polarization to vary as depending how the source changes. So expect's most advantage is that we can give you time selected ideas of when the system is in one particular state. So in advanced studies, we can study how the polarization goes, and that's going to be one of the main part. A secondary part of it is that because of the way this source system is managed, we're going to have long stays, about more than days and weeks, at a single source. And so hence, previously this was never done that we stay at a source, single source for such a long time. So we get an advantage out here that we'll get to know the evolutionary history of the source. All these sources which we talk about in generic, all X-ray sources, typically change in timescales. They have different spectral and temporal properties, and expect will allow us to study the evolutionary aspect of how do these spectral states studies. In fact, that's all I'm going to talk about the science part of the whole thing, because I think these two are the main broad ideas, and we'll have a lot of discussion in the afternoon about how we will take these advantages forward. But I would like to more emphasize on what is the possibility and how capable would expect would be to do this. An important aspect of this is that suppose you want to understand the timing properties of a particular source, we know from experience that the timing property of source changes. In fact, can changes over. For example, in a few thousand seconds, the timing property, the fast timing properties of these sources can change. So it is actually typically expects capability of measuring timing property in a few kiloseconds, which will be important. And not that we are integrating over days and months. So its ability to do something in few kiloseconds is going to be one of the main aspect of it. So we have to understand that what kind of sources can expect study in this. So here are some simulations which have been done, and let's take the best possible case scenario. You've got the brightest X-ray source in the sky, OX1, and it has got and you see something which is called a quasi-periodic oscillations. That means these are temporal variations which happen, and we want to characterize this kind of variability. Suppose you have something at 8 Hz at 5%, you'll clearly get from expect in less than 2 kiloseconds this QPO. So this is clearly a good size that if it happens, we can, and this is typical value of 5% is not very large, and such kind of thing we should be able to get. But however, if the QPO goes down to 2%, we still will be able to get something from SCOX1, but not very specifically. And if at 1%, it's gone. So the limits we have is that whenever the, some kind of property is very high, we will be able to get this in few kiloseconds. But what is important is not just detection. I always emphasize that detection is not important. We have to find what is the properties of this temporal system, like what is the RMS and how does the time lag change with energy. And if you do the simulations for SCOX1, they're perfect. I mean, at 5%, which is typical, you can get the RMS varying with a function of energy in at least 4 or 5 bands, and that can tell you how the RMS is varying or energy at 4 bands, which is very good. And also, even if it is 1 millisecond time resolution, you can get time lags between the different high energies accurate to milliseconds quite well. So these simulations assume no time lag, so that therefore the error bars are the ones which are important. So you would see that around 2 milliseconds accuracies you can get for SCOX1 kind of a source. If the percentage is 2, I mean the QPO has a low frequency, I mean lower RMS, you can go down to around 5-6 milliseconds. But typically this is still a good numbers. We can do good characterization of a source as it goes to spectacle. However, if you take another kind of source like Cygnus X2, which I take as another example, which is much more fainter than SCOX1, at 8 Hz RMS QPO at 5% is not visible. Can't see this at even for 10 kiloseconds. So that is I would say that we have a bracketing region of this number of sources where we can do rapid temporal variability, which is from something like SCOX1, which has the flux of 4 × 10⁻⁷ to something like 1, so around a factor of 40, 50 levels where we can do. So it'll, in my estimation, we'll be able to cover something like 10, 30, 40 sources very well, and that's the kind of a margin we are looking at how to do this. This is the timing analysis. The spectral analysis is a little bit more complex. So let me explain this a bit more. So what we do for spectral analysis, and we want to, is that for each and every kind of source, we have to go and simulate and look at the spectrum to find out what it does. and how is it. And it is not sufficient in this kind of a science we're doing with expect and all to detect the source. We already know the source is there. We in fact already know what kind of broad X-ray spectral property the source will have. We want to do much finer than that, and we want to know exactly how the source changes in spectrum in few kiloseconds. So that is a little bit more difficult. That requires simulation for each kind of sources. But here I would like to show you some broad simulations. This is the kind of thing which I like to show of a spectrum. This is a 50 milliCrab source, and this one, this green line is the 50 milliCrab source. This is a count per second per energy. Now this is what we will get in count per second. So we have to compare with two things. One is what is the actual Poisson noise at for this exposure at 10 kiloseconds, and that is this blue line. And so it shows that even if I bin up till about 10-15 kV, and this kind of a spectrum is what I'll get very nicely. I will be able to characterize the spectrum excellently. This is all very good, but the important thing is this curve out here, which I estimate to be 3% of the background spectrum. Now it's important to realize that it's not a background level which is important. It is the uncertainty in how much you know the background that is important. So if you know the background uncertainty to 3%, then such kind of analysis can be perfectly done. If the background is uncertain by a larger factor, it will start affecting the. So this comes back to the previous talk of this, that the background estimation and uncertainty in the background is something which we need to. In fact, we can go down to 5 milliCrab also, but now you have to increase the time exposure time to 50 kiloseconds, which is getting low. But again, you can see that the Poisson noise is not dominating. We can get. It is not that you just match it up here. You should have good signal to match the characteristic of spectrum, but this is the kind of thing you can do. And again, if the background is uncertainty is not very heavy, it can be done there. So overall, I think it is broadly good news. The broad good news I would say is the expect will be able to characterize long-term spectral temporal evolution of bright sources, which we did would be the target of polarization space, and we will be able to do it very well. However, there are two important points we need to do. We need to get good spectral response, which we hope because this is a good CCD. Background estimates close to a few percentage, and then we will be in good business to do this. It has a. Let me talk a little bit now for a few minutes about the general use of expect in to the broad scientific community. There is of course this. We will be observing some large number of sources, and we study the evolution of these sources and all. There's another side effect of expect is that whenever we, let's say we look at SCO-X1 for 40 days or for a month or something like that for a long time, some source, then any other community out there, this has become the repository of a data where we can say that suppose somebody else is studying the same source and they've got observations from other satellites, they want, and because it's a long exposure, there's a good chance that XLect data will be available at a time. So then they can use that and compare it with systems. Also, when you're looking at the spectral and temporal evolution of the source, this is model dependent. People will try the different models on how the spectral dependence goes. So we do have a scope and capability of a fairly large community to use this kind of data. So we need to also start thinking very seriously about these two conditions about data policy and availability of this data from general ExpoSat. And also, if we are going in, because these things will still be complicated, we will need, like we did for AstroSat, I think, some kind of a support cell in a modified way to do this. So I will stop here. Thank you.
Okay.
A quick question. See, we know that satellite is rotating. That is primarily required for getting the polarization information. But would it not impact your spectral and temporal information? Would it statically, when you observe a source, would it be better? And with resolution, with rotation, any impact is there?
There should not be a significant impact on the spectral.
Because we are using a detector, as far as I understand, a detector is there, and static, when you observe a particular spectrum, would it not be better?
The point is that the rotation is about 0.2 per minute. So about the rotation, each rotation about 5 or 7. Each of the exposure time we are talking about is much longer. You can go into a very long exposure and they are not resonant. So we will get some kind of, the timing properties of this kind of a system can get affected when you're looking at milliseconds. Sorry, let me get back to my power spectrum. So if you are going to, this is frequency in timing. So this kind of, there'll be effect around at 0.01 or 1 millisecond for this rotation, and that can affect your timing part, millihertz, right? Because they'll be beating with, in fact, even for polarization, you have to worry about beating of things to give artificial signatures. So at low frequencies, when if you are looking at a source which are varying at the same period as we are moving on, that can cause a lot of
Thank you. Varun?
The last slide where you had about data policy, one more thing which would be very useful is that this is a rare scenario for an Astro mission where we actually know the target order well in advance. And knowing that publicly would also help significantly in planning any coordinated observations from a broader community perspective.
Absolutely. Thank you. That is a good point.
That's a very good point. Any further comments, questions? Yeah?
Regarding the thing that you said about the rotation, doesn't the source remain in the FOV even when the satellite rotates?
Oh,
so
it's ideally,
so it doesn't do anything.
Ideally, if everything was fixed and your detector was completely symmetric, and you characterized it, it wouldn't make a difference.
No, no, I'm saying that the source remains inside the FOV of expect.
So
there will be no effect on timing aspect that she was asking. I mean, I'm just commenting on that. I have no question.
No, it depends on whether there is some vigneting effect. Like,
Right.
for example, I mean, if it is within 0.1, 0.2 degrees, it should not make too much of a difference. But what do you think, Vivek? See, if there is a pointing discrepancy of slightly higher, then you can have. But as I'm also not sure whether the Pollux direction and expect direction would be identical.
Yeah.
So if there is about some offset between them, this source will keep rotating on within the field of view.
Yeah, but with a small angle about the axis.
Yeah, about it. So that can cause a slight modulation in time. So and timing can get affected. Can be modeled. Yes.
Yeah. Girish?
It will not.
That level, nothing.
That affect.
Ranjiv.
Would be at 300 seconds kind of.
Yeah.
Girish at a point.
So even if there is a vigneting and some effect, since you know the rotational period, you can model and remove it, right?
Yes, but you should know that. I mean, even I think even for polarization measurements, for sources which could have millihertz QPOs, like I was discussing, it could be something we have to take into account. Because there could be beating of the real signal from the source and its rotation, and we should be little careful on how this can.
So I like to answer your question. This question was asked actually in one of the review committee. I think Dr. Koteshwar Rao sir, he asked, and there was a great deal of discussion was there with science PI on this aspect. And based on the, I mean, certain requirement, you know, the alignment of the pole axis plus expect axis, this was the understanding that there is no impact on the spectrum. Yeah.
The spectrum there is no
Yeah,
impact.
it was a.
But timing there will be is a modulation will be.
Timing.
Modulation will be.
But like I said, the expect is not going to look at that kind of timing.
Okay, Santosh is.
No, just one small question. For Polix, if I understand, there is a specifically designed collimator with a flat top response. Expect, is that the case or not? Because if it is not the case, then even a small offset might induce some
timing, yeah, modulation.
Some timing, yeah.
Okay. Thank you. Then that closes the part on the payloads, Polix and Spec. So we have now a presentation by Sachin Naran, Project Manager, Exposat, on the Exposat proposal processing system.
So good afternoon, everyone. My name is Sachin Narang. I am project manager for ExpoSat, working in ISSDC. So today I will be presenting the ExpoSat proposal processing system. So ExpoSat is a community science community driven mission. So this means that the science community need to submit proposals to make ExpoSat work for them. So for submitting the proposals, there will be various opportunities which will be opened for the science community for submitting those proposals. Those opportunities, which we term as cycles, will be defined through a certain timelines. So one timeline for proposal submission, a timeline for proposal review and evaluation, and the observation window during which those proposals will be operated or carried out. So I am suggesting the kind of type of proposals which will be allowed in through ExpoSat. So here I would like to mainly focus on the type of proposals and who can submit those proposals. So the type of proposals here, like in the initial phase, you have a performance verification. Here only the POC team will be allowed to submit the proposals, followed by the calibration and the GT phase, where the POC team will be submitting proposals. The timelines will be decided based on the guidelines by the Science Program Office. Similarly, after the initial verification and all those phases are over, then the proposals will be opened for submission by the science community. The science community will be able to submit proposals under AO as well as TO. Here, the TO proposals will be not driven by any cycle. They will be always opened for submission. So there will not be any. So for any urgent requirement or any immediate requirement for observing any target, the proposals can be submitted under TO category. So being a proposal-driven mission, I would just like to point out the proposal inputs which the user will be allowed to enter. So first is the target selection, the target name and the target coordinates, the right ascension and declination of the target in the J1000 frame of reference. Then the required observation time. So how much duration you need to observe the target, be it in hours, days and weeks, mostly because it's a long observation proposal. So we are expecting that the proposals will be submitted in terms of 1 week or 2 weeks. But still we have given an option of giving it in hours and days. Then whether the proposal is a fixed time proposal, like it's a time constraint proposal, the proposers want the proposal to be submitted during a specific time window. In that situation, they have to provide a justification for that in the system. Similarly, if it's a flexible proposal, so the proposal can be observed during any of the in that timeline specified in the observation window for the cycle. Coming to the instrument configuration, so there is only default mode of configuration which is applicable for ExpoSat. Still, we are giving an option of giving a primary instrument selection option for the users. So here it basically means any differences in polix or aspect mounting. So if suppose polix basically will be given as primary, if suppose there is any difference in the alignment between polix and aspect, so the aspect will be taken if aspect is chosen as a primary. But more or less this option may not, if there is no alignment mismatch, then this option basically stands void. Then coming to the supporting documents as attachments. So the users will be required to submit the target visibility analysis during the observation window, and the scientific justification for that. Then the users need to enter the title, abstract and the supporting information. The users will also have the option to add an ordered list of co-authors in the proposal. And if the proposal is going to be a coordinated observation with other observatories, so that information also the users can enter in the system. That will be used as an information purpose. The users also have the option. To link the currently created proposal with the earlier previously submitted proposal. So I'm just making a little bit deviation from the proposal and coming to the services offered to the users by ISSDC in this context. So first is the ExpoSat proposal processing system, which will enable the proposal submission, review and observation planning among other functionalities, which is presented in the subsequent slides. Then comes the Expo Viewer user interface which is the target visibility analysis user interface, which will be integrated with the flight dynamics module. It will provide the SA-free eclipse duration suitable for the target pointing during the given start and end time. So, and it will also have the option to download a visibility analysis output as PDF Excel, which they can upload in the proposal processing system. And third is the Pradhan application, which is ISSDC's web-based dissemination software to host the science data for access by the proposers during the lock-in period and public release of data after the lock-in period. Now I will focus on the proposal processing overview. So the proposer will first access the Expo Viewer user interface to analyze the target visibility during a given duration, and based on that they will be able to submit the proposals to the ExpoSat proposal processing system. The evaluated and accepted proposals will then be scheduled and uplinked to the spacecraft for the desired period operation. The period operation will be carried out and the data recording will be done. Data will be played back and received at the ground station and will be eventually received at ISSDC. At ISSDC, the preliminary level of processing will be carried out and then the data will be disseminated to the POCs. The POCs will carry out the higher level processing at the POC centers. So the POLIX data will be processed at RRI and the aspect data will be processed at the SAG. Once the processing is completed, the POCs will post back the dissemination ready products to ISSDC. Those data sets will be then hosted at Pradhan and the users will be able to download data during lock-in period, and after the data is released, even the community users will be able to download the data for carrying out science. So this is a context diagram for XPPS. So XPPS is going to be a centralized solution for cycle management, proposal submission, review and observation planning. It shall enable role-based functions. So we can see so many roles which will be allowed to access XPPS, and based on the kind of role assigned to the user will be able to submit or carry out different functions. So here I would like to focus on the community proposer and the PIs and POCs. The community proposer will be able to submit the science proposals and the PIs, POCs will be able to submit the science proposals as well as the calibration proposals. It shall enable three main function classes: the proposal submission and modification, proposal review by the committee, and the observation planning. It shall also enable the calibration proposal processing. So coming to the proposal functions. So first and foremost, it will allow for creating a proposal. It will allow to save a draft proposal to modify it later. Copy an already submitted proposal to create a new proposal. It's a kind of a convenience function which we are offering, and they can modify differentially to create a new proposal out of that. Then you have the option of searching your proposals and viewing your proposals. You can search proposals by a proposal ID or proposal state, whether it's in submitted state or draft state or reviewed, and by cycle ID, like under which cycle you have submitted some proposal. You can also view the draft submitted proposal and download the proposal information as PDF. You can track your proposal. So basically, after submitting the proposal, you can always see whether your proposal is reviewed or not, it is accepted or not, whether it is serviced or not. So that complete tracking of the proposal will be taken care at ExpoSat proposal processing system. Then the reminders and alerts. So they'll be reminded or they will be alerted when the proposal is submitted. So that information also will be mailed to the users. So it will also allow for observation planning. Now coming to the user management. So the system will allow, so ISSDC is hosting a single sign-on service which will allow single sign-on across applications. So as mentioned earlier, there are multiple applications for ExpoSat hosted at ISSDC. So for XPPS as well as the dissemination application Pradhan, for both the applications, users need to enter the same credentials for accessing these applications. For existing registered users at ISSDC, for Chandrayaan 2 onwards, the same credentials shall be required to access. So for Chandrayaan 2 onwards, if any user is already part of our ISSDC user base, they need not even register for accessing the ExpoSat applications. Service provides the new account registration, account activation, password recovery, profile management, etc. And these are the inputs which the users have to submit for registering. So how to access for the users? So the users will be required to log into or access the ISSDC web page, and through the mission menu they can select the ExpoSat page, and among other things the ExpoSat page shall have links for all these applications. Summary. So I will just like to summarize like the XPPS and ExpoViewer applications which are newly developed by ISSDC for ExpoSat mission. XPPS and ExpoViewer internal testing is going on, and it will be hosted in a phased manner to the POCs and scientific community users over internet after clearing the functionality and security related tests and evaluations. The Pradhan application shall be configured for ExpoSat payload data dissemination. So I would like to demonstrate the few slides for a quick overview for XPPS. So this is the home page. So once the user enters the ExpoSat XPPS system, so this is the home page. So here you can see that when a cycle is opened, so those basic information is available readily in the home page, like the GT cycle is opened or AO cycle is opened, so they can submit the proposals. So once they try to access a authenticated page, they will be redirected to a login page. So they have to enter the credentials. They have to, if they are not registered, they have to register. Then they have to submit the proposals. So here you can see they have to option to select the cycle. And suppose already an existing proposal, want to link the proposal to existing proposal, they have an option to link the proposal with the previously submitted proposals. You have the option to add co-proposers. And if it's a coordinated proposal, so you have the option to mark it as yes, and you can enter which coordinate observatory you want to coordinate the proposal with. Similarly, suppose it's a TO, so in the proposal type, if you it's a toggle button, so if you click on that, you can submit a TO proposal. So it's a cover page where you can enter the title, abstract, and the remarks, and this is the observation duration. So you can mention how much duration and in which unit you want to submit your thing. Similarly, whether it starts with it is a time constraint proposal or it's a flexible proposal. And if it's a flexible proposal, then whether you want to allow to split observation into multiple slots. So if that option is okay with the users, they can submit it. So this is the same page where I have selected the time constraint proposal. This is the target selection page. So here I am showing the two screens, one after the other in the same slide. So you have the option to select the target name, and if the target name is among the known 50 targets, it is selectable here, and the corresponding array and deck gets pre-selected for them. If a new target needs to be observed, they also have the option to resolve from the databases, NAD and SIMBAR. Then these are some extra information which may not be directly useful for planning and carrying out the observation, but still they are provided for information purpose. Then you have the option to do a primary instrument selection, and then you can upload the documents. So in the first you can enter the ExpoViewer outputs, and in the second you can also upload the scientific justification for your proposal. So these are proposal details. So it's like a wizard. So you start with step number 1 and go to step number 7, one after the other. Then you have the option to validate all your user inputs, and if everything is validated, then you can submit your proposal. Proposal gets submitted. You have the option to view your proposal, and you can search and view your proposal. Then this is okay. This is for review and evaluation. And this is the ExpoViewer user interface, which is designed newly. Thank you.
Does the ExpoViewer include the smart sensor constraints also when allowing the proposer to make the proposal?
Yes, ma'am. Actually, the Expo Viewer, this is a user interface which is developed.
Correct,
It is
but does it include that is what I'm asking. Just if you don't know, you can
it
check
actually includes the SAP eclipse time as well as it also provides the. I'm not sure about the star sensor.
Yeah, just
but
you can
it provides
check.
SAP eclipse.
Yeah, you can check. And then I wanted to know this coordinated observations. It should not go only as information. Actually, that information has to go to the scheduling team in some way, because they have to know that this is coordinated observations and that therefore there is a constraint in scheduling it. And there should be a provision for the proposer to actually enter later when the other observatory is scheduled. So that's one thing you might want to take.
Actually, one thing is that we would like to automate the process in such a way that to avoid manual interventions. So one option which we were discussing also is that for a coordinated proposal, the user always have an option to give a time constraint as well. So for a coordinated observation, they can submit a time constraint proposal, and that can be taken up in the scheduling process.
Or just like ATOO in AstroSat, it can be triggered when the other observatory is also scheduled the time. That also provision.
Girish. Actually, I just wanted to talk on that, whatever Sita has pointed out. So the reason why she is pointing it out is, it is one of the major drawbacks of AstroViewer. Many times the users submit a proposal assuming that that is available. Then in the last minute, we have to go back and say that, no, we cannot actually observe it because of star sensors is not available. I'm not sure how sensitive this XPOSAT data, these observations for star sensor availability, but it is really important to have it. Otherwise, we will actually miss out certain observations.
Then we will take up this requirement and we will incorporate that also in Expo.
one minor in this one in UI. Somewhere I saw that file sizes are in bytes. It's very tough to convert that into megabytes or something. You can actually.
It's a nothing. It's a configurable
just
software.
Can
so it can be configured to any size.
Okay. Yeah.
Currently, the model on which this whole process is there, is it necessary to follow that model? Here, can it not be completely predetermined? Only for some transient requirements, make provision for changes. Is it possible to plan the entire observation systematically and keep doing that? And only when there is a call for some specific change, incorporate. Why should it go in the AstroSat model? Because the whole thing is much more streamlined here. There are not too many changes that are required. And within one operation, you are not going from one target to another target. The whole thing is much more, can be simplified. Why should we stick to this model? Has that thought been given?
Dr. Sita wants to.
The only thing is, if it is so perfectly streamlined, it will be streamlined based on the POC proposals.
No, I agree with you. Yeah. That is okay. But today, a priori, that whole thing can be thought of, done, and only when you have a transient requirement which comes once in a while. Yeah. For that, you deal. Yeah, otherwise, don't try to make it as a multi-sensor system, which is the AstroSat model. Here, we don't have such complication. Yeah, and in fact, observation for one orbit is completely fixed. And for days together, you are going to do same thing.
So why can't they have to see how to accommodate the proposal based.
I understand. Yeah, see, you have 54 targets or whatever is there. A team can completely a priori look at in what way it can be done, etc. And even if you want to bring in some periodicity, say once in 6 months or once a year, that can be revisited. But we don't have to give so much provision like what you are doing in AstroSat and make life complicated.
Thank you. Okay.
I saw this proposal. The software is very good, like AstroSat. Is there any mechanism to get a feedback? Whatever the proposer asked, are they satisfied with the data, or where do he gives a feedback?
Thank you. Yeah, that. KP? No, but he wants to respond to that. Sachin, do you want to respond?
Sir, so basically, as I mentioned in that slides, that there's an option to for the user to track your proposal. So once your data gets serviced, it gets available in the Pradhan interface for dissemination. So the feedback mechanism can be worked out. We have not given thought on that, but it can be incorporated. We will take up that.
I think that's important.
See, I'd like to reinforce what Kiran Kumar has said, that this satellite requires a different model than Astrosat. You have 50 sources. Let's say you spend 1 month on a source. So you have 10 sources and 2 for background, let's say 12 pointings. And these are predetermined. And in fact, it's very good that they're predetermined so that you have a larger involvement of radio, infrared, optical observations and other X-ray satellite observations together. And this is unnecessarily complication the way it is put, the using of Astrosat model. And the thing is, to even larger, you have 50 sources, you make 50 teams, okay? And you invite people. Okay, you want to be part of SCOX1 team, or GX301-2 team, and so on. And that's why you create a larger user base and a scientific thing. And then you have a fixed target for the whole year. And you have a large involvement of various other observatories and so on. And I think that this should proceed in a different way. And as you said, accommodate TOs. That's all. So all you need is to accommodate TOs in the whole system. It will simplify. It will reduce the overhead on the missions and so on. And unnecessarily recalculating of on short-term visibilities and so on. You have already a visibility. So I would say you go for one target, 70 days, your minimum visibility is there. You observe it for 70 days, then you go for a background, and then you have covered your science,
So I suggest something like, so what I understand is it might be good to spend time now to the first observations, to set up teams to really make a clear plan. And
Sir, I would like to answer that.
That sounds very nice. I mean, it goes back to what Varun was also suggesting. The community should know what should be. Sorry, Sachin?
Yes, I would respond to that.
Yeah,
sir,
please.
actually, for the initial 1 year or 2 year of period, where we know that what is the schedule of the targets and how we have to go about them, that is that approach would have been useful. But maybe later on, when you open it for scientific community submission, then it gives a freedom to the users to submit proposals based on the science value. Because that it was taken.
If I can respond, actually the initial model was that only, that over a year.
Can you hold the mic closer? Because I can't.
During the first year for persistent sources, we'll make a observation plan, and if a transient source comes up, this to be removed, and the transient source source or a few sources can be seen. And in fact, it's not 50 sources. Out of 50, only about 20 to 25 are persistent sources. The overall model, observation plan has to be done always around these 25 sources only, and remaining 20 or 30 sources, or if a new transient comes up, only those are the new ones which can, replace the persistent sources. Otherwise, for XPOSAT, that is a valid model. That we start with 2025, and throughout the mission lifetime, plan is around these 25 sources only. Only a transient source replaces it, but somehow, somewhere, this came up that Astrosat proposal system has to be used and so on.
No, even if you use that model, you can think of a way of simplifying it. You can use only some features of that and don't have to bring it up as a scheduling which has to be done frequently. Even if you use the basic model same, right now, like what he is telling, if something can be planned and done, go ahead and do that. Transient you handle. You don't have to change your software for that. But we don't have to operate it like that all the time.
So do I understand right that, at this point, the team should really do a pre-planning? So the community should be aware. So I think that is a major issue. I don't know to what extent the rest of the community and the broader community in the country, not here, is aware of what XPOSAT will be observing. So if we want to go for this model, then that should be made clear well in advance so that people can take part. Otherwise, people by the time they get to know something is being observed and was interesting for them, it would have happened already. Yeah, so we have to do that. So there's something to be done right now then, if this is the model the community wants to go with. Yeah.
So Vishwajit, so is why is this constraint? Is this constraint because of you have to see only the bright sources and then that energy range?
Yep.
Okay, I mean, okay.
Yeah.
Another thing about is can you look at winter sources?
So that's an exhaustive list of what you can do, right? If I understand right. So that should be easy to put out, right, on a website or something so that people can be invited. Okay, if there are no further points, let me thank all the speakers and close the session for lunch. Thank you, everybody. Okay, I'll hand it over to.
Thank you very much, sir, for having chaired this session, and to all of you to have wonderful questions and suggestions, especially during the last deliberation on the proposal processing system. So I have a request to all of you. In this session, you have witnessed lectures on the entire mission and the scientific instruments as well as the proposal processing system. In case you have any queries or any suggestions which you might have spelled out or might not have spelled out during this session, you please mail us. All of you are aware of the email ID of the Science Program Office. So my request is to send a mail to us with your specific suggestions or comments so that it is easy for us not to miss any point so that we can take it forward for the good of the users. So with this, I thank all of you and let's join for lunch. It is downstairs and we'll join back here at 14:15 hours sharp. Thank you so much. Yeah, anything else? Yeah, for the online viewers, I request you to stay tuned and we are going to come back at 14:15 hours sharp.
Yes, Hassan.
Yeah, Professor Dipankar, actually most of the people are still taking lunch.
I see that there is an announcement that has been put for 2:30. Okay.
That's all right for you, no?
I'm in my office. I'll wait.
Okay.
Yep.
So I was able to see you, but
Okay.
let me, the technical person come, then he
So
will
if some test can be done before that, then
I will give.
Hello, check. 1, 2, 3, 4, 5.
Hello, hello, hello.
Hello.
Good afternoon and welcome back. We are going to start the session 2 of the Exposat user meet. And in this session, we have 3 lectures which will be delivered online. And this session will be chaired by Professor A.R. Rao. So before we start the session, sir, I would request you to say a few words from here, sir.
Good afternoon. Welcome to the third session. And morning we heard what wonderful instruments are going to go up next year. Now will be a detailed discussion of what science can be done. Actually, science of polarization, new thing, anything will be new. Okay. Actually, from the ISP results, whatever we see in X-ray polarization is a surprise. Of course, there will be surprises, but there are 8 talks now. They'll take up the various aspects of various sources in the polarization perspective. To start with, Deepankar, almost a review of the subject. Deepankar, over to you.
Yeah, hello, can you hear me? Are my slides visible? I'm not getting in. Hello, am I audible?
Deepankar, can you hear me?
Yeah, I can hear you. Can you hear me?
We can't hear you. We can't hear you.
Yeah.
Maybe you have to
You know, it says everyone can hear you now.
I can hear you.
Oh, okay. Sushant can hear me. But
I can also hear you. Yeah.
all right. So
No,
people
we
who are
can't
on
hear.
Bluetooth can hear me, but I think the audio is not being routed to the loudspeaker in the hall. Can someone do that, please? Sanjay, Sushant, were my slides visible?
Yes, I could Yes. also see the screen.
Yes.
Yeah.
I'll go back
Now
to
we can
it.
hear Deepankar.
Okay, you can hear me?
Yes, yes. Now we can hear you. You can please start now.
Okay,
So
so
it's
let me
12:33.
start
After
sharing.
12, I will give a signal.
Okay. I will then begin. Good afternoon. So this is a express review of importance of X-ray polarization studies in astronomy. Many of almost everything that I talk about will be discussed in further detail in the talks that will follow. So this will just be a general overview of the importance of X-ray. Astronomy is entering an era of detailed X-ray polarimetry, multiple polarimetry capable missions. Dedicated ones, such as IXP, which is already flying, XPOSAT, which we are discussing today, XIP to come, and possibly other missions. So what I thought I will do in this lecture is to give a very brief overview of how does polarized X-ray emission work, and what does X-ray polarimetry tell us about this. And for XPOSAT, since the band is roughly 10 to 40 keV for polarimetry, I will confine my discussions to those aspects of X-ray polarization which are more prominent in this band. So I will not talk about every possible source of X-ray polarization, but something that is more relevant. Polarized emission from charged particles is, of course, a natural occurrence. If you take a charged particle and ask how does a charged particle emit radiation, charged particle, when it is accelerated in an external field, which could be either due to electric field or magnetic field or gravity. Once the charged particle is accelerated, the instantaneous electric field has a very definite direction given by the velocity and the acceleration. And so this electric field in the parlance of polarization is 100% polarized. But when you take a real source, the net polarization will be different, much lower, for multiple reasons. One is, even for a single charged particle, as time progresses, the charged particle is going to move and it's going to change direction. And both its speed beta and acceleration beta dot is going to change with time. So as a result, the electric field direction is going to change with time. And you will always observe with integration over a finite time band. And that is going to average out the electric field. And as a result, you are going to get a net lower polarization, even from a single particle. But more importantly, what we see from a source is a collection of particles, large number of particles. And each of these can have its own independent electric field direction. When you sum it all up, you will get an average, which in an isotropic source with isotropic configurations will come to zero. So non-zero net polarization requires anisotropy. Anisotropy in the local conditions or anisotropy in the geometry of the source. So that is a given. If you see polarized emission, it is only due to anisotropy in the source, either geometric or due to anisotropic velocity distribution of particles, or due to anisotropic distribution of acceleration, and therefore the electric field or magnetic field that is present. Let's consider one particular emission mechanism which produces very strong polarization, for example, cyclotron radiation. A single particle gyrating in a magnetic field that is linear if you see in the plane of the orbit, then the character of the radiation changes somewhat, and we mostly see the radiation which is close to the plane of the charged particle's orbit. It is largely linear, and when you average over multiple charged particles, there is only one component which survives, which is orthogonal to the projected magnet. And synchrotron emission normally comes from particles. The observed synchrotron emission normally originates in non-thermal distribution of particles with the energy distribution typically a power law, with the power law index between, let's say, 1.5 to 2.5. And in that range of power law index, the net average polarization fraction for synchrotron emission for a strictly ordered magnetic field lies in the range of 65 to 75. So it can give fairly strong polarization. On the other hand, completely ordered magnetic field over the entire source is very difficult to get. So this polarization fraction will correspondingly reduce depending on the distribution of magnetic field, degree of randomness in the magnetic field that you encounter in the source. The third and possibly more ubiquitous source of polarization comes from scattering. It could be Compton scattering or Thomson scattering. It's basically the same process. It just depends on the relative energy of the photon that is being scattered with respect to the rest energy of the scattering body. In case of electron, if the incident photon is much less than, it has an energy much less than 511 keV, it's by and large Thomson scattering. But there is some amount of energy exchange that happens, and that amount of energy exchange becomes larger and larger when in the rest frame of the electron, the incident photon energy becomes higher and higher. But the scattering geometry remains the same, and the origin of polarization is still the same. So let's consider an incident ray on an electron which has polarization in the plane of the slide over here, which makes the electron oscillate. The electric field oscillates this way in the incident radiation, the electron oscillates in response to it. And this oscillation of the electron, which is an acceleration, then results in radiation, which is the scattered radiation that we see. Now this scattered radiation will have polarization vector depending on which is the direction in which you are observing. Now consider an observer located exactly along this path of electron oscillation. That observer will see zero emission for this incident electric field. However, if for the same incident ray, if the incident electric field was normal to this, that means normal to the plane of the slide, then the full oscillation will be normal to the plane of this slide, and full linear polarization will be seen by the same observer. So when the scattering angle theta is 90 degrees, Thomson scattering or Compton scattering will produce 100% polarized light, and it will produce a smaller fraction in intermediate angles between 0 and 9. So basically all that is required to understand polarization of X-rays originating in various circumstances are just those basic things. Now, one needs to apply this to actual geometrical context that obtains in astronomy. For example, accretion disk in a black hole X-ray binary. So, the accretion disk in a black hole X-ray binary produces X-rays, thermal X-rays, because the matter gets hot as matter approaches the central black hole. And this radiation is then scattered before coming to the observer. So the observer sees some direct emission, some scattered emission, and so on. And scattered emission would in general be polarized. Mixed with the direct emission, the total degree of polarization will be a few percent. The larger the amount of scattered radiation in the mix, the higher is going to be the degree of polarization. Some of the radiation that we see from accretion disk is actually reflected from the top of the disk, which is directed towards us. And that reflected component also will have substantial amount of polarization. But all put together, one can then sum it all up and then ask what kind of polarization you see. And one finds that the observed polarization will depend on the inclination at which you view the disk. It will depend on the general relativistic effect, because near the black hole there is a bending of light, and as light bends, because of parallel transport, the polarization plane will bend apart. So due to the GR effects, you will have the inner portions which are normally hotter, so produces higher energy X-rays, having a different polarization angle compared to outer regions of the disk, where typically lower energy X-rays will be produced. Furthermore, the whole geometry is affected by the spin of the black hole. The spin of the black hole drags the space-time around it, and accordingly will modify the polarization. So a good study of the energy-dependent polarization degree as well as angle can find the inclination of the disk and work as an estimator of black hole masses. So this is one of the important things that polarization studies can do. Polix band is well suited for this. Along with accretion disk, these binaries are jets, and jets are typically magnetically confined, and they are copious sources of non-thermal energy. And polarization is therefore expected to occur from synchrotron emission, which will depend on the local magnetic field. Also Compton processes, either external Compton or synchrotron self-Compton, which will also have their own polarization. And by studying the polarization of the jet emission, one can find the jet geometry, one can probe the launching mechanism of the jet, as well as one can find whether the emission, the higher energy part of the emission that you are seeing, particularly, for example, laser jets, whether that's synchrotron self-Compton or external inverse Compton. There is still an ambiguity about that, and polarization is certainly one way. Strongly magnetized neutron stars, where accretion flow is, yeah.
Hello. You have
Yes.
only one more minute. Okay.
1 more minute. Okay, so I'll quickly wrap up. So accreting strongly magnetized neutron stars can produce strongly polarized radiation, particularly near cyclotron resonance. And that cyclotron resonance is very much in the band that Polix will be able to study. That's another important aspect that can be studied by X-ray polarization. Also, one can study from the polarization profile the geometry of the beam, fan beam or pencil beam, which again is an open question. From magnetars, the high energy part of the spectrum, which is resonant Compton upscattering, thought to be, is also likely to have strong polarization. If we have strong enough magnetar outbursts, perhaps POLIX can also study that area. And finally, rotation powered pulsars, where it's a strongly magnetized region, and there are several possible emission zones which can produce emission with different types of polarization geometry. So finding the polarization can tell us where the emission is originating from and where the acceleration is. Therefore, X-ray polarization can probe multiple such important effects which would not be possible or will remain ambiguous without the polarization studies. We hope the XPOSAT will help us unravel some of these. Thank you.
Pankaj, so now this talk is open for discussion. Any comments, questions?
Divankar, a very nice review. One question, how would the spin of the black hole will modify the polarization that would, we can sort of observationally interpret the spin?
Yeah, so if you look at the degree of polarization as a function, which basically is a tracer of how close to the black hole you are going. And if you have a curved black hole with a strong spin, then the disk extends much closer to the black hole. Whereas if your spin is lower, disk stops earlier. And so since the light bending is going to be larger and larger and larger as you go closer to the black hole, if you are able to measure the polarization angle, you will see a larger excursion in polarization angle, and also a lower degree of polarization when you average over the entire disk, because you are going to have a larger range of polarization which are even.
Thank Dipankar again.
Thank you.
Next speaker again online, Chandray will speak on expected impact of XPOSAT on high mass X-ray binaries. Chandray, so 12 minutes talk and 3 minutes discussion. I'll give you a signal after 12 minutes.
I'm still trying to share my screen. Somehow, do you hear me? Can anyone hear me?
Yeah, I can hear you, but we can't see your screen.
Yeah, I'm trying to share my screen, but it somehow asks us for some permissions, and I'm trying to grant them, but it's not accepting it. I will try for one moment more, and then maybe I already sent my presentation.
Chandra, is it okay if we share the screen?
Yeah, maybe due to lack of time, go ahead. Yes, I seem to have some problems.
Okay, we will share the screen.
Sorry about that. Yes. On full screen, please. Okay. Thank you very much, and sorry for the glitch. So I'm Chandray Moitro, and I will talk on the expected impact of XPOSAT on high mass X-ray binaries. It's a bit easier after the wonderful review provided by Dipankar. So for this talk, I will concentrate on the schematic that you see here, which is a typical view of a high mass X-ray binary. where the compact object is usually a neutron star and the companion is a early type star which a mass greater than about 10 solar mass. And when you zoom into the compact object, which is a neutron star, in these systems, they are highly magnetized with magnetic fields. No, don't change the slide, please. I will tell you when to change the slide. Please go back to the first slide. Yes, I'll tell you when to change the slide. So on the left here, you see a highly magnetized neutron star of the order of 10 power 12 cos. And as matter is accreted, it is channeled along the magnetic field lines and decelerates and forms an accretion column on the poles of the neutron star. And as we lose gravitational potential energy, it emits an X-rays. So this is the most simplistic picture, and given that they are one of the brightest X-ray sources in the sky, both in our galaxy and in the nearby galaxies, and they are expected to show a high degree of polarization, they are one of the prime targets for POLIX and XPOSAT. Next slide, please. So X-ray polarimetry now has opened a new window in astrophysics, because now we have two additional observables, that is the degree of polarization and the angle of polarization, in addition to the energy, arrival time, and position of a photon. And this is crucial to break the degeneracy between different models that predict the emission and the geometry of accretion-powered pulsars. And the three most important questions that it can answer is, firstly, high-mass X-ray binary pulsars have complex emission geometries, which I will come to the next slide, and they are highly dominated by the effect of the, no, not next slide, I just said, sorry, there's a confusion, go back to the previous slide. So I will just say, please switch. So because I will explain in the next slide that because of the presence of strong magnetic fields, they can have different emission geometries. And these accretion geometry can change with the infalling accretion rate or with luminosity. In addition, the broadband emission is complex in nature. They have multiple components, and it is difficult to disentangle which region the different components originate from spectroscopic signature alone, for example. And this is where polarization becomes important. Next slide, please. So why is a strong degree of polarization expected? We heard it partially already in the previous talk. So let's concentrate here on the left figure, which is a zoom in on the accretion column, where we see the seed photons on the thermal mount being upscattered in the accretion column. And this is Compton scattering in the presence of very strong magnetic field. And this is dependent on both the energy of the photon and the magnetic field strength. So on the right figure, we see here two emission geometries. On the left is the fan beam, and on the right is the pencil beam. And we see here below is the cross section, which is a function of both the energy and the magnetic field. And the fact that the cross sections are highly dependent on the magnetic field is what governs the emission. For example, when the opacities are lower along the direction of the magnetic field or parallel to the magnetic field, most of the photons escape along this direction, forming a pencil beam. And in the other case, most of the photons escape along the columns, forming a fan beam. Next slide, please. So in the left, we have the predictions from Meszaros in 1988. So this is a very complex figure, but the takeaway point is that the paper simulates for different emission geometries, which are these are on the top are the two angles, which is the inclination angle and the angle with respect to the magnetic field, for different energies and electron temperatures for both the fan and the pencil beam emission. And on the top is the pulse profile, and then we have the polarization degree and the polarization angle. So on an average, very high polarization degree is expected for about 60 to 80%, which is of course dependent on the other parameters that I mentioned. And studying the pulse phase dependence of this pattern can give us insights whether it is a fan beam or a pencil beam. The energy dependence is also very important because especially in the cyclotron line of the source, the degree of polarization increases. And by studying the luminosity dependence of this, one can disentangle the components of the fan and the pencil beam. Next slide, please. So here is a more recent simulation done in 2021, which also confirms the scenario of a very high degree of polarization expected from these sources. So what is plotted here is polarized intensity in random units. But the takeaway point is that as we change the theta, which is the angle with respect to the magnetic field, the polarization increases, which means that at a line of sight perpendicular to the magnetic field, the polarization degree is maximum, and this has a peak near the cyclotron energy that we see. Also, the fan and the pencil beam have different patterns. For example, the flux and the degree of polarization are in phase for fan beam and out of phase for pencil beams. And this way, by studying the total component, one can disentangle the contribution from the pencil and the fan beam emission. Next slide, please. So here is a slide to explain the power of XPOSAT in this regard. So we have the IXP, which is the NASA mission, which was launched in 2021, which is actually complementary because it works in 2 to 8 keV, and POLIX works between typically 8 to 30 keV. But next slide. POLIX has advantages with respect to IXP, in particular for the high mass X-ray binary neutron stars, because the polarization in X-ray pulsars peak near the POLIX band, because they have typically a power law kind of spectrum with the exponential rollover energy, which ranges between 20 to 40 keV. And many of these sources have also cyclotron lines which will fall in the POLIX band. And also we have the XSPECT instrument, which can help to obtain a broadband spectrum of our objects, and also have energy resolved pulse profiles from energies 0.8 to 30 keV in the end, combining both the instruments. So one can simultaneously study the timing spectra and the polarization signatures of the neutron star high mass X-ray binaries to understand the details of their emission geometry. And also the sensitivity can go up to 50 keV for very bright sources. So this is also an advantage POLIX has in this regard. Next slide, please. So here are some results from IXP, which was published last year. So this was indeed surprising, because on the left you see a plot of the energy dependence of the polarization degree and the angle, the top and the lower panel. And we see that the polarization degree reaches a maximum of about 10%, although there is a trend of a slow increase with energy. And here on the right, we see the phase dependence of the polarization signature, which shows a dependence with phase. So the main takeaway point is that although the polarization degree was not detected to be very high, at least in the IXP band, the phase dependence of the polarization signature was helpful in constraining the geometry of the pulsar, namely the two angles, the inclination angle with respect to a line of sight and the angle with respect to the magnetic field. Next slide, please. So there were two other high mass X-ray binaries which were studied, SEN X3 and VILA X1. So these are very classical sources, including Hercules X1, which was also discussed in the talk of Trishojit in the morning. So all three of them actually showed in the IXP band very low degree of polarization. And in fact, in the low state of SEN X3, the polarization was not detected at all. So there were some possible reasons of low polarization degree discussed. One of them were because the atmosphere of the neutron star near the poles is not well modeled yet. So there could be strong temperature gradients that could lead to a change in the polarization modes. Or maybe we are viewing two accretion poles simultaneously, which have very different polarization signatures. And when we average over it, the net polarization degree decreases. But of course, this is then even more crucial to measure for these sources the polarization signature that we get in harder band, because we see that the polarization increases with energy, and POLIX energy band is best suited for this purpose. Next slide, please. So here is on the left, we have the effective area of Polix that we see in the morning. This was mainly to demonstrate that we also have some sensitivity for very bright sources above 30 keV. And on the right, we see the minimum detectable polarization. This is for 3 sigma detection, and the S is the source counts, the B is the background counts, the T is the total integration time, and the nu is the modulation factor considering 100% polarization. So depending on the S, B, and T, one can determine the minimum detectable polarization required for a source. Next slide, please. So this is also the minimum detectable polarization plot that Bishojit showed in the morning. So again, the takeaway point is that these accreting pulsars, HIMARS X-ray neutron stars, are on the brighter end, where you see the intensity levels marked for some of these classical sources. And depending on the exact value of the background count rate or the source count, which depends on the broadband spectrum, they lie within the dashed region. But this demonstrates that Polix can very comfortably detect polarization up to 8 to 10% for these sources. And another advantage we have is that there are 16 such sources with known cyclotron lines in the Polix band. So these are also very important to study. For example, what happens to the trend of the polarization in the cyclotron line band. Next slide, please. So here are some key questions that XPOSAT can address for HIMARS X-ray binary neutron stars with the help of simultaneous timings and spectrum information in a broad band and polarization information in 8 to 30 keV. What is the beaming geometry in accretion-powered pulsar? How does it change with luminosity? Second, is the magnetic field simple dipole, or we have a more complex configuration? For example, if we see a sudden change or a sudden glitch in the trend of the polarization, that could indicate a more complex magnetic field geometry. And another important point is that there are some classical sources which has all the signatures of a neutron star binary. For example, they have a very hard X-ray spectrum, but the conformation of the compact object is missing, and we believe they are neutron stars. So also studying the polarization in these objects can help us to confirm the scenario or reject it. So below here, I just wrote some sources which have open questions, which Polix or the XPOSAT can help us answer. For example, we have some sources which have very asymmetric shape in the cyclotron line. So maybe the cyclotron line regions originate from different emission regions on the neutron star accretion column. So these are very interesting targets to study. Then we have some very slow pulsars pulsating at many thousands of seconds. So there is a hypothesis that these could host magnetas. So these targets are also very interesting to study. Then there are sources awaiting neutron star confirmation, as I just mentioned. These are also important to study. Then there are sources which show special signatures near the cyclotron lines. For example, they show phase lags or a sudden change in the pulse profile. For example, this is 4U0115 plus 63. And in addition, it has 5 cyclotron lines, so the fundamental and harmonics. And then there are sources like GX301-2 and Hercules X1, when one can study changes in the accretion columns structure, so they can be studied at different luminosity or intensity levels, and their polarization signatures can be compared. And of course, we would hope for new transients which go into outburst, and many of which can actually exceed the Eddington limit. So how does the polarization signature look like at super Eddington levels? I will stop here. Thank you very much.
Thank you. So any comments, friends? Chandra, this very low polarization seen in these few sources by IXPE, is it totally different from what we expected, or is it telling something new about the pulsars?
Yes, so the simulations expected a very high, so on an average about 50 to 60 degree, which can exceed to about 80% at favorable geometries, for example. But the IFP results show a maximum of 10% degree. So they could indeed either indicate a very strong energy dependence if we see a very high polarization degree in the Polix band, or maybe it indeed tell us we need to revisit our models or modeling of the accretion column and the emission mechanism in accreting pulsar.
Okay, thank you very much for your time. Okay, thanks again for Chandra. We move on to the next talk by Aru on low mass X-ray binaries.
Good afternoon, everyone. I'm Aru from ISMOHOLY. So today I'll be talking about expected impact of XPET on science of low mass X-ray binaries. So I'm sure in this audience we don't need to describe what are low mass X-ray binaries, but just to kickstart my talk. So these are objects where the accreting object, which is a neutron star or a black hole, accretes from a companion star, which is a subsolar mass or a solar mass companion. And these systems are exotic in sense they illuminate not only in X-ray band but also shows multi-wavelength signatures. This is we have been hearing about XPSAT since morning. So this is like a instrument overview, and we know we have two payloads on board: XPSAT, Expect, and Polix. So they work in two different bands that have different scientific goals which can be achieved with Expect and Polix on board. So for low mass X-ray binaries, what science can be expected or can be achieved with XPSAT? So for low mass X-ray binaries, as we heard in the morning's talk by Professor Paul, that we do have spectral state transition being observed in low mass X-ray binaries. So they have hard and soft spectral state observed in low mass X-ray binary systems, which can either be a neutron star or a black hole X-ray binary system. And in this case of hard state and low state, it's a mass accretion rate, which basically changes the accretion geometry in these systems. So in the case of hard state, we do expect to observe the extended corona, which is Comptonized emission in the form of hot electrons, and the receded accretion disk, which is in contrast to the case of soft spectral state, where the accretion disk goes very close to the compact object. So in order to discern between the geometries of this hard and soft spectral state, in addition to present information which we get obtained from timing, spectral, and position information, we also need polarization measurements which can help us in discerning the geometry of corona in the case of hard spectral state. And in the case of soft spectral state, one can also infer the information about the spin of the black hole, as the accretion disk is very close to the black hole. So how we can do that? So from broadband X-ray polarimetry. So these images or these pictures, we also saw it in the morning. So these are from Shipman Kroll in 2010. So what these information, so these plots are on the top are for the soft state, and on the bottom panel it's for the hard spectral state. And as I mentioned, the geometry changes in the hard and soft spectral state basically they have strong dependence on the energy. With IXP, what we are observing in the soft state observations is basically the contribution to the polarization from the Faraday rotation. However, above 8 keV, it's the returning radiation which is causing the bending of light. So there are two components. One is like Faraday rotation and other is returning radiation. And these two both components contribute in two different energy bands of X-ray polarization. So when we measure the X-ray polarization in higher energy bands, we will get to infer the polarization measurements at higher energy bands, which is basically showing a very higher energy, higher degree of polarization at higher energies, which IXP is completely missing currently because it's restricted below 8 keV. And similarly, in the case of hard spectral state, we can get a different dependence of the polarization angle and the degree of polarization, which is expected to show higher percentage of degree of polarization at higher energies. Again, with IXP, we completely miss out this band. So synergies with multi-wavelength studies, as I mentioned that for low mass exabinaries, we expect to observe strong radio jets, for example, and with ExpoSat we have long observations and week-long observations. We can also look for multi-wavelength coverage in with radio observatories and with other optical and other wavelengths. And for example, this is a recent study which was done with IXP, and with the study of Cygnus X1, the researchers basically they observed the radio jet which was aligned in the direction of the polarization polarization vector, and which basically helped to discern the geometry of the corona in the hard spectral state of this source Cygnus X1. So similar studies which can be done, and it's very useful to discern and refute or basically accept certain models which have been proposed to study the geometry of these black hole systems. For example, with this study, they basically refuted the models which basically favored lamppost geometry, and the extended model, extended corona above the accretion disk was a favored model which can explain the observations with polarization. So Dr. Chandray basically gave a very nice introduction and review about what can be done with high mass exabinary. And similar system, accretion powered pulsars are also observed in low mass exabinary systems. So studies which can be done, explored with ExpoSat are performing pulse profile studies. And this is an example. Dr. Chandray basically explained all the fan beam and the possible geometries which are proposed in the literature, fan and pencil beam. So these possible geometries can be probed with additional components, additional measurements from polarization aspects, and can help us in understanding the geometry of these systems. And this can also help us in testing different models which explains or try to model the pulse profiles which are being observed. For example, this is a particular case where scientists have tried to explain or model the pulse profiles being observed by understanding or by taking the different contribution from fan and pencil beam possible geometries, and see how much is the percentage contribution of the fan versus pencil beam. And with polarization measurements, we can get the contribution of each geometry and try to see whether they are complementing or they are rather consistent with our model predictions, and help us in understanding what our model predicts, or if we need to refine. So this figure again has been seen quite a couple of times since morning. So again, exopolarization measurements for pulse profile study can really be useful in understanding and discerning two different possible geometries in the case of exopulsars. So this is an example of IXP observations of 4U1626. So this observations was also reported in Marshall et al. In 2012. We obtain a very low magnetic, low value of polarization, degree of polarization, which is 2.3%, and completely agree with the fact what Chandray has mentioned. It could be just because these are hard access sources, and major contribution is going at a higher energy band, which is completely missed out with IXP. So with ExpoSat, we expect to observe or measure higher degree of polarization and give more reliable measurements of or tool to understand the geometry of these systems. So with Expect, we have additional onboard instrument which is Expect, and which is really useful for us, because we can have now all diagnostic tools with us, timing, spectral, and polarization measurements all together on board in one satellite. So with Expect, I performed some simulations to understand what could be achieved with Expect. And this is some light curve simulations which I generated using these parameters. And this is using 1 millicraft flux. and using an exposure of 2000 seconds. So even with this 2000 seconds at least, but in the morning, so this is like a low frequency QPOs in terms of timing, which can be detected with expect onboard XPOSAT. However, I would like to mention in the morning, I listened that there could be a modulation in the low frequency QPOs at specifically at millihertz range. So we might have to be very careful if we detect such feature in the expect. But of course, I think there are ways to rule out or accept the observed feature by doing certain simulations if you observe any feature in the power density spectrum. So these were the some parameters which I used based upon the shape of the power density spectrum. Another simulation was done. So these simulations were done based upon different range of X-ray luminosity values. So this is now if we have a really bright source of 1 crab. So this is a light curve which can be observed, and I try to generate a QPO at low frequency of 0.25 and with a time resolution of 0.1 second. So we really get a good detection of a QPO feature in expect if we observe only for 2000 seconds. So which basically hints us that we can really do time resolve studies with expect in terms of tracking the evolution, what Ranjeev was talking about in the morning, which is very useful tool in terms of studying the X-ray variability in these low mass X-ray binary systems. And for X-ray pulsars, of course, spin measurement studies, which is again a very useful way of probing the equation geometries. And so these simulations were done for X-ray pulsar for U1626, for which the pulse profiles were observed. And using this spin period of 7.7 seconds, we can basically get a good hold or measurement of the spin period of the neutron star. And this is the pulse profile, which can be obtained using expect observations of an observation length of 2000 seconds. And this is a shaded region, which basically shows the background contribution. Again, so these two simulations, so here I used the mean count rate of 20 counts per second, which was based upon some communication with expect team. And when I was doing some simulations using the spectral count rate, and then I was getting a very low count rate. So I also simulated using a lower count rate value, which I was getting from the X-ray spectrum. And if we really want to measure the spin period using that extremely low count rate, I think then 25,000 second was the value which was giving us a reasonable pulse profile for doing any additional study. So this is some discrepancy which I might want to discuss with the team. So these are some X-ray spectrum simulations which I performed for the same X-ray pulsar for U1626 67 and using 50 kiloseconds exposure. So this was a expect spectrum which I obtained using the model which was used for NICER value. Source has recently undergone a very low state. So I used the parameters of reported in Mota et al. In 2012, and using that I simulated. So this is a observed spectrum, and in a high state of GRS 1915, this is the X-ray spectrum which we may expect to get from expect in. And lastly, I would like to conclude that in terms of X-ray timing and X-ray spectrum studies, so this is if we have in future large X-ray spectroscopic detector, then perhaps it could be possible to do narrow spectral line feature studies or time resolve study, which we cannot currently reliably do with current expect instrument on board. So this is one simulation for the same spectral parameters which I've shown you earlier for 4U1626, but using the responses of large X-ray detector on board. And with this, I will just say thanks.
Very good. So, okay.
Aru, yeah, I'm here. To basically break the degeneracy between fan and pencil configuration, is there any preferred energy range where polarization measurement will conclusively break the degeneracy?
Yeah, so in case of pencil beam, so what is expected from simulation 1988? Pencil and fan beam basically show the exact reverse situation. So below vacuum resonance energy, it is like in phase for pencil beam, And above that, energy basically shows out, I mean, if you look at the intensity and match it with the degree of polarization measurements in the pencil beam, if it is a pencil beam geometry of that system, then it should be in principle correlated to the pulse profiles. But if it is not, then there could be some percentage contribution from the fan beam.
Yes. So what is the typical energy range?
I mean, it's vacuum resonance energy, what they mentioned, but then again, I would say the X-ray polarization measurement will be an indirect tool to measure that vacuum resonance energy, because we don't know exactly what is that
Okay,
energy.
so you mean the change will
Change or the shift in the behavior.
Thank you.
Yeah, you in the black hole hard state in that plot, you then plot some polarization degree and you change it the car parameter, right? So where exactly are you measuring that? I mean, say for example, at 1 keV, you got not 1 keV, maybe a little less than that. You get about polarization degree of 2, right? Where are you getting that from? Which part of the equation?
Okay. So in the case of hard X-ray spectral state, basically what we believe it's we have the disk which is receded away from that. And so now we have two contributions. One is coronal contribution and other is the reflection features which you observe in the X-ray spectrum. If it is a coronal component, then we expect to observe it in a lower energy band, which is IXP energy band. But if we talk about higher energy bands, it will be contribution mostly from the reflection features in the X-ray spectrum, which will be scattered emission in the X-ray spectrum, which will be causing higher X-ray polarization due to scattering. So we expect to observe higher polarization, degree of polarization in higher energy bands due to scattering or the reflection features we observe.
So you have taken an average value, or you actually? That's what I'm asking. I mean, where you did, from which part of the, I mean, day square corona or whatever you call it, from which part did you take that radiations and computed that polarization, or you took an average of the entire? Yeah. These lines.
These curves are not my curves, but basically they are.
Whoever did
must be average, no?
Yeah, they are average. Yeah, they are average.
Okay.
Okay, so this is regarding phase resolved spectroscopy of cyclotron line, not spectroscopy, polarimetry. Okay, so for that you need to do energy resolved spectroscopy, polarimetry as well to estimate the cyclotron line or what is the polarization at the cyclotron line. Okay, for that you need to have significantly long exposure, and then to carry out phase resolved spectroscopy at that energy range, is it doable? Or what?
Oh, you mean in terms of simulations, are we able to observations for phase result? Is it possible?
Phase result and energy result, is it feasible by colleagues?
So it's a very good question. It also depends on the brighter sources. I think it may be possible, but for sources like 4U 16, 26, 27, where the yeah.
So only if the cyclotron line is lower energy, higher energy may be difficult. So some sort of crude spectrum can be obtained using expect jointly with Polix?
I think that is
not possible.
very useful, but I will request Professor Paul to.
No, even rough thing. I mean, suppose black hole sources, if you want to know, is there a hard tail or something, expect you have a very good spectrum. Some few points can be available using Polix.
I would still say, for those observation dates, you just go by Maxi and sweep that light curve. That gives you the. Polix, after scattering, since you have energy loss, altogether this is not a suitable instrument to talk spectroscopy.
Thank you. Now we have one more online talk by Sushan Konar. Okay, she's online. So you can start now.
Can you hear me?
Yeah. We can hear you.
Okay.
Please start now.
Yeah.
You have 12 plus 3 minutes.
Yes, I'll share my presentation.
There could be some problem. Can you quickly send across your file?
I'm just trying to see if I can
Yeah,
do that. Is it visible?
Yeah. We can see it. Please continue.
Okay. Thank you.
Yeah, please make it full.
Just give me a second. Right?
Yeah. Continue.
So let me begin by thanking the organizers and in particular Bishwajit for inviting me to talk about rotation powered pulsars. Rotation powered pulsars are actually synonymous with radio pulsars, particularly because most of them are visible in radio. And so what I would try to do is try to give a flavor of why one is talking about X-ray polarimetry in context of rotation powered pulsars and how it is going to help the study of rotation powered pulsars. Of course, my task has been made easier by Dipankar giving an excellent review of the entire subject, and also Bishwajit for showing what has been done with CRAB. Probably the only pulsar which has been studied extensively in polarization, both in X-rays and in radio. So let me just tell you a different kind of story today. So now neutron stars, as we know, are roughly can be classified into three categories: rotation powered pulsars, that's what I'm going to talk about; accretion powered objects, particularly objects in X-ray binaries that Chandri and Aru have given excellent reviews on; and the internal energy objects, which are powered by some internal energy, like the magnetars, which are powered by their extremely strong magnetic field. And I understand Manonita would be talking right after me, telling you about the magnetars. Now, most of the neutron stars that we know today, close to 4,000, most of them are actually rotation-powered pulsars. And look at the numbers. This plot is slightly old, but the nature remains the same. So the rotation-powered radio pulsars observed in radio are about 3,400. It's all these orange points. So they are the actual bulk of the neutron stars that you know about. And there are about 100 of them which are NRAD, meaning they are not visible in radio. They're only visible in high energy, meaning optical, X-ray, gamma ray, etc. And about 200 of them which are primarily seen as radio pulsars, but they also have emission in high energy which has been detected. So this two groups total is about, as you can see, is not more than 10%. So most of the radio pulsars, most of the rotation powered pulsars are only seen in radio. And in contrast, the magnetars, etc., are very small in number. But please notice this group, magnetar with an R there, it's the magnetars which also show radio pulsation, and these radio pulsars with an M, radio pulsars which show magnetar-like bursts. They are very important in our endeavor to understand the connection between these objects, and so I will talk about them later. So why is one interested in X-ray polarimetry for the rotation-powered pulsars? It's because of the emission mechanism, which both Dipankar and Bishwajit have alluded to. And I would add two other issues: the subclass characteristics and the evolutionary pathways. Now, for emission mechanism, as Dipankar has talked about, that the emission mechanism of rotation-powered pulsars is a very complicated and still ununderstood subject. The one thing that we understand is the radio emission is only a small fraction of the energy that the pulsar puts out. Most of it comes out in high energy, even though we not, for most of them it is not detected. And radio and high energy emissions come from very different regions. So in particular, if we can have most of the pulsar, many of the radio pulsars have been seen in radio polarization. Detailed studies have been made. But if we can also have simultaneous X-ray polarization studies, that would give us a handle on the emission mechanism better, what are the processes that are happening there, and also give us an idea of the magnetic field configuration, which is very, very important in our endeavor to understand how the emission mechanism works. Now you can see comparison of the pulse profiles of these pulsars. So this is famously Crab. This is another pulsar. This is Vela, and this is Geminga. What you see is for Crab, the pulse profiles are actually similar across the frequency bands. This is gamma ray, X-ray, optical, and radio, even though the width, etc., and the nature changes. Whereas for Vela, the pulse profiles are completely different. They have completely different nature. In case of Geminga, this is one of the NRAD pulsars. We do not see it in radio at all. So its radio beam probably points to a direction which our line of sight does not cut, and we only see it in high energy emission. So therefore, we can clearly see that different rotation powered pulsars are behaving differently, showing different pulse profiles, probably because the regions in from which the emission is coming have different kind of magnetic field structure. So therefore, it is very important for the rotation powered pulsars to have also X-ray polarization studies. Now we will go to the more interesting part, as I try to think of it, as various subclasses of radio pulsars. One of the subclasses in terms of emission is the nulling pulsars. Now what happens in nulling pulsars is when you see this is a pulse profile, for example, and you see that there are some small gaps here, you do not have pulses there. That situation is much more extreme for pulsars like this. There are big regions where you do not see long time intervals in which you do not see any pulses. Here it's more or less periodic. Here the presence of pulse is only for a short time. Most of the time it is absent. So now why do we see such behavior in pulsars? We really do not know. There is another phenomenon that is associated with such nulling pulsars is what we know as mode changing. Now, one of the extreme cases of mode changing is seen in this pulsar, where you see in one phase, this is the radio pulse, and the X-ray pulse is almost absent. Whereas in another phase, the radio pulsar is much weaker, where there is a strong X-ray pulse. So now these studies have been done with XMM Newton for the X-ray and GMRT and LOFAR for the radio. So we do not know why this pulsar is changing mode within some tens of seconds from one kind of emission to another kind of emission. Does the magnetosphere change significantly? What happens to the magnetic field? These are the questions which need to be answered, but we do not have any answer yet. So these kind of systems would be very good candidates for X-ray polarimetry. Now, in a recent work, we have tried to look at the population of the nulling pulsars, and it looks like that nulling pulsars may be associated with specific kind of magnetic field configurations. This is a plot in spin period and surface magnetic field, and these lines are supposed death lines. Death lines meaning that rotation powered pulsars, that emission mechanism doesn't work beyond these lines, and these are theoretical lines, come from a specific assumption about the magnetic field configuration and spin period. And so it seems that we do not see radio pulsars beyond this death line. So maybe there's a specific kind of field configuration associated with it or not. We still do not have the answer to that. We have a GMRT observation program going on, trying to look at all the known pulsars to see whether we can really answer this question. But if we have X-ray polarization studies for some of these objects, that would probably give us an excellent idea as to whether to be able to help us understanding such behavior. Now, one of the classes of neutron stars, the rotating rotating radio transients, that is the RRADs. Now, many people used to believe that RRADs are case of extreme nulling, that is, they just sporadically emit and then they disappear for a very, very long time. And we have done, and you can see in this diagram, in BP diagram, that they more or less occur in the same region of BP space. But we have done detailed statistical studies to see that the populations are completely different. Statistically, there is no correlation, even though the radio polarizations seem to be similar. So therefore, there is again this question: if the radio polarizations are similar but the population statistics are different, is something is happening at the higher altitudes? That is, the magnetic field configuration is different as you go away from the star, which could be answered by X-ray polarization studies. So this is again another question where we can think of X-ray polarization studies. So now we know that the magnetic field of a neutron star is not a simple dipole, which is the basis of our basic modeling to begin with, but various pulsar emission studies, existence of very slow pulsars indicate that there are strong twisted surface field, and there are also indication from the magnetite activities that the magnetic field structure would be very, very complicated. And this again brings us to another context, is the connection between these classes. Now, people believe that there might be connections between these rotation-powered pulsars and the internal energy object, and they would perhaps be connected by magnetothermal evolution between them. Now, observationally, what are we seeing? Observationally, we are actually seeing some indications for that. For example, look at this classical spectra of the X-ray spectra of three types of neutron stars. This is for rotation-powered pulsar, this is for magnetar, and this is for accretion-powered pulsar. Now you see that the accretion-powered pulsar, the curve is totally different. Whereas for the rotation-powered pulsar and for the magnetars, it looks like the nature of the curve is similar, but it's somewhat shifted. So maybe there is a connection. We still do not know. This is a way to try to see whether these objects are connected. So this is from another recent work, and this gray region is again the radio pulsars. These objects are magnetars, but not all of them are magnetars. The red ones are proper magnetars. The blue ones are magnetars which show radio pulsar-like emission, and the green ones are bona fide radio pulsars which show magnetar-like burst. So therefore, there are connections between them. And now we also have extremely slow radio pulsars that are coming up in recent refined searches. And here is GLEAM XJ1627 plus something. It's a very long name. And this object, there is a confusion about this object, whether it is a magnetar, whether it is a radio pulsar or something else. But we see that yes. Maybe this also belongs to the class of very long radio pulsars, which we have started seeing, and these could be connected. So this is a recent work by a young student from BITS Pilani. So what we have done here is these gray dots are present radio pulsars, but very high magnetic field radio pulsars. These red ones are magnetars, and the yellow ones are RRADs, and the blue ones are present X-DINs. Now, there is another work which has come up recently by Jawar and Thomas Tauris. They have shown that the magnetars would probably evolve into these X-DINs, and our work shows that the magnetars do evolve into X-DINs, and these high magnetic field radio pulsars tend to evolve into RRADs. So it seems that all these, the rotation powered objects and the internal energy objects.
Sushant, your time is
yes,
up.
Yes,
Hello?
1 second. Yes, yeah. So, so there are probably evolutionary connections, and I'm sure the X-ray polarization studies might help us. In which way? This is Vishwajit's plot that I'm showing again, and here is the Crab pulsar, which goes from radio band to X-ray band, and you will see that these regions are very well can be studied by POLIX, and so therefore there is hope that we can see magnetars, radio magnetars, and radio pulsars with magnetar bursts with polarization if we have interesting appropriate objects, and that can probably answer some of our questions about the neutron star evolution. Thank you. And sorry for exceeding my time.
Thank you. Any questions?
Considering this, for this isolated radio pulsars, so X-ray flux is very, very low in this band, right?
Yes,
POLIX band.
yes, it is. Yes.
So how long exposure do you expect to have any meaningful estimation of polarization?
I am not the right person to answer this. Really, Vishwajit would be a better person to answer this. I really am not much conversant with the data.
Apart from Crab, any other rotation powered pulsar can be seen by POLIX? You can see that. Maybe two pulsars.
Yes.
There are two pulsars which can be accessed.
Anybody else has? Okay, thank you very much for this nice talk.
Thank you.
We move on to the next speaker. Manonita will speak about magnetars.
Okay, so hello everyone. First, I would like to thank the previous speakers for giving such a nice introduction, so that I don't have to cover some of the topics which I plan to in my talk, particularly Professor Bhattacharya and Dr. Konal. So today I will be talking about magnetars, but given the introduction, what I will do is I will give some unique aspects of magnetars which have not been covered in the previous talks, and then talk about two particular latest case studies, and from there we will discuss how POLIX and ExoSat can come there to have an impact. So three main key points to take from here. Magnetars are, unlike canonical pulsars, powered by their internal decay of the magnetic field, which you already heard. The magnetic field is typically higher. It goes around 10 to the power 14 to 15 Gauss. And most interestingly, in their bright state, they are characterized by a series of repetitive bursts or flares in the X-ray or the soft gamma ray band. And they show a bunch of radiative and spin temporal behavior. The radiative behaviors can include like flare events, outbursts, and short flares that I already mentioned. Alongside the timing behavior can include glitches alongside of complex profile changes with torque evolution as well. So we can try to address at least some of this using ExoSat. So let's start by flares. What are the magnetar flares? These are divided into three broad subclasses. The short flares, which are order of like few fraction of seconds. Then the intermediate flares, which are larger duration, few seconds to tens of seconds. And the total energy output here goes up to 10 to the power 41 to 10 to the power 43 ergs per second. And finally, you have the very large giant flares where a huge energy, almost greater than 10 to the power 43 ergs per second is released over the span of few hundreds of seconds. Now, what are the reasons behind this flares? So there have been two primary scenarios that have been proposed as possible candidates for behind the origin of these flares. One is the change the slide, please. Okay. One is the crust cracking scenario where due to internal stress developed inside the magnetous crust, there is a large scale fracturing of the crust resulting in a huge release of energy. The second scenario is magnetic reconnection events of the twisted magnetic lines of force of the magnetic field resulting in a huge release of energy. And often during these events, during the tearing events, it is expected that the trapped fireball is left behind, which is basically a plasma formed of electron-positron pairs trapped by the magnetic field. Okay, thank you. The next is the magnetar emission, which we have been hearing about in the last talk. So the magnetar emission is interesting, and there can be some thermal component coming from the hot spot where the particles are hitting back following the magnetic field. There can be non-thermal component from the resonant contents upscattering that Professor Bhattacharya mentioned in his talk. But the most interesting part is this hard emission, which is often seen in a bunch of magnetars. And the origin, okay, I won't say unknown, but at least quite highly debated. Why this hard emission comes in the case of magnetar spectra. Next slide, please. And that was a continuum, but we also see lots of spectral lines in magnetar spectra, which are attributed to proton-cyclotron emission lines. Here you can see an example. So the dips are basically the lines, and the corresponding ones are the harmonics. And using this, we can measure the magnetic field of magnetar, but also can get an idea of the complex magnetic field morphology of the magnetars. We often see that this, unlike often the canonical pulsars that we heard about, these lines that we see in magnetar spectra are often very transient events. That means, of course, that can depend on how the resonance scattering process, cyclotron resonance scattering process is happening, but also there can be geometric effects present, which can also affect the polarization. Next slide, please. And another interesting thing, I mentioned temporal changes. So what we see that during a burst event, like shown here, like 40 seconds after the burst to 100 seconds after the burst, the profile can show a significant change. There can be complex peaks that can appear just after a flaring event, but that can disappear after the flux is decaying a significant amount of time. This is also seen during the outburst event. Here you can see as the outburst decays, in certain cases the profile does a significant change from here to here, this to this, and then slowly comes back to its original position. So that can signify a significant change of the magnetic field morphology. And in the previous talk, we already heard about the blurring of classes. I really loved it. This is one of the things that actually excites me very much. And what we are seeing that over, as we are discovering more and more sources, often a large class of pulsars are behaving like magnetars and vice versa. So here I talk about two such examples. One is magnetar-like pulsars, where we see a rotation-powered pulsar is giving actually X-ray emission. Just to answer the question that was asked, this can be another case study. So it actually showed a significant amount of X-ray emission. I don't have any idea about the polarization, but the X-ray emission was significant enough to be detected by the standard X-ray satellite. And it showed magnetar-like flares. And there can be pulsar-like magnetars which can show radio pulsations in the radio band. Next slide, please. So can you go back, please? So here is an example. So this is the pulsar showing magnetar-like flares, and this is the magnetar showing radio pulsar-like pulse profile. Next slide, please. So let's talk about these two case studies. Obviously, the only best thing to use is now IXP. So I will take two examples from IXP and give you an example of what we can do with XPOSAT or POLIX. So this was this was a magnetar that was observed recently by IXP, which is one of the sources in the POLIX candidate list also. This is 4U0142. And what these authors saw is that with energy, the polarization degree showed a certain decrease till around 4 keV, where it went below the MDP, the minimum detectable polarization, and then at higher energy showed a certain increase. And also on top of that, the polarization angle was initially showing a slight variation, but then showed a sudden flip inside as the energy increased. So this is very interesting, but why this flip of polarization angle is happening and why this turnover of the polarization degree is happening, that can be even further probed if we have the further information at higher energies, which POLIX can provide us. And this was thought to be consistent with the resonant Compton upscattering that Professor Bhattacharya mentioned. Next slide, please. To explain this, these two models were proposed, where the idea was that the low energy photons are basically polarized in a particular polarization mode, and coming from the two scenarios on the magnetar surface. So the two scenarios can be either a cap and an equatorial belt where there some condensation has formed, or an entire surface that is kind of heat up and emitting in that particular polarization mode. Now, this polarization, the photons in this particular polarization mode is then getting reprocessed by the magnetosphere of the magnetar, and the higher energy photons therefore are getting emitted in the X mode, other type of polarization mode. So that was used to explain the behavior that we saw in the previous slide. Also, here you can see the pulse profile of the magnetar, and we see that the phase dependent behavior of the magnetar showed a kind of correlation with the intensity in the pulse profile at a particular phase. Next slide, please. So this is the second case. This is another magnetar, not the previous one. The previous one was a persistent, very nice, bright magnetar. This is not a persistent magnetar, but this was also observed using IXP, and it showed a very strikingly different behavior. What they saw is that the polarization, instead of doing a turnover kind of a flip, showed a very steady monotonic increase, and thereby increases in higher energies. What was discussed in the previous talks as well. No flip of the polarization angle could be seen in here as a function of the energy, and these two behaviors were quite different from the earlier case. And the idea was that the scenario here is therefore the physical scenario here should be very different from what we see in the previous case. So even though the high degree of polarization is there, we cannot reproduce it using the RCS model that we have discussed in the previous case. So here, though the non-thermal, one possibility can be that the non-thermal emission is still there. It is emitting at higher energies, but there is something happening in the non-thermal emission which is making it variable, and as it is making it variable, it is also changing the polarization at the higher energies. But then again, the current models, even in this picture, is very difficult to reproduce the degree of polarization. So this is where POLIX can come in to explain what is exactly happening at the higher energies, and is the non-thermal emission really there, and how much it is contributing to the polarization. Next slide, please. Yeah. So this is again the phase dependent polarization for this particular magnetar. And interestingly enough, what we see here is that this is the polarization degree and this is the standard pulse profile. As opposed to the previous case, the polarization degree is anti-correlated with the pulse intensity particular phase. So even for magnetars, different magnetars are behaving in very strikingly different, distinctly different manner. So we need more insight, particularly at the higher energies where magnetar emission can be quite dominant. Next slide, please. Also, not just polarization angle, not just polarization degree. Here we have polarization angle as a function of phase. So here it also shows some variation with the phase, And this has been explained in the light of, again, the previous physical scenario that I have explained, where there is not much significant non-thermal emission because it's difficult to provide the polarization degree that is observed. But more importantly, the idea is that possibly here only one polarization mode is significantly dominant rather than the other one, and resulting in such a very strikingly different behavior compared to the last case. Also here the different line represents the different physical scenarios where the photon emission is coming out on the surface of the neutron star, and the red line here represents the rotating vector model, which is a classic model used to explain the polarization from standard pulsars. Here a high energy coverage may provide more insight, particularly how much the non-thermal emission is there, or what kind of polarization mode or single or both polarization modes are present here or not. Next slide, please. So, in short, to summarize, what we can hope to address through both POLIX and XPOSAT, therefore, are this bunch of questions, at least. Some of them may be more ambitious than the others, but since we are trying to hope, why not hope for the best? So basically we can put constraints on the emission geometry, which I have talked about, and as well as the mechanism, particularly at the higher energies. Remember the hard tail, that's what we call the hard excess, which is still quite debated. And we can compare against the different scenarios among the different magnetars. I just showed you two cases and showed how distinctly different they can be. We can have, this is the last slide. We can have insight in the magnetic field morphology, whether it's a standard dipolar field, of course not, but how complex that is, and the twisting of the different magnetic fields that Dr. Konar mentioned can also be probed through both polarization and spectroscopic measurements. And insight into the complexities of pulse profile evolution during a burst or a flaring event can also be studied using XPOSAT. And finally, cyclotron resonance phenomenon is also related to the geometric effects and can be probed through XPOSAT. And finally, the radio pulsar magnetar connection is of course a very interesting idea that can be addressed through XPOSAT studies. And Professor Bhattacharya in the morning mentioned QED effects like vacuum birefringes. I have hardly talked about it, but I just want to put it here that that's also something that can be in the very long run thought to be probed using polarization measurement. Thank you.
Thank you. Comment.
You showed one case where the polarization degree was increasing with energy, but the angle did not. And any thought about that? Why is happening?
Yeah. So we're talking about the second case, I guess, right? Yeah. So yeah, the idea there, it's a very complex model. It cannot have a one-line answer, but they have come up with the scenario that it's basically the non-thermal case, there is not dominant that much. So, okay, to be fair, that's also not the only unique scenario. But basically one polarization mode is getting dominated, and that is being emitted from, that is being polarized due to the geometric effect of how the belt and the cap are forming on the surface of the magnetar. So that is therefore not affecting the angle that much, but the degree more significantly. But of course, we need to delve into more details to really find out whether that exotic scenario they came up with is really true or not.
Yes, Sachir.
So this polarization measurements during flaring events of few seconds or tenths of seconds. So first of all, you need to have timing, simultaneous timing observations so that you can at least look at into the polarimeter data into detail, whether to find some changes or not. First, that is required. I don't know this spectrometer on board that will give you that kind of light curve.
1 millisecond is the time resolution.
And second thing is, even though flux rise is their order of magnitude, but it's a very small second duration, right? During flares. Okay, that time, with that flux change, it is sufficient to give any meaningful polarization measurement for X?
Okay, I can answer your question in a twofold manner. The first one is the short flares I ignore, but the intermediate and the giant flares are for longer duration, higher energies, so that can be addressed to the expect, if not the Polix. And second answer is, okay, fine. Even if we are not able to catch the flare itself, even for the giant flares, but following the giant flares, the idea is that, there is a lot of changes in the uh, magnetic field configuration, and there is a trapped fired ball left out on the surface of the neutron star. At least for the intermediate flares, even after the flare event has happened, the star doesn't come back to its original state. There's a lot of history that is remaining. And that has its impact on the magnetic field as well as the polarization. See, if we see significant changes in the pulse profile, I would expect some change in the polarization.
Anyway,
And
that
we
we'll
have
see
to,
when this.
that we have to.
Any other? So okay.
Is it fair to say that in general the polarization is all circular, and this O and X mode is this collapsed version of the circular polarization? I'm just thinking aloud. I don't know. Because detectors only see linear polarization,
Yeah, exactly.
and whereas the sources are in general producing mostly circular polarization. So isn't the O mode, X mode are some kind of the way you detect the component of the polarization?
Very sure.
I don't know. It's
Not very sure.
linear is a special case of circular, right?
In general, O and mode, theoretically one mode,
Yeah.
X mode can exist, definitely. But detection-wise, I'm not sure what we are saying.
No, because we don't have detectors for circular polarization.
Yeah,
in
we just
X-ray.
detect linear polarization.
Yeah.
So
In
how
X-ray
much,
we don't have.
how much the circular polarization affect that maybe,
Yeah.
I don't know.
That angle change is an effect of circular polarization or it's a real change of mode?
That's a very good question. I will think about.
So in SPECT, we measure spectrum in low energies, and POLIX this measures polarization high energy. At least for magnetars, will it be worthwhile to have simultaneous astrosat observation, so you have good wideband spectrum also simultaneously?
Oh yes, definitely, because we can have that entire energy range, broadband spectrum, basically. So that would be very helpful.
Particularly this one source which showed very increasing polarization.
And also
right?
the hard tail,
Yeah, correct,
that is
correct. Goes up to
regularly
100K.
seen for a
Correct.
significant number of magnetars. That would be exciting to see.
Thank you very much. So,
Thank you.
we're nearing 4, so we will break for tea now, and we will assemble by 4:10 because we have 3, so that we don't have to waste time. Okay. Hello. Okay, we will start this session with a talk by Santosh Vadavale. He will talk on black hole X-ray binaries, observation with Polix.
Okay, so good afternoon, good evening to all. I will be talking on black hole X-ray binary observations. I have mentioned here specifically Polix. When Hassan actually asked me, the subject was impact with XPOSAT, but I am talking about only Polix. That doesn't mean that expect is not important. In fact, expect is also going to be very important and crucial observations for black hole binaries, as discussed earlier by Professor Ranjiv Mishra. And in fact, I would like to thank Aru because she actually showed some simulations of X-ray binaries with expect, and which actually shows what kind of quality observations we are likely to get from expect itself. So, but because Polix is going to give us a qualitatively a new observation, new type of this thing. So right now I thought it would be more useful to focus on what we can actually achieve with Polix as far as black hole binaries are concerned. So in this particular talk, I am going to focus only on Polix. So in general, I mean, we are all aware about these aspects. Professor Dipankar Bhattacharya also mentioned in detail in his talk why it is important to observe X-ray, black hole X-ray binaries. Primarily, it is like we want to understand the accuracy rejection geometry, and also these are the only source which gives us a possibility to probe general relativity in what we call a strong field limit. And both these aspects are very closely coupled because it requires complete understanding of the not only spectral, timing, and polarimetric properties of the sources. Eventually, it all boils down to the measurement of black hole spin, because even if you want to understand geometry, we require knowledge of a spin, or in order to estimate a spin, we require intimate knowledge of geometry. And all this has been known for a long time, attempted for a long time, many decades. But we know now that the traditional spectroscopic and timing observations which we have their own limitations. They almost reach up to saturation, and basically we require some completely new fresh insights, which is what X-ray polarimetry is going to provide. And in this case, like there are these three primary components. I'm not going into too much detail about this, but basically accretion disk emission typically on a softer X-ray side, coronal emission dominant on a medium energies, and jet emission dominant on a higher energy side. But we know black holes have these different spectral states. They are interplay of all these components, and then their relative importance changes. So at the end of the day, what is important is that we essentially require measurement of polarization properties as a function of energy. So this is very important for black hole X-ray binaries. these plots have been discussed earlier in the for many earlier talks. We will see how they are matching with our observations later on. So again, so what we have discussed so far was kind of applicable before, let's say, 2020. Right now, till all the at least 1 year ago, we were always saying X-ray polarimetry is unexplored. There are no observations. Now that is no more valid, and we are literally in the middle of a revolution, which is caused by IXP. I was just going through total papers, and you can see first 6 months or so, actually, there were not too many papers because people take time to understand the observations, analysis techniques, etc. In only last 1 year, we have more than around 60, 70 papers have come. Almost every month, we get 2, 3. And all of them are very high quality, high impact papers. Most of them are coming in Nature Science, Nature Astronomy. So this is really flooding with us a completely new data. POLIX, when originally was proposed, it was supposed to be a kind of a first X-ray polarization measurement. And in that quest, the impact of POLIX would have been completely on a different domain, because that it would have given us a completely new measurement. Now, with this background, we still need to little bit scale with respect to what IXP has given to us. In some sense, that comparison would not be fully correct, because IXP and POLIX are completely different types of detector, and not only detector or instrument, but by design and by energy ranges. For example, IXP works in soft X-ray 2 to 8 keV with a very high quality polarimeter detector based on a GEM detector, pixel detector, which is at the focus of an X-ray optics. So by definition, it's supposed to have very high sensitivity, and it works with the primary interaction. All X-rays interact with the material with by different interactions. So photoelectric is the most dominant interaction is the energy range. So here, most of the X-ray interactions are being used to probe polarization measurement. Whereas POLIX, first of all, collimated instrument, so essentially it will have a much larger background compared to any of the focusing detect instruments. It will have much larger volume, which adds extra background. And also, in some sense, it works on a scattering, either from Rayleigh or Compton, which is still in this range, a secondary interaction in a sense. Photoelectric interaction is still dominant, even with a beryllium low energy, low Z scatter. And more importantly, as the energy increases, the source flux are typically lower. So, and these are not the comparison between, let's say, IXP and POLIX per se. These are basically the comparison of the difficulties of the polarization measurement in these two corresponding energy ranges. So even if it's not like that, if we have to design a 2 to 8 keV polarization measurement, we will not be able to do this. In fact, yesterday only we had discussion where we are thinking of making a soft X-ray polarimeter, which might actually be better than IXP. But that, when we talk about higher energy, 8 to 10 or 8 to 30 or 50 keV, all the limitations are there. And then that is what is the most important point for POLIX, because there is no other mission plan which will give these measurements in quite some time, at least next 10 year or so. I don't see any real mission planned in this energy range. So in that way, POLIX is still going to be very, very important, even though IXP is essentially flooding us with the completely new and very high quality data. Before moving further, so in that spirit only, I would just like to quickly flash a couple of slides for IXP results. We won't have too much time to discuss on that, but one of the most important result is on Cygnus X1, which is a hard set observation. It showed very high polarization. Basically, it has given us a completely new idea about, not completely new idea, but some very strong constraint on geometry in hard set. Essentially, it has rejected this kind of coronal geometries which people were talking, where there is either lamp post or a vertically confined corona. And these observations are only compatible with either an inner sphere or a overlapping slab model. And then, so this comes very strongly from the energy dependence of the polarization as well as the polarization angle. So both of them are important. Another important point is coming here is that this observation, in order to explain, it requires a very high inclination of an inner accretion disk. And then this is something is also very new, because probably first time we are having this observational evidence for what we call as a warp disk, because it says that the black hole spin is actually misaligned with the binary plane. So outer disk is in a different plane, whereas the inner disk is in a different plane. And then this is the kind of observational evidence which we are getting from polarization observations of Cygnus X1. This is another black hole binary which has been observed with IXP 4U1630-47. This is actually a transient source, and it was recently in outburst. And this interesting from the other side, it is a soft state, gives very high polarization. In fact, so high that it is not compatible with any of the standard accretion disk polarization predictions. So now this is a major problem, that so far whatever earlier we have been used to see this kind of plots are actually not valid for this new observation for 1630-47, because the observed polarization and its energy dependency is much higher than what is expected from the standard accretion disk theory. And in order to explain some very exotic scenarios are required, for example, relativistic wind coming from the entire accretion disk, but with the velocity of 0.5 c. Whether it is realistic, likely or not is a different question, but basically unless we have some very exotic scenarios, we are not able to explain this particular observation. The another point, they had also one more observation which was in what we call SPL state, which is a peculiar state. There also it showed the same energy trend, and then that actually raises a very important question whether there is some contribution of a jet also in this at these energies. So these are still open question, or rather the questions raised by this particular observation. Interestingly, we also should note that we have a couple of Indian groups which had actually published the same results, and interestingly, actually this came also before the original IXP team publication, which actually tells that now our Indian X-ray astronomy community is also quite geared up for all our polarization analysis, and so we hope that we will be able to utilize POLIX very well. Slight one catch, that we need to have high-level software. Oh, my time is over, but so I am not even halfway through. So I will just I'll skip this. So okay. So these are the two other sources. I will not go into detail. One is only LMC-X1. It was completely opposite observation, soft set but no polarization. Cygnus X3, it's a very important, but again I will not go. Basically, it raises a question whether it will have a black hole or not. Authors have categorically avoided to address this question in a paper, but all the indications are that yes, which is long-standing question whether it's a neutron star or black hole, still open, and the polarization observations are possibly more in a favor of black hole. So I will come up. So basically, IXP observations have shown like what we were really expecting from X-ray polarimetry, and obviously because we are very new in the situation, it's very confusing, and more observations are the only way in which it is going to get solved. But what is important now is how well POLIX can take an advantage of the situation. We know that generally a polarization fraction increases with energy, and but at the same time black hole sources are transient. So how we will be able to actually manage this in terms of observation is one point. In terms of actual POLIX impact, I am just showing here some models which have been proposed for Cygnus X1 and for 1630 observation explanation, where you can see that at a higher energies the expected polarization fraction significantly increases compared to lower energy. So this is one very important advantage for POLIX which we are going to have compared to let's say when we compare with IXP. The point is that at these energies, because the decrease in flux, whether even this 20% or 30% polarization, how well we will be able to measure with POLIX is the primary question here. And so also that requires, so what all we need ideally to optimally utilize POLIX is, first of all, okay, so this is where I think we are lagging a little bit in terms of overall Indian community, where we require a very strong modeling framework to expect, to raise the expectation on what kind of polarization signatures are expected from black hole binary sources particularly. There has been a lot of effort on international level in the context of IXP earlier or even earlier GEMS, and so, but all of them are geared for a low energy polarization with respect, since POLIX is now coming up. Either there is one way is to independently do all the theoretical calculations, or maybe possibly we should join with some of that group, because without this it is going to be a little difficult to fully comprehend the POLIX observations of black hole binaries. The next important point is we require a kind of a simulation framework, which is what everybody is now used to, this particular software IXP OpSim, where which tells that with some assumed source properties, spectral and polarization, what level of measurements we can actually achieve. And so this is very important in order to make a realistic expectation and also to plan observations, because how much time we should spend and how much whether, because if something requires, let's say 5 million seconds, then it would be unrealistic to think. But if something is like between 1 million and 500 kiloseconds, there is a significant difference, then we should maybe aim for a little more time. So that kind of idea can be obtained only if you have a robust simulation framework. And then also analysis, where conventionally we have been used to do this kind of modulation curve fitting. I'm showing this one example from an old paper pre-IXP era. This is a polar light observation, where a low statistics modulation curve, how would they look, and then still by fitting them, what you can achieve. So this is how probably right now we will say POLIX analysis might be geared, but what would be important to have kind of this new approach where we do spectropolarimetry using the Stokes parameter approach, where we can actually simultaneously fit all three parameters. This is nothing but a standard intensity spectrum, but these are the Q and U spectrum for the observation. And then when we do this, by definition, it says that the polarization model which is included is consistent with our spectral model or not. So development of this kind of analysis framework is going to be important. We have some idea how to go about it, but it will require some effort. So with this in mind, and I've done some simulations to show what are the characteristics I have considered. So this is the effective area which Paul showed earlier in the morning. This is coming from GN4 simulations by Sujay. These are the latest simulation, 23. The modulation factor as a function of energy, I am showing it from his last year's simulation. There is a qualitative. One more minute, yeah. Some difference between these two. So these are not from the same runs, but I think modulation factor should still remain same with the new scatterer also is the expectation. So whatever results I will show up may not be 100% applicable. There are some approximations made. Similarly for background, I have taken a simplistic approach right now to use a LXPC observed background and scale it to the POLIX volume. And with these, if we see Cygnus X1, I am showing what are the kind of expected energy dependent position we can measure. So if we see the pure hard state, you see these are the actually IXP points, and these are the all other points, including our own CZTI, which are still not reported under preparation for a long time, but these are some of the CZTI points. So you see, if you have some trend, if we assume it to be like say energy independent, then these are the error bars which we will see. Whereas if we assume that this is going to increase as a power law as a function of energy, then these are the error bars which we are going to get. So typically we will get around 3 to 4 energy beams even with the POLIX, and then if we use this simultaneously with the spectral spectroscopic measurement to fit it, then we can actually get a proper spectropolarimetric analysis of Cygnus X1. This shows the same thing in an intermediate soft state. So the underlying power models are different, but because of the fluxes are different, you see that the significance of the measurement changes. So this part, so that is how I think we will be able to estimate it. Same simulations can be done for various different sources. I mean, right now I have not done because it's just a question of time. But essentially, even with the relatively limited sensitivity, POLIX is going to have very good impact on this field of black hole X-ray binaries. But we will need to include, I mean, so this framework need to be made much more robust, including all the latest understanding of our instrument characteristics which we have now, because we have the flight model fully characterized now. So this is what finally I'm summarizing. And then at the end, I would still insist that we need to have efforts in the direction for independent modeling and interpretation framework. Either maybe you can have some of our independent calculation. This is what I was talking with Ranil, or maybe we can kind of join hand with some international groups, because without that, it is going to be a little difficult to interpret what we observe with POLIX, particularly for black hole binaries. So I will just stop here. Thank you.
That's very nice talk. So, the accretion disk emission becomes extremely weak in the POLIX band above 10 kV. So do you think the probing GR or measuring spin is still?
So probing GR is not realistic.
What about using iron line reflection? Is there anything one can do to probe GR?
In general, reflection component does have a hump in this energy range, but I am not sure whether POLIX will have sensitivity to differentiate between a normal underlying quantized component and the reflection. So probing GR, this, but I said it's kind of a generic X-ray observations aim, but not specifically for POLIX.
Lithium scatterer would have given you threshold down to 4.55 kV. Beryllium, the limit is at 8.
It's regarding the last line that you've written in conclusion. I mean, what are we doing about the, the explanation, the modeling? Are you planning anything?
My approach was, okay, I mean, ideally speaking, because in terms of international acceptability also, it would have been important to apply some of the same models which people have already developed instead of redoing the starting from scratch everything. So ideally, we should join efforts with those groups. That is what my approach would be. But I mean, that's where somewhere we have to kind of take a consensus and see how to.
But are they open for collaboration with?
I have approached number of them. I mean, I don't know many of them personally, but so they will be open, but at the same time they will be a little skeptical. So that is how to actually. It is possible, doable, but at the same time, then there are other policy question comes that how we will share data with them, whether we are ready or not, etc. All these things.
All right, thank you.
Last question.
Nice talk, Santosh. And very interesting results from IXP, and I hope from Polix also have similar results. My question is a bit different. Basically, we have been seeing this measurement of spin from polarization measurements.
Measurement of spin.
Spin of black hole. So we have two different ways from spectral fitting. We know the spin, and here the third alternative. Which one is it fair enough to say that polarization measurement of spin is more or better?
No, I would not say that. These are three independent or four actually independent methods. When they converge, you can assume that okay, the spin measurement what we have is a more realistic. Right now, there are two black hole sources for which there are spin measurements from spectroscopy, also two different methods, spectroscopy, iron line fitting and continuum fitting, and QPO. All three are giving different spin measurements. Some of them are actually significantly different. So, right, in that case, the only way you can see is that spin measurements are not fully reliable. When we will have all of them consistent, then we can say that our idea of the spin measurement for that particular system is correct. And this could be different from system to system.
Okay, let's thank Santosh again. Next talk is by Dibijay.
Hello everybody, I am Dibijay from Manipal Academy of Higher Education. So now I will discuss about the expected impact of XPOSAT on active galactic nuclei. So we are going to now extragalactic sources. Now, unlike our Milky Way, in case of active galaxies, we have a very active nucleus which can outshine the rest of the galaxies. And observationally, we do see very different classes of active galaxies. In some cases, we see jet kind of structure. And to give a brief, our current understanding is there is a supermassive black hole sitting at the center, which accretes matter. And also some of these active galaxy harbor jets of relativistic particles. And when this jet makes a small angle to the line of sight, this class are called blazars. And blazars, emission from blazars are jet dominated. Now, even for many decades after the discovery of these astrological jets, still many questions are unanswered. Like we don't understand very well how they are formed, what are the constituents, whether the emission coming mostly from the electrons, leptons, or from the hadrons, the structure of jet, the energy production mechanism, and so on. And also, these jets shows variation. Emits throughout the electron spectrum, and they are highly variable. They show variation from very small scale for few minutes to it can go to few years also. Now, typically how we study this and try to understand the underlying physics of a jet. So what we do, we actually, my apology, it is a Ghisolini et al. 2010 paper, the data taken from there. So we do the observation and we observe from radio to very high energy gamma rays, and then we consider some theoretical model and try to fit that model to understand what are the physical processes happening there. And typically, this emission from the jet shows two hump kind of structure. Now, the two major physical processes which we consider that it happens in the jet, but still, I will come back to my, in my few later slide, that still we are not able to differentiate between whether it is primary emission comes from electrons or it is from the protons. Now the two processes which dominates the jet emission, one is synchrotron emission, where one expects the polarization level to be quite high, and the other one, when these synchrotron photons get upscattered by the jet electrons, then the polarization called synchrotron self-compton, and this inverse quantization reduces the polarization of the synchrotron photon. So it can actually reduces to 20 to 40% of the teeth photon polarization, which is the synchrotron polarization. So now when you consider the on-axis blazars, they are typically considering the broadband spectra, we differentiate in three classes. One is called low synchrotron peak. So this is the most important one, because in the down, if you see, this is the broad ACD, only one part shown. This is the X-ray band, which will be even observed by expectant colleagues. And the red color shows the leptonic model, and the green shows the hadronic model. Both explains well the observation. ACD modeling wise, we cannot differentiate it. However, when you see the expected polarization, then what we find that for leptonic model, the emission comes from inverse Compton, so polarization goes down significantly. Whereas for hadronic model, the polarization comes from X-ray emission primarily dominated by the hadronic process, the proton synchrotron, and that is why the polarization is quite high there. So if one measures the polarization in X-ray band, one can be able to differentiate between whether it is hadronic jet or leptonic jet. The other two cases for intermediate mass black holes, still we are able to differentiate between leptonic and hadronic, but for the last one where we have a high synchrotron peak, they are both cases, both for the leptonic and hadronic model, we get the same polarization. So definitely a low synchrotron peak sources would be a good candidate to study polarization to differentiate between hadronic and leptonic model. So the few important point is, a maximum synchrotron polarization is expected 70 to 75%, but observation is what we find around 10 to 13%. So if in X-ray, if we get a polarization which is similar like the optical polarization, then we can say the jet emission primarily coming from proton synchrotron. However, if the polarization is much lower than that, then you can say it might be because of leptonic jet, where the X-ray is coming because of inverse Compton process. Another important aspect is, as I told, that the jet emission is highly variable, and this is quite one of the source TC279, where you can see that and the particular, if you go to any particular wavelength, there is a lots of variation happens, order of magnitude variation happens over time. Now, flaring study usually is done in a small, when the flare is short term, around the days or less than that. There are flares are found in AGN which goes to weeks, even for months time scale, and that has been studied with gamma ray band as well as in optical band. Still, we are not able to have any very firm conclusion about what are the physical process for the long-term flares. And just to show you, few pictures on that. If you see that in gamma ray we have lots of observation, but when you come to X-ray, we have a very scattered observation. These are one of the flare with one of the jet emissions where we see, and this is the red one is the weekly light curve in gamma ray, and this the band is which is observed in SWIFT XRT. The thin line is with AstroSat observation, and you can see these lines are wherever we have X-ray observation. So though we have the flaring profile in which is around few months time scale, but we don't have any long-term monitoring in X-ray band. So an instrument which can observe for a month or so, spectroscopy, the timing wise, that will give a new information and to a better understanding about the dynamics of this object. Now when we come to XPOSAT, we have one POLIX and another is one XPECT, and XPECT can play an important role to study these flares, which is like a month's time scale, around few weeks to months time scale, to understand the physical process, underlying physical processes there. Coming to the Polix, the possible, what we did, we took around 20 sources where we have optical polarization. These are all low synchron peak and mostly AGN jet dominated sources. And for that, when we calculated, we found that 5 sources are best suited among these 20. So Sene, and among these, I think 3 are in the list of the first year. Sene, 3C273 and NGC 4151. Sene is the nearest AGN to us, and then 3C 454.3, it is the brightest AGN in gamma rays, and low synchron peak. So expected to, this is a good candidate to differentiate, as I earlier mentioned. And then another source, 1ES1959, which is a BLX source, and we have 3C273. NGC 4151, it is also in the list of the first year. This is not a source where we see jet emission. It is basically an AGN where the jet is not so dominated. When you calculate the polarization, so this is not 4 weeks actually. When I saw today's the background number, it will be around 6 weeks. For 6 weeks observation, optical polarization is whatever, the 2 means the second one where we have a multiple observation and the average taken. If you see the MDP is quite high. And as I told, if you go for whether it is hadronic or leptonic, the expected polarization should be of the order of optical polarization or lower than that. Even for 6 weeks observation, all these sources, we need one thing is that these sources, they are very highly variable. So if we can catch them in a bright time, and their flaring time, we may get a better number. But eventually this number does not look very good in that way, in the polarization way with Polix. However, in the future, if you have a better sensitivity, so polarimetry study will be a crucial play a crucial role to differentiate that leptonic versus hadronic scenario. Definitely, we need to observe even with Polix a deeper observation, longer, so that we can have whatever I showed earlier. That also it is, even if it goes something, we have to go beyond 4 weeks. And the added advantage is that when we are observing with expect. So expect can see the flaring activity which frequently happen in these sources. So that will help us to study the flaring profile in a longer time scale. So that's why I told that the long-term monitoring of AGN with expect will have an important role. And of course, we need to study always with a multiband with AstroSat, Fermi Gamma Ray satellite, and as well as ground-based telescopes. One important part, that simultaneous optical polarization observation is essential, because then only we can scale it. So I'll stop here.
As per your simulation, the blazars can be seen by Polix. Even
polarization, very tough to do.
You
have to be very lucky that we say. But as I told, the byproduct can be very strong if we observe with expect.
Vishwajit, which are the AGN you?
These 3, Sene.
December, January, February are relatively bad for
X-ray binary.
X-ray binary.
Yeah.
So Sene, 3C273 and NGC 4151
you are going to see
currently included.
Okay.
Observation plan is not firm.
Yeah. So these things will be observed anyway. So maybe you can have the optical polarization and other observations simultaneously.
Yeah. Maybe the on-axis source will be better if you have to.
Yeah, anyway, these are one of the list in the part of the list.
So observing long term with expect, in coordinate this observation with other observatory like radio observations or optical observations.
Yeah.
That is plan is there something like that? I expect.
See, if we see any blazars, every cases we are lagging there. X-ray part.
Okay.
And so if we have expect, which can observe for a longer time scale, that will be, that will give a complete new information about the
For
system.
me also.
Then we always observe, continuously observe. Optical can be planned. Some of that optical monitoring is there. The X-ray part only missing.
Gulab?
Yeah.
So in blazars, when we are looking through the jets, possibly we are observing emission from different parts of jet, including the core, and if there is a hot spot, that also. So these things, when we are summing the emission, the polarization may get affected. Overall polarization may probably reduce. So anything, any comments?
So if you consider that if it is polarization is coming fast, as I told first that purely synchrotron, expected is 70 to 80%. But because of what you told, it can be multi-zone another, it comes down around 40% to 50%, and observation we see 10 to 20%, 10 to 30%. So that is all. And if you go to that inverse conformation, another scattering, it will come down to another, it will be 40 to 50% of that. So 10 to 20% you expect, not 70 to 80.
Okay, let's thank Dibujay again. Now we move on to the last talk in this session, ULX sources, Vikram.
Good afternoon, everyone. So I'll be talking about ULX sources, the ultraluminous X-ray sources. The names sounds quite different than the whatever previously people have talked, but there has been a lot of similarities for ULXs when I heard the talks, high mass X-ray binaries and low mass X-ray binaries. So I'll be mostly concentrating on a subclass of ULXs, ultraluminous X-ray sources called ULX pulsars, which are very interesting. And this subclass is recently discovered. It's very, very new. So we don't have much information about it. And it has been very exciting results from the spectroscopy and timing already coming out from other observatories like XMM Newton and NuSTAR. Which gives us a very different perspective, or which forces us to think in a very completely different direction compared to what earlier people used to think about ULXs. So as the name actually suggests, ULXs, these are the ultraluminous X-ray sources in which the luminosity is exceeding the Eddington limit, which is basically a limit for a compact object to have a maximum luminosity. So it's kind of difficult to explain that how this sources are exceeding this Eddington limit luminosities. Okay. And there have been quite a few theoretical models to explain that how this could be possible. And earlier, one of the very attractive model was basically to invoke the possibility of existence of intermediate mass black holes. That if we need to explain this luminosity which is above the Eddington limit, then it has the compact object or the central powerhouse has to be an intermediate mass black hole with mass of 1000 to 10,000 solar mass. But recently, like in last 1 decade or so, there has been, as I said, a lot of excitement for this particular field, the ULX in X-rays, because of the discovery of the pulsations coming out from the central object. Now, the pulsation is basically a signature of neutron stars. Okay, so when we observe the pulsation from a compact object, it has to be a neutron star. The possibility of black hole is ruled out. And how the neutron star can have such a high luminosity into a compact object, it's very big questions. So then people have developed another theories where the compact object or the central powerhouse is a neutron star. And one of the possibilities that the neutron star is accreting at a super Eddington accretion rate, which can boost or which gives basically this luminosities above the Eddington limit. It could possibly be a neutron black hole also, but then it will, in that case, it will be a stellar mass black hole. And in the case of stellar mass black hole or the neutron star, the super Eddington accretion scenario is invoked. And in the case of the IMBH, intermediate mass black hole, it could be accreting at sub-Eddington accretion, considering isotropic emission from the objects. So there has been a lot of excitement in last 1 decade or so. So considering that, there is still kind of ambiguity that what is the true nature of this compact object, whether it's a neutron star or black hole, and if it is a black hole, then is it an IMDH black hole or stellar mass black hole? There is no single unified model for the ULXs which can actually describe a broad property of these sources. So in that case, that sense, it is these are very interesting class of sources, and their nature is still debatable. So currently, the new observations combined from XLM Newton and NuSTAR, I mean, most of them actually points towards the possibility of having some kind of beaming which can boost the luminosity if the observer is directly looking towards the beam. Then that can explain this ultra-luminous luminosities. So that combination of some kind of mild beaming and super radiant accretion onto a stellar mass black hole and neutron star, this is coming to be a kind of scenario which people are favoring based on the new observations. And so these sources are pretty powerful sources. I mean, they are emitting luminosities at the above the Eddington limit and giving us a lot of new ideas about how it could be done. But at the same time, most of these sources are extragalactic sources. So they are quite faint and hence required significant amount of exposure time to study them in detail. So what are the spectroscopic measurements tells us about these sources? That as I told you, when you have a simultaneous broadband spectroscopy with this is basically XLM Newton and NuSTAR observations, and if you look at some typical AGN spectrum in this energy range, it shows increasing profile. If you look at the black hole binary, a typical LiPo binary, it shows similar profile with there might be cutoff, but at very, very high energies. Whereas if you look at a typical spectrum, broadband spectrum from ULX, it shows a cutoff pretty close to about 8 to 10 keV or so. And this is kind of has been observed from almost all the ULXs that has been observed so far with such a broadband spectroscopy. And this is then it serves as a signature for ULXs that if you look at the broadband spectrum of ULX, you are expected to see the cutoff around 6 to 8 keV. So in that sense, this object has a particular signature that one can look for in spectroscopy. And of course, in terms of timings, basically people are now trying to look for signature of pulsations, so that to basically see how much ULXs can be described as a neutron star compact object. And this population of neutron star, what we call ULX pulsars, is growing day by day, because the evidence of pulsations are now coming. The first was discovered about a decade ago in M82, and it's a kind of coincidence that when this pulsar was discovered, the observation was taken for almost 10 days continuously. Okay, and that was not aimed for the ULX, but it was some supernova and into a galaxy M82, and the observatory was looking at supernova, but luckily in the field of view the ULX was there. And that was the only kind of observation of a ULX exist for so long, continuously for about a week or 10 days. So it's just a coincidence that such a long observations can be useful, okay, for ULX pulsars. And expect and Polik's typical observations time will be of the order of a few weeks. Then we can actually have a better search for pulsation in expect considering its 1 millisecond timing resolution. Okay, so now as I showed you that since this population of ULX pulsars are growing, still there are only handful of sources available which shows pulsation for ULXs. So they are called ULX pulsars. The first one was M82 with a pulse period of about 1.3 seconds. And after that, there has been almost couple of other ULXs, NGC 7793, NGC 5907, 300, 1313, and M51X7. These have all shown pulsations of different periods. And however, these are the interesting sources because the neutron star is there at the center. But if you look at the typical flux from these sources, they are of the order of minus 12 at the most. The brightest one is somewhere few to the power minus 12. So if we look at the typical effective area curves of the polix and this flux, the observations will be of the order of maybe months or something like to have some kind of detection from these sources. So it's okay. Sorry? I'm coming to that, right. So these are basically all extragalactic sources, and that is the reason that they are very faint. So, but luckily we are not restricted by only extragalactic ULX pulsars. There are these two pulsars. One of them, Swift J0243, is luckily a galactic pulsar, and that one is quite bright. As you can see, the flux is 10 to the power minus 7. Okay, and this was the only galactic pulsar known so far. This is the only galactic pulsar. We can also try to look at our neighboring local group of galaxies, SMC and LMC, and they also seems to be pretty reasonably, bright to study the polarization. So the importance is that even if we cannot go for extragalactic pulsars, we should look for the pulsars in our galaxies that exceeds the Eddington limit. Okay, so one of that similar source was observed recently. Santosh has just mentioned. This is the Cygnus X3. This was recently observed by IXT, and they have classified it as a galactic ultraluminous X-ray source, but it was hidden. Say. So it has been observed that Cygnus X3 was exceeding the Eddington limit, and IXP has observed this. I think Santosh has showed these plots, but the important thing is that the IXP made two observations. One is in hard state, one is in soft state, and these observations for of the order of 6 to 7 days, maybe this 5 to 7 days, and they have detected a continuous polarization of the order of 20% for the hard state and of the order of 10% for the soft state. So the polarization features or the polarization characteristics changes as a function of the state of the source. So you can see here, this is energy, the polarization as a function of energy, and the polarization is more or less constant throughout the IXP energy band from 2 to 8 keV. Now the question is whether this, you see some kind of dip here, this is the iron line region, 6 to 8 keV, and other than that it's more or less constant. So 20% is quite high polarization from Cygnus X3, and the question is that does this energy independent feature of the polarization continues at hard X-ray, or as we expected the polarization signature increases as a function of energy? Then we can have that impact using the Polix data from 8 to 30 keV, and another thing that they have done is that, as Santosh again mentioned, that they have done the spectropolarimetric modeling for this source, and they found that the spectrum is basically very similar to ULX spectrum. It can be described by power law, low energy component, thermal component, and of course the iron line. And they could in fact distinguish the polarization feature for each component. And they found that most of the this power law component was highly polarized compared to the thermal component, the black body component. And hence they concluded that the primary X-ray source is obscured, and we see only the reflected or the scattered light, because power law was mostly the dominant, was dominated in the polarization features. And they came up with a geometry of the source, but as previously mentioned, they have kind of not given any particular conclusion that whether this source contains a neutron star or a black hole. Okay, so they have mentioned that if this opening angle is of the order of 8 degree or so, a neutron star can explain the Eddington luminosity, or if it is more than 8 degree, like almost double, 16 or so, then 20 keV black hole can also explain this super Eddington luminosity. Another galactic source that I told you that this is the first galactic X-ray pulsar observed, Swift J0243, and this was discovered in 2017. The outburst started from October 2017 and lasted almost for 5 months. So we have enough time in case the source goes into outburst. We can observe there is no need for fast moving for the satellite. It lasts for 5 months, so observing should not be a problem. And the peak luminosity at the outburst is 7⁻⁷ Earths per second, which is more than the Crab. Okay, in 3 to 80 kV energy band, the luminosity exceeds the Eddington limit, few into about 39 Earths per second. And since it is a galactic, it's very nearby, so we will have a lot of photons, lot of sensitivity with the polys. So this was the first outburst, and I think I recently heard that it has gone into second outburst now, the going on. So it will be very, very interesting source to look with the polys. And this is what the geometry they have come up with, but it's not sure whether it's a pencil beam or fan beam geometry. Just I'll show this last slide that this IXP has observed the 10A region, and within that region there was one ULX. Now this is the core of the Centaurus A, so this ULX, and they could put a limit of MDP about 15%. So if you look for a normal ULXs, this is not a pulsar ULX, and this is extragalactic ULX, so there is a MDP of 15%. But if we look for the galactic pulsars, these are the only sources which can actually tell us about what happens to the polarization signature when we go for the super Eddington accretion compared to the normal pulsars. So I think what we should do is that the galactic pulsar is the prime target for first half or first lifetime of the polys. Later on, if you find interesting results, we can go for the extragalactic pulsars. I'll stop here.
Thank you. Questions, comments?
This extragalactic ULXs you have tabulated.
Which one?
Are they transients or persistent ones?
They are mostly persistent. Actually. Don't see it as transient. Yeah. This galactic one was transient.
Extragalactic ULX polys cannot say no. I mean, it's not possible.
Not possible, right?
It's very faint.
But I think we can learn something about from the galactic ULXs, and then I try to extend that to the extragalactic.
So you have not talked about any spin of the ULXs. I mean, any comment related to that?
It's basically kind of same as normal pulsars. If it is a neutron star, okay. So as I showed you in that table, I mean, the spin ranges from sub-seconds.
No, I'm talking about the black hole ULXs.
Black hole, no. I think it's very, very difficult. Spin of the black hole.
How well the galactic ULXs resemble with the extragalactic ULXs in terms of spectrum? Because the extragalactic ULXs so cut off around 8 keV, and if that is if these objects show the same cutoff, some kind of cutoff, then studying with polys may be difficult.
I think so. As far as these two sources are concerned, Cygnus X3 and Swift J, they have mentioned that the spectra actually resembles quite well with the extragalactic ULX pulsars. They have seen the cutoff around 10 keV for Cygnus X3 and the Swift J also. For Cygnus X3.
And even with the cutoff,
100 keV. But then it will give us a chance to study the super Eddington accretion.
Even with the cutoff, the Swift source peak was 10 Crab.
Vishwajit, can you hold it closer?
The Swift source at its peak, even though it has this 8 kV cutoff, was a 10 Crab.
Oh,
in the Swift band telescope, right now. It's very bright. The spectrum has a cutoff at 8 to 10 kV. In spite of the cutoff, the luminosity in hard X-ray band was 10 Crab. That is also possible.
So.
I mean, the Fermian integral has shown up to 100 kV. Yes.
Vikram, you showed the cutoff typical ULX. Are they similar for pulsar ULX and other ULX?
They are for extragalactic pulsars. They are quite
similar, whether pulsar or not.
For ULX, it is a signature. No.
Are they going to observe or not?
I'm not sure. Do you have any idea? Outburst, I think it's going on still.
Okay, I think we'll continue.
The first one was 5 years ago, but now
I'm
the
not
second one
sure.
is
I haven't heard of anything.
Vikram, thank you.
J0243.
Okay, we'll now continue this one. So
Yeah,
this-
and it has a very long outburst.
Okay, let's thank this session gets over and next session
Thank you very much, Rao sir, and
Second.
all the participants here for making it so lively. And we are going to start the third session, and it will be chaired by Dr. Sita. Over to you, ma'am.
Come to the last, which we will have discussions. So as a team, now we have to work towards timekeeping. So let's work towards it so that everybody can participate in the discussion session, including the online members. So over to you, Varun.
Thank you. So
I'll give a ring after 10 minutes.
okay. So in the interest of time, I can keep my talk very, very short. The topic is how can XPOSAT revolutionize medium energy polarimetry of GRBs? The answer is it cannot. Thank you. So should we go over to the next talk or should I use a few more slides? Okay. So why polarization, right? So when we are talking about new era of polarization, lot of these new revolutionary observations and so on, all of this is also happening in the world of GRBs. GRBs, gamma ray bursts, we have been studying for several decades now, right? And overall, there is a strong magnetic field creating strong jets. So it means that you are going to see polarization. And this polarization measurement is important for a lot of scientific inferences. There are open questions about the very central engine of gamma ray burst itself. Okay, so for example, the emission mechanism, we see signs of synchrotron. We know that Compton has to be playing a role. There are hints of thermal components. It's going to be a mix of all of these. How do we know what it is? Just from spectral modeling, we have been unable to say anything about it. Improved prompt spectroscopy will help, but also each of them has a different signature in terms of polarization. So polarimetry matters. Then directly the magnetic field itself. If you have an ordered magnetic field versus random incoherent magnetic fields within the jet, that's going to give you a different signature. If you are looking at the geometry of the jet, are you looking at small angles, large angles, that changes everything. So the idea is that you actually measure the polarization amplitude, you measure the, polarization angle, the polarization fraction, and you do it statistically for a whole set of GRBs, and that will help you answer some of these questions. Okay, so what GET models? Typically, there are three models that are discussed in this context. The first one here is the synchrotron ordered model, where the idea is you have a global coherent magnetic field within the jet. So you have an ordered magnetic field, you are getting synchrotron radiation from particles in that magnetic field. Or you can have a synchrotron random model, where now the field, instead of being generated by the central engine, is being generated by shocks within the jet. So it will have, each shock will create its own magnetic field in that region. They will have different directions. So you have a random set of magnetic field. The Compton drag model talks about soft seed photons from the base of the jet being Compton upscattered by electrons and other particles within the jet. And then that is giving you polarization again as a result of your viewing angles. The basics of this were discussed by Dipankar in his lecture today. There are other factors that matter as well. So for example, if we look at this thing here, what is shown in red, so this is a slide made by my student Divita. What is shown in red is basically your prime jet. And in the jet now, you imagine that the outflow has some
factor gamma. Okay, it's a relativistic outflow moving out with some factor gamma. So the beaming from that will give you a characteristic angle of gamma inverse. So if you have a highly relativistic jet, each particle is going to emit only pretty much in the direction that it is going. If it is a mildly relativistic jet, it will spread out more. So this is a, so imagine you have random magnetic field and these three green circles show those three random directions. If you have a highly relativistic jet, you are going to see just one of those. Whereas if gamma is lower, then you are going to see all of them together, so that the whole effect is averaged out. You will see strong polarization here and weak polarization here. On the other hand, over here, this is now an ordered synchrotron case again. So I have a global magnetic field. And if the observer is inside here, then what is happening is that the net polarization in that, not for synchrotron ordered, but actually for Compton drag and other models, the net polarization just cancels out. Whereas if the observer is actually outside the jet or at the edge of the jet, you get a different effect. Now, all of these can be calculated in great detail and you can make very, very confusing tables. So let's look at the first case. So suppose I am an observer within the jet. The jet is beamed directly towards me. I have also considered a photospheric model here, which I didn't discuss. But most models show that this is not going to be polarized. Here H, M and L talks about cases where the jet is highly relativistic, mildly relativistic. Okay. And then you can see that as you keep going over, for every possible case, there are 3 columns here with 3 cases per and 4. So there's way too many things that you can do. And you can cook up a lot of numbers for what the polarization of a given GRB might be explained by. Okay, but there are some key things. Some models intrinsically show lower polarization. Some show, so here what I'm showing is, this is from a review paper by Toma et al. What is shown is for a population of GRBs detectable by a certain mission, on the x-axis is the E peak for the typical band function of the GRB. So you could think of it as a characteristic observed energy. And on the y-axis is the polarization fraction. And what you see is that Compton drag model can sometimes give you very highly polarized GRBs. The synchrotron random typically gives you low, which is in green, and then the synchrotron ordered seems to follow this relation. But again, an individual GRB, if I see a GRB here, for instance, it is right within the territory of all 3 of them. So what you need to do is observe a lot of them. So this is a figure from a proposed GRB polarimetry instrument called LEAP, which is an American proposal for the International Space Station. On the x-axis is number of bright enough GRBs, and on the y-axis is the number of GRBs where they would detect polarization. Okay, so what it says is that if you look at, say, the synchrotron random model, if that is the one that is really explaining GRB polarization, then the percentage of bursts that are polarized is low, and even in those cases, the polarization fraction is going to be quite low. So if your statistics start going that way, then you are proving the synchrotron random model. On the other hand, if you have a Compton drag model, there's a medium number of bursts which are polarized, but some of them can actually have a very high degree of polarization. So that is here. And the synchrotron ordered model, if that is what is really causing the emission. Also, in this case, we are assuming that all GRBs share the same emission mechanism, which may not be true. But if that is indeed the case, then you will see a large fraction of GRBs being polarized. Now, all of this is talking about detecting hundreds and hundreds of GRBs, at least 100 to distinguish between these. With more sensitive polarimeters, people are claiming maybe 60 would be enough. The status so far is that throughout all these decades, about 40 GRBs have measured polarization. Great news for us. Dominating the field is AstroSat CZTI with 19 measurements right now. Remember, CZTI was meant to study cyclotron lines for on-axis sources. We then started discovering GRBs, discovered 550 of them, measured polarization for 19 of them. Polar, on the other hand, was a dedicated polarimetric mission, and we are doing better than this. So this is great, but still not conclusive enough through all of these to actually say which of the models is true. Right? So now the question is XPOSAT, great, polarimetric mission, different energy range, what can we actually do about this? But the whole thing is designed to look at on-axis sources, which also means that it is designed to avoid interference from off-axis sources. right? So will this actually work? Maybe, maybe not, right? And then of course we need to simulate this to figure it out. So I sent a SOS to Sujay. You have heard his name in many talks by now, clearly rising star of giant simulations and polarization and everything. And he said, yeah, sure. He's done the AstroSat mass model for polarization and then swarm and now this. So he actually ran some simulations, starting of course with the on-axis GRB. So you take a GRB on-axis, the flux is 10 raised to minus 4 ergs. This happens for about 5 to 10 GRBs per year. And you take a normal band spectrum and you simulate it, and the two curves here, okay, the blue curve assumes that the GRB is completely unpolarized, and this is the modulation curve that you would see, and the orange one is a fully polarized GRB, and you can see that there are many bins with a statistically significant difference. We did not take this all the way to evaluating a MDP and so on, because the odds of getting a GRB on axis are 0.02%. So 2 into 10 raised to minus 4, that's just the fraction of the sky that is covered by polix. What about off axis? So there are two different thetas here, two different phi's, and in all of these cases now the curves are completely indistinguishable. So that's my summary on slide 1, that unfortunately for off axis GRBs, we are not going to see a polarization signature. Not very surprising again, given that the instrument was not designed by this, but for this goal. But it's always nice to investigate if something else can be done with the instrument. So with complete simulations, the answer is that it cannot. So in the primary field of view, the percentage, the odds are simply 0.02%. So not going to work. On the other hand, off-axis GRBs, can XPOSAT do anything at all? It can detect GRBs still, because you will see it as background, as an increase in background. You'll also see it in expect. And if you take all of that data, if you have time tag data, then it can actually contribute as a node of the IPN. So by just using the GRB detection, by using the light curve as seen by XPOSAT, you could actually triangulate a GRB by combining it with other observatories. This is routinely done for several satellites. So that is what can be done. About GRBs and polarization, of course, AstroSat is going strong, and we will keep measuring polarization for more GRBs with that. The CZTI team is actually close to releasing publicly the full pipeline for polarization analysis. So if you are interested, you can contact me or Rao or Santosh, Mithun or anyone. Among future missions, Daksha will be able to do great polarization measurements. So here are two simulated GRBs with polarization contours drawn. In both cases, the red triangle shows the actual polarization that was injected, and the blue cross shows the values that were recovered. And you can see that they agree quite well. This is not a Daksha talk, so if you want more details, go to the website, and I will stop here. Thanks.
Thank you. 2 questions only. Questions? Yes.
How faint GRBs can be detected by XPOSAT?
We did not check it out as to how faint a GRB can be detected, but
just -4, how much count?
No, how many counts did you get? Yeah, okay, my guess is that it will go to -6. So, respectable number of GRBs will be detected per year.
Nice talk. Maybe it's a naive question regarding the models. You discussed the 3 models. What are the other parameters other than polarization which can help us in understanding whether which model is favoring?
See, if you look at the 2 models, they are both talking about overall synchrotron radiation. Even if you have multiple shocks creating multiple emission regions, you are always seeing an average spectrum. And also the spectrum itself is evolving with time. There have been papers which say that the reason why the band model works well is that it is a time average of many individual spectra. So given the sensitivity of even something like Fermi, we cannot do fine enough time resolved spectroscopy in order to do instantaneous fit of a multi-component model. So if I want to fit inverse Compton plus synchrotron, I cannot do it currently. This can, again with the increased area, but right now we don't know. So spectrally, these models are indistinguishable.
Thank you. Varun, speaker is Alan.
Okay, so I'll be talking about the AGN sources. Already you had one talk on this. So there will be some overlap between some of the slides here and what WJ has presented, but I will try to skip those. So I'll be talking about AGN sources, IXP reserves, and the prospects with ExpoSat. So here I will be talking about both radio quiet category of AGN as well as radio loud category of AGN. If you see the radio population, about 85% emit less or no emission in the radio band, which are termed radio quiet. So firstly, I will talk about this population of sources. So if you talk about the radio quiet category of AGN, the X-ray emission is basically by condensation of the optical UV photons, which comes from the accretion disk. And this produces a power law emission having a high energy cutoff. And from X-ray observations, people measure this cutoff and try to infer the temperature of the corona, and this cutoff is related by 2 to 3 KTE, where KTE is the temperature of the corona. So part of the X-ray emission, which is also reprocessed by the accretion disk, as well as the torus and the broadline region, and this gives rise to some reflection features in the spectrum, and you notice a Compton hum around 10 to 30 keV, as well as an FE line around 6.4 keV. Therefore, from the analysis of the X-ray spectrum, it is possible to characterize the temperature of the corona. But this is not new. This has been actually for about 3 decades. People have used observations from Compton Gamma Ray Observatory, the POSAC, SWIFT-BAT, as well as integral to characterize the temperature of the corona. And most of these observations, they generally fit a cutoff power law, try to determine the E cut, and try to analog with the temperature of the corona. But for a realistic estimate, one has to fit physical models to really infer the temperature of the corona. And this field took a tremendous advancement at the launch of NuSTAR, which happened in 2012, mainly because of its broad spectral coverage of 3 to 79 keV and as well as the high sensitivity beyond 10 keV. So what do you know from NuSTAR? Since the launch of NuSTAR, there are several observation studies mainly reporting the temperature of corona of a large number of sources. And in all these, or majority of these studies, they mainly fit a cutoff power law to infer E cut. So here in this work, what is done, the authors have looked into the publicly available NuSTAR data for the last 8-9 years. They tried to fit physical models, and here is shown the distribution of the temperature of the corona for about 3 dozen Cepheid 1 sources. Similar plot is also there for a Cepheid 2 category of sources. And in addition to inferring the temperature of the corona, one can also ask the question, does the temperature of the corona vary? And it is possible to address this question because of the availability of multi-epoch data from NuSTAR. And here it is, I have shown 2 examples where people have found variation in the temperature of corona by analyzing NuSTAR spectrum over multiple epochs of time. Alternatively, these 2 authors have used single epoch spectra, divide the data into several flux states, and these 2 authors also have come up with the variation in the temperature of the corona at different flux states of the source. The takeaway message of this thing is that from X-ray spectral analysis, one will be able to constrain the physical parameters of the corona. However, X-ray spectral analysis is insensitive to the shape and location of the corona. So this is a major thing to know, and the measurement which can provide answer to the geometry of the corona is X-ray polarization. So what do you know from X-ray polarization? Here I show a simulation done by Ursini about a year ago, where they have done detailed Monte Carlo simulations to predict what could be the fraction or degree of polarization expected from these 3 coronal geometries. So what is shown on the top is the slab geometry, and this is the spherical lamppost corona, and what is shown on the bottom is about a cone-shaped geometry of the corona. So here are the expected polarizations. For the slab geometry, you expect high polarization of around 12%. For a spherical geometry, it is low of the order of 1 to 3%. And for a cone-like geometry, the polarization is typically intermediate of the order of 7%. This is based on the simulation. So can we see this from observations? So I would move on to a recent IXP observation carried out on the source IC4329A. The observations happened on 5th January 2023. So what we have done, we have taken the data and we have tried to infer the polarization, and this is what we obtained. So between 2 to 8 kV, we obtained a polarization of 3.7%, and between different energy bands of 2 to 3, 3 to 5, and 5 to 8, these are the numbers. So between energy bands, there is no wavelength dependent polarization. This is what we noticed. And the same IXP data, we also tried to do spectropolarimetric modeling, and that yielded a polarization degree of 4.8 degree, which more or less matches with this. And based on these measurements, what we conclude is that the observations rule out the spherical lamppost geometry in this particular source, and the observations tend to favor a corona with a conical geometry. So this is on this particular source. Now I will show you a summary of what all IXP has done. So this is the status of X-ray polarization studies done by IXPE. As of now, IXPE has observed 4 sources. So this is the source which we have recently carried out the analysis. So apart from this, we have the MCG source. It is a limit. So they argue that their observations tend to favor a lamppost corona. NGC 4151. Here again they found a polarization degree of 4.9, and they rule out the lamppost geometry. And in IC 4329, it's about ruling out the spherical geometry. So these observations give some indication, though the observations are limited, it is very clear that the geometry of the corona in all sources are not common. So it may be because we have a limited number of studies. Possibly these studies need to be extended to a large number of sources to really pinpoint whether all sources have an identical geometry or the geometry of the corona changes from source to source. This is about the radio quiet category of AGN. Now I will move to the radio loud category of AGN. So when I talk of radio loud category, this is mainly blazars. So already you have heard a talk by Dabujay, who has concentrated on this. So coming to blazars, these are a special category of AGN, and they come in 2 flavors. One is called flat spectrum quasars. They have broad emission lines in the spectrum. The other flavor is BL-like objects. They have a featureless or a lineless spectra. And if you see the broadband spectral energy distribution, they have 2 humps. This is the low energy hump, peaking mostly in the optical UV IR region. The reason for this hump is reasonably well understood. Basically, it is because of synchrotron process. However, the origin of the high energy hump is highly debated. We do not know whether it is because of a leptonic origin or it's because of hadronic origin. And by modeling the spectral energy distribution of these sources, the situation is really complex, because by modeling the SCD, it is really difficult to pinpoint whether the SCD is explained by a hadronic model or a leptonic model. As an example, I show one plot of a flat spectrum quasar. It is 3C279. So this source, there are 2 SCDs plotted. The blue SCD is based on the observations done in a flare in 2013 December, and the red points pertain to the SCD which was done in 2014 April. So if you fit this broadband SCD, the 2014 observations are nicely explained by a leptonic scenario, whereas these blue points, when you go to the high energy, there is some upturns seen at high energies which cannot be explained by a single zone leptonic emission model. Alternatively, the SCD can be fitted by a multi-zone leptonic model or a hadronic component. So the situation, if you look into the broadband modeling of SCD, it is highly complex, and it is difficult to pinpoint whether leptons are playing a role in the high energy process or hadrons are playing a role. So this is based on SCD. Subsequent to that, people thought if you try to look into the correlated variations of GeV photons and optical photons, we will try to pinpoint whether leptonic model is playing a role or hadronic model is playing a role. This is the idea. So what people did, they tried to look into the optical light curves and the GeV light curves to try to see if they are highly correlated. The outcome of this study is that people found that these 2 variations are highly complex. People found cases where there are optical flares without gamma ray counterpart, and there are gamma ray flares without optical counterpart. So from optical and GeV studies also, it is difficult to pinpoint whether leptons are playing a role in high energy emission or hadrons are playing. So what is the way out? The way out is neutrinos. Okay, neutrinos have recently picked up, and the other possibility is for X-ray polarization. And X-ray, this was launched in 2021, so possibly in exposure also may do, but from the earlier talk I heard it's very difficult to do some polarization using exposure. But irrespective of that, I will try to see how polarization can play a role. Here I have shown the theoretical curves of a low synchrotron peak sources. So here if you see, it's a hadronic origin, the polarization is very high and it increases with energy. Alternatively, it's a leptonic origin, the polarization is moderate and it is nearly zero in the gamma ray band. So in addition to constraining leptonic hadronic scenario, X-ray polarization can also pinpoint what is the particle acceleration mechanism. So if it is a magnetic reconnection, you expect to see low polarization, and if it is due to shocks, one expect to see high polarization of the order of 50%. So polarization can do two things. It can put constraints on particle acceleration, and it can also tell whether it is leptonic or hadronic scenario. And this is the status of IXPE. IXPE has absorbed three sources: Mercurian 421 is a BLAC, Mercurian 501 as well as BLAC. So this is what they found. For Mercurian 421, they found 15%, and they found the X-ray polarization was larger compared to optical polarization. And the conclusion of this X-ray polarization is that the jet is stratified, and X-rays are emitted closest to the acceleration site of electrons, while the optical comes from a much larger region. So this is based on the X-ray polarization of blazars observed by IXPE. So these are the, as of now, results we know only for these three sources. So we also did some SCD modeling of one such IXPE observation of a source, and we found our SCD tend to favor a leptonic scenario. So what I did, I tried to look into potential candidates for IXPE. What I did, I went into the SwiftBAT catalog, tried to identify all sources with a cutoff of 1 e power minus 10. I found, this is the plot for blazars and this is the plot for radioactive Seyferts. I found 5 candidates having flux limits more than 1 e power minus 10 in the case of blazars. We have Mercurian 421, 3C273, SENA, and 3C454.3. Compared to coming to Seyferts, I found 25 candidates, and NGC 4151 is one among these 25. But of course, this is based on 14 to the SwiftBAT band. One can really do one can really look into the new star spectrum and try to see what is the flux in 8 to 30 kV band, so that we can have a more realistic estimate for Polix. So this is how the 25 plus 30 sources are distributed. Here orange is for blazars and this blue is for Seyferts. And this is the summary. X-ray polarimetry of radio quite AGN could provide constraints to the following questions. First is, what is the geometry of the corona? Does the coronal geometry change with time? This is the two. Similarly, if you come to radio loud sources, X-ray polarimetry could provide constraints to the following questions. What is the origin of high energy emission, leptonic or hadronic? And what is the nature of particle acceleration, whether it is shocks or magnetic reconnection? And what is the scope and plans for Polix? Putting a flux limit of 1 e power minus 10, we added a sample of 24 Seyferts and 5 blazars. This sample can refined by calculating the flux in 8 to 30 kV band. Some of the refined sources could be watched upon for flaring state, so that if their brightness is sufficient enough, one can try for Polix. But in addition to polarization observations, to make realistic constraints on models, one need to have observations in the optical or IR in polarization, so that some realistic constraints can be put on the model. So I stop here.
Questions?
Very nice talk. In radio-quiet AGNs, we see scattered emission, for which the polarization is likely to be, is expected to be high. And the fraction of the scattered emission relative to the primary emission depends on the absorption column. Yes. So there is no doubt that the polarization will vary just because of the contribution of the scattered component. In fact, in Circinus galaxy, there is a Compton thick AGN, yes, where the primary emission is almost zero. So high polarization is not surprising.
So in the Circinus galaxy, what they argue, the high polarization, what they see is mainly because of scattering from torus.
Yeah,
that's what they argue.
So unless we correct for the polarization due to the scattered component, yes, saying anything about the corona may not be appropriate.
Agreed. So, but if you are able to pinpoint the primary emission plus the reflection component, if you are able to find that, then we will be able to put better constraints.
Thank you, Stalin. Let's move on to the next talk. Let's thank Stalin again. Next speaker is Ritika Chatterjee.
Good afternoon, everyone. I am Ritika Chatterjee from Space Astronomy Group, URSC. And today I'm going to talk about ATOL and Z sources. What are the IXP results in terms of polarimetry? And what are the prospects that we see from XPOSAT? Okay, yeah. Okay, so neutron star low mass extra binaries, this is the very familiar schematic of a low mass extra binary system. We have a low mass star, and which is losing mass via Roche-Loeb overflow, and then here is a compact object. In this case, it's a neutron star, and then it is accreting matter. And yeah, sometimes there is a jet, and there is also a corona, and whose location and all those things are not very clear yet. So today I'm going to speak about these neutron star low mass extra binaries, and they are very weakly magnetized. So they have magnetic fields of only about 10 power 8 to 10 power 10 Gauss, and they are highly variable sources. So they have variabilities on time scales of say few hours to few days. And okay, so based on their pattern that they trace in the color-colored diagrams, they are mainly classified as ATOL and Z sources. So ATOL sources, they trace a shape like this. They have two states. So this is the high soft state at high luminosity, which is like at high mass accretion rates, they are in the banana state. And at lower intensity, they are in the low hard state, which is the island state. And for the Z sources, they trace a shape like this Z, and they have three branches: horizontal branch, normal branch, and flaring branch. So again, like I mentioned, this high soft state for Z sources, they have very high luminosity, greater than 10 power 38 ergs per second. And ATOL sources, on the other hand, they are found in both high soft state and low hard state. And so from the point of view of the spectrum, usually the spectrum has two components: a thermal component and a non-thermal component. The thermal component might come either from the disk, which is usually modeled by a multicolored black body, or it might also come from the surface of the neutron star, or a boundary layer, or a spreading layer. We don't know. And then there is a non-thermal component, which is Comptonized emission by a corona. Plus, sometimes there might be a reflection component as well. So usually there are these two kinds of models called Eastern and Western models. So here, like schematically shown, these three kinds of, like actually there are many more. These three are the common models of the location and geometry of the corona. So there is this slab or sandwich model, which is the Western kind of scenario, where you see the neutron star directly. So the thermal emission comes from the neutron star, and these represent the corona, and the Comptonized emission comes from these parts. So this was the Western model, and here we have the Eastern model, where you directly observe the disk. The thermal emission comes from the disk, and the corona is here, so it Comptonizes the seed photons from the neutron star surface, and then we observe the higher energy part. And then this wedge geometry is also somewhat similar to this model. So spectroscopically, these three models are often indistinguishable. Like this, all these three models can equally well fit the spectrum. So this is where polarimetry comes in. And so now I'm going to describe some results which we have got about from X-ray polarimetry of NS-LMXBs. So earlier it was thought that because these objects have very weak magnetic fields compared to, say, magnetars or pulsars, it was thought that they may not show any significant polarization. And yes, even though the polarization degrees that have now been found for these sources are small compared to these other sources, the results are very significant because they help us to constrain the geometry of the corona, the system inclination, and many other things. So before I go into IXP results, I want to speak about this SCO-X1, which was observed by Polar Light. So Polar Light was sort of an technology demonstrator kind of mission, which was flown in 2017, I think. And so they observed this SCO-X1, and it is a Z source, and they found that depending on the luminosity of the source, the polarization degree varies. So at low fluxes, they did not find any significant polarization, whereas at high fluxes, they found an energy dependent polarization. Again, 2 to 4 keV was consistent with no polarization, and 4 to 8 keV they found a significant polarization. And also they found that the polarization angle that they calculated, it was aligned with the system symmetry axis, the jet axis. So this was a very significant result. And using this result, they excluded a wedge or a slab-like corona, and they say that the corona is more likely to be a transition layer or a boundary layer corona, because only then can you have a polarization angle which is parallel to the symmetry axis. Now going into the IXP results, IXP has observed about 5 low mass X-ray binaries, neutron star low mass X-ray binaries till now, and for 4 of them there are published results. So I'm just going to briefly speak about them. So first there's this Cygnus X2 source, which is a Z source, and it was found in the normal branch during the observation. And so for both these sources, there was simultaneous spectroscopy done by NICER and Integral, and this is a very important point which will also be applicable for XPOSAT. So in the case of Cygnus X2, they found a similar energy dependent polarization, increasing with energy. And also when they did the spectropolarimetry, they found that the Comptonized component is polarized, whereas this component is consistent with unpolarized. And from their analysis, they found that a Eastern kind of model scenario is more favorable. On the other hand, for this other source, GS1826, which was an atoll source, they did not find any polarization signatures. But even then, because of some available models, which I will show later, they could put constraints on the inclination of the system and also comment on what are the possible geometry of the corona. So next, I come to these 2 sources which we looked at recently. GX9+9 was an atoll source, is an atoll source in the high soft state. And this other source, it is kind of a unique kind of neutron star low mass extra binary because it shows both Z and atoll kind of behavior. For this source, there were simultaneous observations from NICER and NuSTAR available. So they were actually TO observations, so they were available soon, and then we could do the analysis. For this, there was no simultaneous observations, but AstroSat had observed it, I think in 2021. But since this source is a very stable kind of source, and we also compared the color diagram, and then we found that during the IXP observation and the AstroSat observation, the source is in the same state. It is usually a very stable source. So we could do the spectropolarimetric analysis using AstroSat data. So in case of GX9+9, again we found an energy dependent polarization degree here. And we also found that the Comptonized component, which is shown here, is polarized, whereas the disk component is unpolarized. And from this analysis, we say that a shell type corona is favored. And for this source also, we got similar results, a similar increasing kind of polarization degree with energy. And then in both cases, MCD, which is a multicolored disk, and a Comptonized component was found to fit the spectropolarimetric results. Okay, another important result that we had for this source is IXP observed this source in 2 epochs. In the first epoch, we found these kind of results. 2 to 4 keV and 4 to 8 keV, we see an increasing trend. Whereas in the next epoch, we found that the Comptonized component, the NTH comp component, it has weakened. And during that epoch, we do not find any polarization. So that is another significant result which says that the polarization is coming from the Comptonized component. Okay, so these kinds of comments that we have been making about the geometry of the corona, that were possible because of these simulations which are available. It's like, so you give the input parameters like the neutron star physical parameters, accretion parameters, and so on. And then you get what are the expected polarization degree and angle for different kind of geometries. So here you have slab geometry, shell geometry, and at different states, low hard state versus high soft state. And these simulations can be done at different viewing angles. So from here we can see what are the approximate trends. So although the results that we obtained, these numbers do not match exactly, but that might be because of the specific parameters which were used for the simulations, but we can see the trends and we can distinguish between the different models. So yeah, coming to opportunities with XPOSAT. So there are a number of neutron star low mass X-ray binaries which are among the 54 sources, and among these about 5 or 6 of them are planned to be observed in the first year. And so basically the main science goal would be you have long duration observations. There are low mass X-ray binaries which have many state transitions on these timescales, and you are able to do branch result spectropolarimetry. So this is a very important science goal that I see. So we can find the geometry of the corona in different states where spectroscopy is degenerate, but using the polarimetric information, we can talk about what are the different physical properties of the source. Again, at all sources, as I mentioned, they show this low hard state. So in the hard state, the spectrum extends to like, say above 30-40 keV. So Polix will be the data from Polix will be a very useful thing to assess that data. And yeah, this Comptonized component, this is also related to the geometry of the corona. As for the reflection component, for Z sources, we might have the reflection component at say around 10 to 15 keV. So we can see them using both expect. So the spectrum we can see from expect, and polarization properties we can get from Polix data. And we can diagnose the system geometry as well. So yeah, as for simulations, the impetus is currently on the science community to have more simulations. Like as I showed here, these simulations are only till 10 keV. But now we need to go into yet another unexplored region of the energies and then see what kind of results we get to diagnose the system parameters.
Ranjiv.
Quick question, that simulation which you showed, that Monk simulation, is it the simulation available in public or is only the results?
Yes, the simulations are like the code is available in public domain.
Oh, even if the codes are available, they are only till 10 kV.
Actually, I have not explored that, but one of my colleagues recently explored and he said that the simulations are available, but yeah, he has not yet.
I mean, you can't extend to, I mean, there's no parameter to extend the high energy.
I think it can be done because that other paper, Schnittman and Froelich paper, I think they also use the same simulation code. So there also, it extends till 100 kV. So I think these simulations.
Generic, and it's available in public domain. Okay.
There are problems. You have tried some
Anyone else?
Some codes where it gives some arbitrary result above 30-40 kV. So there are some assumptions which could have been built in which may not be valid and things happen. So you have to validate that before using it to a higher level.
True.
Thank you, Ritika. One second. And we now come to the crucial part, the modeling requirement. So I now invite Indranil Saji for Chattopadhyay.
Thank you very much for this opportunity. Had I known that what Santosh is going to talk about, my talk would have been a little different. So I am very cautious in this talk, so balancing everything. All right, so I actually prepared a lot of slides, and last night I threw all of them away. And I'm focusing on what I have not done, that is polarization. So, what is our broad understanding about the environment around compact? Our broad understanding is that the matter around compact objects will fall into it because of strong gravity. And infalling matter heats up and therefore should produce radiation. However, if you feed the compact objects like black holes or neutron stars with matter more than they can eat or they can consume, they will eject part of it, is basically what are jets and outflows. And if jets and outflows are to be ejected from system, they have to be accelerated. And accelerated matter being passed crashes onto the ambient medium and will again produce radiation. Okay. Now, the emitted radiation spectra gives us the information of energetics of the source. The time variation gives the information about the dynamics of the source. And the polarization gives the information about how subtle this interaction of these photons with electrons and magnetic fields. And that exactly is what, of course, within a certain energy range, our satellite Exposat going to do. Okay. So, since I threw off a lot of material, so I will just focus on 4 aspects which can be, it doesn't matter whether this is focus, the primary focus of Exposat team or not. But what can be done is interaction of the disk radiation with the jet. You can study that. Physics of jet emission itself. Physics of accretion flow emissions from around black holes vis-a-vis that from neutron stars. And again, we can study isolated rogue black holes, neutron stars that are traveling through the ambient medium, and they accrete matter, and they also start to emit. So, what kind of emission, these kind of objects which are hard to detect. Of course, again, Exposat will not be seeing these, but I'm saying that overall, what are the topics that can be studied? Okay, interaction of accretion disk radiation with relativistic jets. So you have an accretion disk, forget about what is the geometry, and you have these jets, and there's a lot of radiation, intense radiation that is going, this around, and the jet is moving through it. And if the jet is moving with relativistic speeds, because of something called aberration, they will see, if you do the angular transformations, they will start to see the sources in front. So although some of the radiation is pushing it from back, there is also a part of the radiation which is holding it back, which is called the radiation drag. But then, because it is of the transformation, the angular transformation, or which is the aberration effect, and the disks have finite size, if it actually moves slightly ahead, say a few hundreds of Schwarzschild radii above the central object, then it will start to cease, the radiation drag effect will start to cease, and it will actually start to accelerate the jet. So you just put theta prime being the angle of ejection of the photons in its rest frame, and then theta is observed frame. So you just do theta prime when it goes to start to 0, theta is also goes to 0. All right. So, and this is the radiation drag term, radiation term, and this is the drag term, and this is the accelerating term. I've just simplified to 1D to make it understandable. And we indeed find very, very fast jets. This particular case is a Lorentz factor of, we achieved the Lorentz factor of 63 or something. All right. So this is a simulation of these jets. Now, if the accretion disk itself is oscillating and it's time dependent, then the radiation field that is produced is also time dependent. So what will happen? But radiation travels with a finite speed. So it will, the radiation when the disk when it is in a certain state, and it starts to change the state, the radiation field is also changing, but it will affect the portion of the jet which is nearer to it, and it will not affect the portion that is far away from it. Okay. So, and that what it will do, at some times the lower portion will be accelerated faster than the portion which is ahead, and they will clash and will produce internal shocks. Okay. So, in all these studies, it was actually done for a different purpose. What we have not done is track the photons after it interacts, what does it do? Now the jets being tenuous, if the radiation itself is polarized, then it will at best, scatter once. And if it is a single scattering, then the radiations emitted will also be more or less be polarized. Okay, so these radiations will be more polarized, number one. Number two, the radiations are very hot which are coming. They interact with the photons, the electrons of the jet, and they will lose energy and will come out to around this 15 keV region. Okay. So that means again it falls in the expect region to look at the at its spectrum. So POLEX and expect will be good. These kind of instruments will good thing to study these kind of interactions. Okay, so now let's say accretion disk. So what is 2 temperature? Forget about the physics of it. And basically electrons radiate and they will settle into some temperature, and protons